see the screen. Okay, it's going live.
It's nice. There are a few ELLIS PhD students. That's nice.
Okay, I believe we are live on YouTube, so maybe we can keep starting. So hello, everyone. So I'm talking on behalf of a bunch of people like Plamen Angelov, Uman, Hima, Nuria, Stratis, and Adrian, all are organizers of this second edition of the Human-Centric Machine Learning Workshop that is sponsored by ELLIS. And my audio was actually doing from YouTube my own voice, so I just stopped it. So only to let you know, since I said this thing of YouTube, this workshop is being recorded and is live streamed in YouTube. So if you enter the Zoom meeting and it happens that you ask a question, you may be recorded or you may be live streamed. That is why we give the possibility also, if you like, you can actually watch in YouTube and you are completely anonymous. So what is the motivation for this workshop? Is the following, no? That human-centric machine learning is a kind of a young new field that many people in machine learning are excited about. And a big idea is to try to design machine learning algorithms that are trying to maximize the societal benefits of machine learning systems. And at the same time, we would like that the potential harms are actually minimized. This is a very broad topic. And in this workshop, we decided to kind of focus on two themes. One of the themes is the differential treatment of historically underserved and disadvantaged communities by algorithms, and more specifically by machine learning algorithms, and also the development of machine learning algorithms to assist humans rather than replace them. So we have like a packed schedule that we are excited about, but also a bit afraid about the timeline. So we will try to keep the talks in 20-25 minutes with a few minutes for questions. And the questions would be moderated by a presenter of the speaker. So we have 5 speakers before the panel, that is before 5:30 p.m. in the UK. And after the panel, we have another 5 speakers. These speakers cover the two themes. They have different seniority levels, they have different backgrounds, and we hope that they give different views about human-centric machine learning. And regarding the panel, it's something that we decided kind of in the last minute, given that was quite timely to discuss a little bit about this new European regulation on AI. So we convinced an officer from the European Union, Gabriele Mazzini, to give a bit of an overview, and after there will be kind of a discussion between several researchers, both in industry and also in academia, and even a lawyer. Okay, and without further ado, I think I'm the presenter of the first speaker. That is going to be Francisco Marmolejo. So I'm going to stop sharing the screen. And Francisco, I guess if you are around here, maybe you can.
Hi, Manuel. Can you hear me?
Yeah.
Perfect. Let me try to share my screen then. Can everybody see my screen?
I think they can. Okay, let me just give a brief introduction. So Francisco Marmolejo is a career development fellow in the University of Oxford, and is also a research fellow and input output.
Manuel, you went on mute.
Without further ado, I realized I went on mute when there was the sharing the screen. Francisco Marmolejo is a fellow in the University of Oxford and also a research fellow in Input-Output Hong Kong. And without further ado, I believe he's going to talk about mechanism design for social good. So you have the stage.
Thank you so much, Manuel, and thank everyone for having me. It's a real pleasure to talk about these incredibly timely topics that you've mentioned. So today for this talk, I want to talk about two very related themes. So the first, I'll be talking about mechanism design for social good, which is a research initiative that I have the pleasure of being a co-organizer for. And I'll then segue into a specific research topic that I've been working on for the past year that exemplifies work from mechanism, that was born out of mechanism design for social good, and that exemplifies a lot of the research questions that we're mentioning here for the workshop. So it'll be very interesting to have a discussion around some of the points regarding the work and mechanism design for social good overall. So just a brief overview of the talk. First, I'll begin by talking about MD4SG, giving an overview of the organization, of the objectives of what we do. And I'll segue into the project, which is called Test and Contain, which, as the title of the presentation mentions, is about optimizing or bringing an optimization approach to resource allocation in COVID testing. And in particular, it's applied in Mexico, where I'm from. And I'll talk about this project, the idea, some of the paths and turns that we've taken to make this more human-centric over the course of the past year, and by giving a current status of the project, some next steps, and opening up the floor to discussion around these interventions that use interdisciplinary techniques for healthcare benefit for marginalized communities. And so just to begin talking about MD4SG, mechanism design for social good, it's an initiative that's been around for roughly 5 years now that has multiple key facets. First of all, it's multi-institutional. We have individuals from multiple organizations around the world, not even necessarily academic institutions, but also working at NGOs, policymakers, et cetera, that employ a slew of multidisciplinary techniques, ranging from algorithms, optimization, machine learning as well, to fundamentally tackle the problem of access of opportunity in marginalized communities. Again, very much in line with the theme of the workshop. The fundamental theme is improving access to opportunity and bringing together these different individuals from around the world, from different walks of life, the very stakeholders of the communities that we wish to help, and using as many tools as possible to tackle these very difficult, multifaceted problems that are of deep importance to these communities. And what makes MD4SG distinctive is, again, first of all, that we bring individuals from different walks of life, different careers, different levels of seniority, as well as you mentioned. But perhaps most importantly, that we bring together the very stakeholders that we wish to work with and help. And this approach allows us to improve access to opportunity for these communities and allows us to provide end-to-end approaches to these very complex, multifaceted problems, while fostering diversity, equity, and inclusion in the space of machine learning, optimization, computer science, and STEM in general. And before continuing, some of the core MD4SG activities that we do to promote the discussion around these end-to-end approaches to helping these communities, because it's important to have a general discussion from all levels, is we have working groups, colloquium speakers that talk about research that is exemplary in their field, workshop series over the past 4 years. We have tutorials at various conferences. And this year, I'll talk more about this at the end of the talk. We'll actually have an inaugural ACM conference on equity and access in algorithms, mechanisms, and optimization. But really, the working groups is what I want to focus on right now at the beginning, because these are the core of MD4SG and a backbone of the community and are a pillar of conversation to around the very topics that we discussed. We bring together researchers, practitioners, and stakeholders around specific topics of interest from multiple countries around the world. And the project that I'm about to talk about was actually born specifically out of a working group, out of this backbone of the community. And I just put here on this slide actually some of the working group collaborations that we have in the organization. But in particular, the project on test and contain and on COVID testing was born out of the Developing Nations Working Group. And in fact, right after this talk, we'll actually have the pleasure of hearing from Chinasa Okolo, who is currently the organizer of this group. And again, the aim of these pillars of research of MD4SG is to bring together people from different walks of life to use these perspectives to give us a more holistic approach to, again, not just the problem, but the very solutions that we want to bring to the table, be it a solution that employs algorithms, machine learning, optimization, et cetera. And so without further ado, the project that I want to talk about is, we've called it Test and Contain, but it's a collaboration with researchers from the University of Oxford, who form a part of the MD4SG group I mentioned before, but other research institutions within Mexico, my home country, and in particular, my home state of San Luis Potosí. So we have the IPCIT, Autónoma de San Luis Potosí, and the Tecnológico de Monterrey. And the main problem that we started working on last year was we're in the pandemic, of course, has been at the forefront of everyone's minds for quite some time now. But at the beginning of the pandemic, it became clear quite quickly that accurate and extensive testing of the population was an important tool to combat the virus. We saw many successful cases of countries implementing a tracing procedure, again, with various amounts of resources and with various degrees of success. But the reality, in not just in countries such as Mexico, but in multiple places around the world, is that resources are extremely limited. They fluctuate in how limited they are. And this doesn't necessarily just mean testing resources, but this could also be trained personnel. It can be lab time. It can be the overall just infrastructure constraints that we have. And the question that we sought out to work on at that moment of time was, how can we help policymakers maximize the benefit of these resources when they're extremely limited? And again, we're talking about the context of what was happening in Mexico at the time and happens in many other places around the world. And in order to maximize the benefit, or to help policymakers maximize the benefit, it's important to take a step back and, again, have a conversation around the potential objectives of this object that we're trying to allocate. And upon our discussion with individuals within our working group, individuals from the community as well, we've isolated two potential objectives that it would be interesting to highlight the trade-offs between these two objectives when choosing testing allocation strategies. And the first of this is that, well, a testing strategy, using tests, of course, is with the aim of minimizing the propagation of the virus. We have many asymptomatic cases that could spread, and we've seen this happen across the world. And by this, of course, we could think of allocating tests to individuals who are potential super spreaders, or to monitor vulnerable segments of the population. But at the same time, another thing that's become abundantly clear over the course of the pandemic is that the impact of quarantine and self-isolation has been massive, not just at a financial level, particularly also for disadvantaged groups of the community, but also at a psychological level as well. And so another objective that we wanted to focus on was also minimizing the impact of these self-isolation procedures. And this, of course, means taking into account what it means for a worker to be essential or not, who is essential, who isn't, who has perhaps the economic means to self-isolate. And again, teasing apart these potential different segments of the population that suffer more or less from quarantine, from these policies. And the fundamental primitive that we use in our family of solutions is group testing. And for group testing, it's a simple testing primitive where essentially one takes samples from multiple individuals. You can mix them into a single sample, and then you perform a single test on that mixed sample. Now, this test will either be positive or negative. If it's positive, this tells you that somebody amongst those individuals from mixed samples is infected. And if it's negative, you know that everybody is healthy. So this has the potential to drastically reduce the number of tests that we need to tackle these objectives you mentioned previously. Now, as an example, and this is not a new idea, this has been around since the 40s, actually, since Robert Dorfman came up with a protocol for testing syphilis. And the protocol that Dorfman proposed is just a good example to elucidate the potential power of group testing, but also mention some key limitations that we tackle. And so this typical protocol, Dorfman's two-stage protocol, is very simple. Essentially, you can imagine that you have a population, which is this box of size n, and it proceeds in two stages. In the first stage, we randomly create buckets of size b, where b individuals are in every single one of these boxes that I mentioned, and we perform a group test on every single one of these boxes. Now we might see some positive boxes, some negative boxes, some positive boxes, negative boxes. And in the first stage, we know that the individuals who are infected are narrowed down to the positive boxes. Now in the second stage, we simply go by and individually test everybody inside these boxes, and we're able to know precisely who has the virus and who doesn't have the virus over the entire population. But what's most interesting is that this can actually be optimized. And if there's some knowledge on the infection rate of the population, you can choose your initial bucket sizes in an optimal way to effectively know who is infected and who isn't in the population with much less than n tests. And the groups that we use could actually don't have to be random. They can even be households, for example. Now, this is all wonderful, and this is a very first example of some of the strategies that people use group testing for to reduce the number of tests that are needed to know who is infected within a population. But the thing is that in practice, even though these provide us some earnings or some efficiencies over the number of tests needed, in practice, we are far below even the tests that are required for Dorfman's method, or even the most advanced methods for using group testing to perfectly know who is infected and who isn't in the population. And the reason for this is that much of the literature actually begins with the goal of using tests to find out precisely who is and who isn't infected in the population. And the thing is, we are far below that, the lower bound of what is required for that objective. And so rather than starting with the population and trying to find out who is infected and who isn't, well, instead, what we propose is actually starting with this budget, this inherent budget that we have in hand, and trying to find out what the benefits are of different strategies of using this budget in different ways. And of course, this means having to relax precisely knowing who is infected and who isn't. But what we relax is precisely knowing the diagnosis of at the individual level, which is what group testing provide us. And with this, actually, simple mechanisms can give improvements and can give and can exemplify actually the trade-offs over the different objectives that I mentioned before. And so I guess we can start with, for the model and assumption, it's probably best to actually go through a possible scenario, which is something that and again, this is a toy sample, but it highlights the trade-offs that we're trying to help policymakers deal with. And so in this toy example, imagine that we have a university of 10,000 individuals, and of these individuals, 20 are academic staff, 480 of them are cafeteria workers. There's a single cafeteria at this university where individuals congregate quite often, and there are 9,500 students. Now, you're a policymaker at this university, and you have 500 tests at your disposal, which is far below what you need to know who does and who doesn't have the virus. And of course, there are biological limitations to how large group tests can be, which what we've seen here at Oxford and actually passed on to universities in Mexico is that 10 is a size that we're safely able to push group tests up to. And the question is, what are good testing strategies given these characteristics of the population and these constraints? Now, the mechanism that we look at is actually basically just Dorfman's protocol, but without the second stage. We essentially consider disjoint group tests across the population in different groups. And if a test is positive, we simply tell all the individuals in that group to self-isolate. And if it's negative, we allow them to continue as normal. And notice that since we're telling a positive group to self-isolate, we run the risk of there being a healthy individual in that positive group. That can happen. And this is what we call an unnecessary self-isolation. And it's in a certain sense, it's a necessary evil to the limited budget of tests. And what we do, according to the objectives we mentioned previously, is that we measure the performance of testing allocations in 4 metrics. Over a randomized model of contagion, which is how many critical cases of COVID are prevented, and per segment of the population, how many individuals of that segment are unnecessarily self-isolated. Now, what are some current practices? Well, if a policymaker is conscious of academic staff, they might allocate, say, 20 tests to the academic staff. Perhaps they really need them to run courses, otherwise the university can't open. And this way, you know perfectly who is infected and who isn't in that segment of the population amongst professors. And otherwise, if somebody is showing symptoms, a test can be done to confirm whether they're infected or not. Now, these aren't very informative in this setting, and there's a bias in the result, and many cases go unnoticed. And so we can look at the performance of this strategy under kind of these 4 metrics that I mentioned before. Namely, we prevent very few cases, but at the same time, there are no unnecessary self-isolations because essentially life is as normal and we're simply confirming cases that are positive, in which case that individual isolates after being confirmed with COVID. Now, we can improve upon this with group testing. And a naive thing that we can do is simply, well, we can do groups of size 10. We have 500 tests. Why don't we just randomly pick 500 groups of size 10 from the university and place them into group tests? And again, if positive, they self-isolate, and if negative, they continue as normal. Now, the benefits to this are that we cover a much larger percentage of the population. We can actually estimate the prevalence of the virus as well if we perform this randomly. But if you recall, I mentioned that the cafeteria, for example, is a place of congregation. So we might miss a potential super spreader if they're not covered under a test. Or it may be the case that a professor is in a larger group and the university needs professors to actually hold courses for hybrid teaching, in which case there might be some unnecessary self-isolations in that segment, which may be undesirable to the policymaker. And so if we map this performance as before, we can see that we catch more cases, but we have some unnecessary self-isolations in segments across the board. Now, what we propose actually is, so the space of solutions that we look at is differentially allocating tests and at different group sizes to different segments of the population, according to the characteristics of the segments of the population that are provided to us by the university. And these characteristics, of course, have to do with the infection propagation, but intrinsically, the university has some knowledge over the impact of self-isolation on these segments. Now, a potential testing strategy in this family of mechanisms would be to say allocate 20 tests individually to academic staff, to allocate 96 tests of smaller group size, of size 5, to cafeteria workers, and the remaining tests to students. Now we can see that in this case, since we cover all of the cafeteria workers, we actually catch a lot of cases, and so our healthcare objective improves. And we, since we're testing all the academic staff at size 1, none of them are unnecessarily self-isolating. But notice that we chose group sizes of 5 for the cafeteria workers and 10 for students. This means that it's more difficult for a cafeteria worker to be caught in a positive group because they're smaller. So they perform better. There are less unnecessary self-isolations amongst cafeteria workers. Now, at the same time, perhaps the policymaker actually finds it highly undesirable, or is actually has some slack in terms of the self-isolations of cafeteria workers. So part of the flexibility in the regime is that they can actually pump up the group size of cafeteria workers to size 10. This means that they cover them with 48 instead of 96 tests, and this allows them to allocate more tests to the student body. And we see actually if this tweak is done, then we improve on the healthcare objective because we have more tests open to test students. But at the same time, this comes at a cost. We have potentially isolated more cafeteria workers because they're in larger group sizes. Again, this is best understood when all of these are put side by side, where essentially we see the performance along these multiple objectives. And in fact, the most salient feature is that this strategy over here is in fact categorically worse amongst all objectives than these 2 strategies over here, which is in this multi-objective approach, which is perhaps what is best for policy, for decisions on policy, is it's dominated, it's Pareto dominated. And what we do for policymakers is that we filter through solutions that are dominated amongst one of these axes, and we present all these other solutions as fundamentally exemplifying the trade-offs between different strategies, because there are inherent trade-offs. We've created a web application for our partners in Mexico that are to be implementing these pilots in the coming months. And this fits very much in line with one of the axes of this workshop, which is we very quickly saw that actually it's very important to put the decision into the hands of the policymaker. And this Pareto front approach is actually very useful for helping them filter the solutions and understand what are the inherent trade-offs in differential allocation strategies for COVID. And so just to kind of wrap up a little bit on the project, so the current status, as we've actually implemented the group testing protocol from here in Mexico, we have data collection pipelines from our partners that are working with the government in the state of San Luis Potosí and at the different campuses in the Tec de Monterrey. And one interesting final point is we have a nascent collaboration with the medical school where the goal is to open up schools in disadvantaged municipalities. And in the spirit of MD4SG and in the spirit of human-centric machine learning, where the fundamental part is actually talking to the community. So we're having workshops, teaching them the core ideas of the methods, but actually getting a fundamental feedback loop for a potential second iteration of resource optimal ways of allowing schools to open in these communities within San Luis Potosí. And again, just to end, this is an example of the approach that we take within MD4SG to have these interdisciplinary collaborations we have individuals from biology, from computer science and in Mexico and here, and the very stakeholders of the communities that we want to work with, working towards the solution of mitigating the impact of the virus. And again, this is work that was graciously been funding by SIGICOM, and again, has helped foster this collaboration between Oxford and these various universities in Mexico. And I'd just like to end kind of going back to MD4SG and how this global organization, these very conversations can help at the practice level tackle these questions that are core to the HCML community. Thank you. And yeah, I guess I can open up the floor to discussion, but I guess just a quick second before opening up the floor to discussion, I want to make a quick, just also mention that I mentioned before that we have our inaugural conference for MD4SG. It's on equity and access and algorithms and mechanisms and optimization. Again, highlighting much of the conversation that is happening around the topics for the HCML community. And it's to take place in October, and there are 2 different tracks in research, but also policy and practice, again, facilitating policymakers with the decisions that they have as well. And there's a submission deadline on June 14th, but I invite people within this community to take a look at this conference and to hopefully engage further with MD4SG. And we hope that we can engage further because this conversation is a very important one to be had overall. But thank you. I guess I don't want to take up too much time and perhaps open the floor to some discussion as well.
Thank you very much, Francisco, on behalf, I guess, of everyone. There are several questions that were typed in the chat. So I'm going to just read who asked the question, since there are currently 3. Maybe we can have even time to go to the 3 of them. So Crikamol Muandet was asking whether you have any assumption on the accuracy of the test and how sensitive is your approach to this assumption, if any.
That's a wonderful question. And as of now, we don't have an assumption on the sensitivity because that comes in at the biological constraint level. Essentially, our partners at the EPC in Mexico have proven that the method works up to group sizes of size 10 with I forget what level of sensitivity, but the standard level of sensitivity for the tests. Granted, it's a very interesting direction to think about how the sensitivity works as a function of the group size, because of course, the moment that you push this past 10, which can be done, you suffer on that. But this is perhaps and as computer scientists, actually, we do think about perhaps this would be best, if you have a test that's actually only 50% accurate or something, but you're pushing up the groups up to size 60. This actually could be interesting in certain regimes, but for now we haven't incorporated that just yet. We do have the models that we have are amenable to this. But for the sake of actually just fitting in with existing policy in Mexico and implementing a pilot, we're currently keeping it at the kind of safe levels of group tests that fit with current policy directives.
So a follow-up that I guess is a bit related. Harsh Nisar was asking whether you can throw some light on the simulation setup used for different circumstances or experiments. It's kind of a rather broad question, so I guess you can interpret it as broad or specific you want.
So I guess this is on simulations that are used for COVID in general, or the ones that we use in our approach to compute the objective values.
From reading the question, I assume it's for your work.
Okay, that's a great question, because for our work, so for the initial stages, actually it's a myopic strategy in case where basically we're given a testing budget, and we model the community as essentially as a graph. Well, individuals form parts of different clusters, and they have different connectivity amongst other segments of the population, which is inferred from, say, the classes that are taken by individuals. So we know that, for example, engineering students take classes with this professor, and we know who is an engineering student, let's say. And so we get kind of a sort of interaction graph that is used to model a single step of contagion in where if an individual is infected, they have a certain probability of creating another infection across an edge. And subsequently, there's a probability of critical cases given infection. So that we in the current model, we compute all of these quantities and expectation over the randomized realization of the virus. But we are also currently working on, and this is future work, on a reinforcement learning approach that would use existing simulations of the virus, and rather than compute things in expectation, actually have multiple runs of the simulation of the virus, and use these to train a policy in hindsight. But we have also seen, so we've run some SIR models over segmented populations with different levels of interconnectivity, and the policies that the Pareto Front has exemplify actually the trade-offs that they supposedly exemplify an expectation in a single step of the process. So, but there's definitely a lot of work going forward in that direction to incorporate other simulations for sure. I hope that answers the question.
We have time for just one last question that Preeti Lahoti was asking whether, I mean, I guess it's a bit related, whether you could expand on the relationship between the Pareto Front and variables such as prevalence, the error rates of COVID tests, that I guess was already the first question, or any other kind of variables that can be, let's say, acquire different values.
Mm-hmm. No, definitely. I mean, so for example, one of the variables that's important is, I mentioned, for example, these potential super spreaders. So a segment of the population could have a high degree of connectivity to other segments of the population. And consequently, any strategy that does not allocate many tests to that segment of the population runs the risk of there being an infection that is not caught and therefore gets passed to many other individuals. So solutions on the Pareto Front, well, there are a multitude of solutions on the Pareto Front that don't do this will have a poorer showing on the healthcare objective. At the same time, of course, if we want to cover that segment of the population with more tests of larger group sizes, we could pay for this in terms of unnecessary self-isolations in that segment. But all of these will essentially appear on the Pareto Front. And the way that we help policymakers filter through these is by allowing them to pick what performance they would like for every single one of these objectives for things that are on the Pareto Front. And they slowly refine, they're able to compare solutions side by side and slowly refine and see where these trade-offs actually come by in the allocations that they can pick.
Okay, many thanks. And yeah, a round of virtual applause from everyone. Yeah, it's my pleasure to maybe leave Stratis, that is one of the other peer organizers, to introduce Chinasa. Thank you.
Thank you.
Hello. I also wanted to thank Francisco for the excellent talk. And I want to introduce our next speaker. Our next speaker is Chinasa Okolo. And she's a PhD student at the Department of Computer Science at Cornell University. Her research interests include AI ethics, computer vision, global health, and information and communication technologies for development. In her research, she leverages computer vision techniques to improve community health in low-resource regions. And she also works on research projects to analyze the applications, implications, and perceptions of AI-enabled technologies deployed throughout the Global South. In her talk, she will talk us about optimizing for human-centric AI in the Global South. And without further ado, Chinasa, I think you can start.
All right. Hi, everybody. I'm very happy to be here today. And Thank you so much for the great introduction, and I will get started. All right, so recent advances in artificial intelligence have increased the potential for AI applications to transform healthcare in the global South. However, as researchers and technology companies rush in to develop AI applications that aid the health of marginalized communities, it is critical to consider the needs and perceptions of the community health workers and other stakeholders that will be involved in integrating these AI applications into the essential healthcare services provided to low-resource communities. Additionally, as a lack of AI policies within the global South leaves room for something, as we know or heard of, as algorithmic colonization by outside entities such as very large tech organizations that are mainly based in the West. Structures that guide the use of AI will ensure that these technologies cause no harms to the populations they intend to help. Empowering such important stakeholders, such as community health workers and other frontline workers who will be the primary users of AI systems in low-resource regions, is a huge part of my work. In work that I'll be discussing on future slides, we focus on, my collaborators and I, focus on the question of designing practical AI tools and systems for use in marginalized communities. I'll discuss a study that I conducted last summer with community health workers in rural India to understand the perceptions of AI in their work, on their communities, and for their livelihoods. So just to give a broad introduction of AI in the global South, we see that as it continues to spread widely into domains such as agriculture, government, and healthcare, most conversations regarding its implications focus on communities in the global North, such as the US and Europe. But as nonprofits, tech companies, and governments rush to build and deploy AI systems, failing to examine the knowledge, needs, and perceptions of the frontline workers who will be expected to operate these systems, risk deploying AI in ways that lead to extra work and inefficiencies, or that could harm the very communities that they intend to serve. And just to also continue with an introduction for community health workers, also known as CHWs and technology. So we find that the shortage of qualified medical professionals in many low-income countries has led to the establishment of programs in which community health workers provide essential healthcare services in hard-to-reach communities. In this paper, we focus on CHWs, who are also known as ASHAs in India. And we were in Uttar Pradesh, which is like the Bangalore area. And so we've seen that prior work has shown that community health workers, CHWs, are essential in delivering healthcare services, and also that mobile technologies play an important role in their work. Nowadays, we see technology becoming an even more important part of their work. For example, in India, the government has introduced contact tracing applications and other applications that are enabled with AI. And so community health workers are rapidly becoming accustomed to using and working closely with these technologies. So these community health workers are likely to be the target users of AI systems around the global South that aim to improve the health of marginalized communities via, for example, things like AI-assisted disease prediction and AI-assisted diagnosis. Thus, as advances in AI lead researchers and tech companies to develop AI applications that target the health of marginalized communities, we find that it's crucially important to study how do community health workers perceive AI and what are its anticipated benefits and challenges. So in our paper, it is published at CHI, the Conference on Human Factors in Computing, this week, which I'm very happy about. And so we talk, just to give you a brief overview of our methodology, we present a qualitative study that examines the AI knowledge and perceptions of community health workers in rural India. So we created an exploratory video provocation in which a community health worker visits a mother and her sick child. The CHW uses an AI-enabled app to scan the baby and then diagnose them with pneumonia. To encourage balanced and diverse responses, we created two versions of the video: a positive scenario in which the mother embraces the use of the AI application on her child, and a negative scenario in which the mother is both suspicious and distrustful of the AI application. After viewing one of these videos, the 20 or so community health workers in our study participated in a 40-minute semi-structured interview. So to talk about some of our findings, the primary thing that we found, or the main finding, was that CHWs don't have much knowledge of AI, which we expected because a lot of them in this region actually, don't have a lot of experience working with, either like mobile devices or even computers. But despite their low level of AI knowledge, we saw that they do have opinions, a lot of opinions regarding the perceived impact of AI on their workflows in their communities and for their livelihoods. So CHW's low levels of AI knowledge is very concerning, especially given that there are already AI applications being developed to target their work. And we've seen that in some cases, AI-enabled technologies have already reported failures when deployed and integrated into low-resource environments. And I'll talk about a study that where we see an example of this in the future, in future slides. And so we saw that, these technologies at best created additional workflow inefficiencies, and at worst, harmed the communities that they actually intended to help. We also see that the community health workers agreed broadly that an AI app may not be able to accomplish, actually would be able to accomplish some of their tasks, but they thought that it would never completely replace the breadth of activities they perform, including consultations, immunizations, and culturally sensitive discussions on breastfeeding and family planning. And I think this is also a very important finding of our study, because a lot of times we see that AI is kind of introduced or just like integrated into a lot of environments, especially in healthcare environments, with the goal of replacing practitioners or physicians or radiologists. And so we find that in some regions, it's actually much better to use AI as a complement rather than a replacement. And again, some of the, I would say the factors that the community health workers in our study mentioned are very important, just because a lot of topics such as sexual health, birth control, family planning can be taboo, and having to delegate these responsibilities to a machine or an AI tool wouldn't be very effective in helping the community with their respective problems like these. So another finding is that we saw that many CHWs felt that having the AI app perform tasks for them would make their work much more efficient. And this would save them, both them and their patients, valuable time when making decisions about if and when to seek further medical help. We saw that participants quickly identified that the improved efficiency would be especially useful in rural or remote villages that may be located far away from hospitals or healthcare centers. Additionally, the community health workers felt that this app could be used for training them and also solving problems far beyond its capabilities, like COVID infections, which is very, relevant at this moment. And so again, another important finding, I think that a lot of the trends that we saw regarding like this theme was that the community health workers, felt basically like underappreciated in their work. And so there were a lot of things about like surveillance and tracking, but the government is the main employer of ASHAs or community health workers in India, or like in NGOs, non-governmental organizations. And so they felt that, having the government be able to see like the scope or like the breadth of activities they performed would be helpful in, potentially providing them with more resources, especially financial resources and compensation for their work. So to talk about a major contribution, we see that, for HCI4D, or also known as Human-Computer Interaction for Development research, it should have a deep understanding of local context, but we see that AI technologies present new societal risk and complexities that must be proactively studied before attempting deployment of these new technologies. And so concerns raised by our findings suggest that CHWs may trust the AI's expertise more than their own, perceive it to be infallible, and also ascribe to it more capabilities than it possesses. These utopian views can have far-reaching consequences if, for example, CHWs act on incorrect predictions instead of challenging them. In our study, we highlight opportunities for HCI and AI researchers interested in deploying AI with communities in the Global South to both understand the challenges of developing AI systems that respect diverse communities' cultural and value differences, while ensuring both safe and equitable outcomes in the design, development, and deployment of these systems. So next, I'll talk about another research question I'm interested in and have begun pursuing somewhat, is that how are AI deployments evaluated in low resource contexts? In this section, I'll talk about a deep learning tool that was deployed in the Global South and the dangers that arise when centering Western contexts in the design and development of machine learning systems. So, motivated by issues with screening for eye disease in Southeast Asia, researchers at Google AI or Google Health applied deep learning techniques in the creation of an algorithm to detect diabetic retinopathy. The goal of this algorithm was to shorten the often weeks-long process of needing an ophthalmologist to review retinal images. With the algorithm showing over 90% sensitivity and specificity, it was perceived to be comparable to a physician. So to evaluate this algorithm in clinical settings, researchers from Google Health conducted a human-centered observational study in partnerships with 11 clinics in Thailand to analyze how the introduction of this algorithm impacted clinical workflows and the factors that affected algorithmic performance of the system. While the system was thought to be beneficial from preliminary results seen in the lab, it was only useful in the clinics when it actually worked. Despite the researchers performing fieldwork both pre and post deployment of the algorithm, there were significant issues that occurred in the integration of the system. A major finding from the study showed that the system poorly handled low-quality images taken in the clinics, as the underlying algorithm had been originally trained on high-quality lab images. The inability of the system to handle images produced from the clinic led to major disruptions both during and after the screening process, affecting both patients and nurses. Additional factors such as internet connectivity, equipment capability, and the availability of medical professionals also impacted the success of this AI system. One thing that I also find very important about this study was that they talked a lot about the impact on patients. And I think that this is somewhat understudied in, I would say, like the deployment of AI systems for healthcare, just because one, there are a lot of different outcomes that can occur, especially when patients receive, I would say, like false positive diagnoses. And this, the mental aspect of this is not really studied enough. And also, I would say, like the socioeconomic impact of this. And in this region is actually very important because a lot of times patients, they take, a day off of work to travel and to wait for medical care. And so having to experience the mental stress of a diagnosis along with the financial stress of having to book follow-up appointments to deal with this kind of diagnosis is very important in these contexts. So despite the negative results that we see from the study, the benefit of the study lies in its contribution as a first known study to use human-centered methodologies to evaluate a deep learning system that was applied in a critical context such as healthcare. And it's also one of the first to evaluate machine learning performance in the Global South, also in a clinical context as well. As similar research evolves within this field, we hope that these techniques will encourage critical reflection during the AI development process that takes into account the implications and underlying harms their systems can cause on vulnerable populations. More so, this study also highlights that in addition to the accuracy of machine learning models, the ability to improve patient care, is a significant factor to determining the success of a deep learning model. I find this statement by the authors that's shown on the screen not only useful for the broader AI for healthcare research field or a community, but especially for AI tools that are being developed both for and in the Global South. End users and their respective environments are really not studied enough in the deployment of deep learning systems. And as these deployments into the real world increase, more effort should be taken upon both human-computer interaction and AI and machine learning researchers to do so. Additionally, the importance of incorporating methods from and/or including humanities scholars such as sociologists and anthropologists cannot be understated and should be definitely encouraged and embraced by technologists. AI's potential to positively impact healthcare throughout the Global South has increased and is now being leveraged in a multitude of ways. Despite this potential, deployments of AI-enabled tools within these contexts have not always gone smoothly, as we saw in the previous example for the diabetic retinopathy tool. The seminal work by researchers from Google demonstrates how transitioning AI systems out of well-funded and high-resource labs can cause conflicts and contrasting settings in the Global South. The power in this work lies in a large entity, such as Google, being able to openly admit their failures in such a manner. As more work in this area emerges, I expect to see similar situations occur more regularly, which is both good and bad, because people may continue to be harmed by these systems, but future researchers will hopefully learn from this and build equitable systems to avoid these pitfalls. As someone who both develops and analyzes machine learning systems for social good, it's extremely important for AI practitioners working for the Global South to understand and work proactively towards ameliorating issues in fairness, accountability, transparency, and ethics in AI. We also see that much more research is needed to anticipate the risk and promote participatory methods in AI, especially in low-resource settings where values such as inclusion, privacy, and others may not align with Western standards. Recent work done by Samba Sivan et al. Show that typical Western takes on algorithmic fairness are not portable in the Indian context. I believe that this research would also hold true throughout many other regions in the Global South. In regions where ethnic or tribal or religious identities hold more power in society compared to the Western notions of race, which do not apply in countries that are, I would say, racially homogenous, like Nigeria or even Pakistan, these demographics should be seriously considered in the development, deployment, and use of AI systems. When doing research on AI developments in the Global South, such as the case I mentioned previously, I became heavily interested in understanding how to make AI usable and equitable in the Global South. I believe that AI researchers and the AI research community as a whole hold a significant role in shaping research agendas aligned with current initiatives of AI for social good. And they should do much more to mitigate potential harms associated with these initiatives. In this section, I'll be discussing some work from a paper I wrote called AI in the Real World, which was presented at the Navigating the Broader Impacts of AI Research workshop in Europe last year. So I found that a potential first step to mitigating some of the issues around usability, fairness, and equity for AI tools in the Global South is that you should think about building, developing, and deploying AI tools with attention. You should think about why, who, and how. Why am I developing this tool and who am I developing it for? And how will this tool be used for and by this population? Integrating theoretical principles of decolonial AI, such as that was pioneered by Mohammed, Isaac, and Ping, into every stage of the AI tool building and evaluation process would also be very valuable. AI tools are often viewed as all-encompassing solutions for problems in the Global South without considering their underlying implications and impact. And this only stands to harm communities while depriving them of any agency over the solutions that are thrown upon them. With the introduction of AI tools into communities, the voices of these members should be at the forefront, encouraging their inclusion in the design, development, and deployment of AI tools, aligning with participatory design methods, and providing resources for communities to be self-reliant and maintaining AI tools will shift them from being subjects of these systems to being active and engaged users. And finally, I believe that centering non-Western values and perspectives will help create computational tools that are effective in a wide variety of contexts and settings. It's the most basic responsibility for AI to work for all people, irrespective of their ethnic background, socioeconomic standing, and where they live. As highlighted in a previous case study, we see that moving AI out of the lab is not always a simple process. However, we believe that undergoing critical and self-reflexive evaluations in the development and deployment process can aid in improving AI systems as a whole. So I'm going on to some other questions that was brought up in this work. We wanted to challenge the role of responsibility and accountability in AI research and what this looks like in non-Western contexts. So I believe that we can improve the collective and individual responsibility of AI through 4 factors. And this leans heavily on the framework that I presented just a few slides ago. So I've highlighted the shortcomings that can occur in the development and deployment of AI systems, despite being situated relatively close to the target user population. Risk identification is not something that can be done retroactively and has to be ingrained within a development team from the start of a project. In software development, both UI and UX researchers were usually brought in near the end of projects, which resulted in poor user experiences. As the field began to embrace and prioritize human-computer interaction work, we've seen a dramatic shift in these practices and improvements in human interfaces. And I hope a similar shift will also be seen in AI. When outlining the dimensions of concern that we should consider, like what are the ethical concerns associated with this technology, what are the cultural factors that should be considered in AI development, and that could hamper its development, and also how feasible is AI in this context, and how explainable is the AI system both to practitioners and users. Outlining some of these concerns in this manner can also improve how responsive AI practitioners are to the needs of affected populations. Being aware of known harms starts by being well-versed in prior literature. More work should and can be done to encourage research that identifies these harms and to establish, maybe even establish venues where this kind of work can be openly discussed, broadening the field as a whole. So, as developers continue to build AI technologies with intent to integrate them into the real world, it is important that they prioritize the perspectives and values of users, especially those situated within low-resource environments throughout the Global South. The burgeoning bodies of literature and venues dedicated to analyzing the implications of AI research in various contexts has ignited these conversations, and actions taken by conferences to include broader impact statements are a good start in encouraging critical reflection in the research lifecycle. But there is still a need for a field-wide paradigm shift among both the designers and developers of AI systems. So we've come to the end of my presentation. I am looking forward to any questions, and feel free to reach out to me by email, or I'm also very active on Twitter as well. So I look forward to answering any questions. All right. Thanks. So I do see some, so the first question I see is that, okay, can you expand on the finding Western context of algorithmic fairness do not match the needs of Global South? Yeah, so this work was done by Nithya Sambasivan. She's also at Google. And so essentially the paper is called, they have 2 papers. One was a workshop paper, the other one was also published in CHI this year. So I'll see if I can find her name. But essentially it's called basically it's the algorithmic fairness paper essentially. So they interviewed AI practitioners, and then also I would say non-traditional AI specialists in the Global South to just essentially understand, what does algorithmic fairness look like in India. And so essentially this work, also brought up some of the things I mentioned, and also this work inspired what I talked about, essentially how things like gender identity, and also more so even queer identities, and also ethnic and caste identities were very important, more important, and not really stressed in AI development in the global North, because obviously they're not really I would say not really prioritized. And so I think it's a good paper. I'll try to link it after I talk, but yeah, hopefully that answered pretty much of that. And so for the next question, do you see a dichotomy where many components of
Yeah, I can read the question. Is that the strategy seems, sorry, the strategy seems to drop the connection so that the speakers in YouTube, the listeners in YouTube maybe can also understand the question, and you can after follow up if that is okay for you.
Oh, okay, yeah, that's totally fine. Yeah, sorry.
Yeah.
So, yeah, the question is, do you see a dichotomy where many components of AI development are outsourced to individuals residing in the global South, but the requirements and needs being addressed are defined in the global North? Most definitely. And so I actually addressed some of this in a paper that I wrote with some collaborators earlier this year called The Limits of Global Inclusion in AI Development, or just in AI. And so we talked a lot about, I guess, like the low-level task of AI, like, data collection, well, not so data collection, data labeling and like management. And so we do see a lot of Western companies setting up, I would say, offices or I don't know, facilities in the global South, such as regions like East Africa and Southeast Asia, and also Amazon Mechanical Turk, as a big place where a lot of researchers actually get cheap labor to annotate their data sets. And so we do see that, there is a wide discrepancy between people in these regions impacting like AI at the low level, but not actually being involved in the decisions that it is made in or made for. And so I think that's something that's very important. And also, didn't get to mention this in my talk, but we are starting to see a shift in this, where there are like research communities, especially within like the sub-Saharan African context. I can name a few, like deep learning in Daba, Sakene NLP, Ghana NLP, data science in Nigeria, and like AI Saturdays Lagos, that are actually actively working to train researchers in different like AI fields, where they can, publish at conferences and also make an impact on like AI technologies both for and by them. Yeah. And so hope that answers your question. And so another question I see is that there are always risks associated with the emerging technologies. What do you think are the key distinctions of risk posed by AI models in comparison to other technologies? Let's see. So I think mainly like the key distinction of the risks are probably it just like not working at all, and maybe even like exacerbating existing inequalities and inequities. Excuse me. And so I actually see this, we already see this a lot, where facial recognition systems are, they work much worse on, dark skin people with darker skin tones. And then also like, hiring algorithms are biased against women and also racial minorities. And again, sentencing algorithms in the criminal justice system are also biased against racial minorities. And so I see that with, a lot of the regions in the global South being more homogenous in terms of like things like skin tone or race, again, which isn't really a thing in some countries. I think that if these, technologies are transported without, working to actively mitigate and improve the biases, and we'll see much worse results, especially in cases where a lot of countries or African governments are actually importing, like different kind of like surveillance systems for their population. And again, if you're like working in a region like Kenya and you import, AI system, there's so many in the US that isn't trained on I would say like a fair, like unbiased data set. Again, unbiased is, I put it in quotes. So you'll obviously like see very bad results in that case. So I just see like the risk of it is like not working and then exacerbating existing inequities in society as well. So, yeah.
Thank you. Thank you so much, Hinasa. I think this is Nuria Oliver. I'm one of the organizers, and I think this covers all the questions for you. So you did it all yourself, including asking yourself the questions. Sorry about that. We had a connection problem. So thank you for taking over, and thank you for a really nice talk.
Thank you.
Thank you. So we're going to move to our next speaker. who is an old friend of mine, Fernanda Viegas. She's a principal scientist at Google, where she's been co-leading the PAIR People and AI initiative. And she will be the incoming Gordon McKay Professor of Computer Science at Harvard and the alumni professor at the Radcliffe Institute for Advanced Study in 2022. And she will be affiliated over there also with Harvard Business School. Fernanda has done a lot of work with a long-time collaborator, Martin Wartenberg, on how to improve human-AI interaction with the vision of democratizing AI-based technology. She's very well known for her contributions to social and collaborative visualizations, and the systems that she has built with her teams have been used and are being used by millions of people. In fact, also some of her visualization work together with Wattenberg has been exhibited worldwide and is part of the permanent collection at the Museum of Modern Art in New York. Fernanda holds a PhD from the MIT Media Lab, which is where I met her in the late 90s. And today, she's going to be talking to us about empowering end users through AI transparency and interpretability. So please, Fernanda, share your screen when you're ready, and I will play a chime when you have spoken for 22 minutes. So that will be a warning, and if you could start wrapping up your talk, that would be great. So we leave some time for questions, because I'm sure there will be a lot of questions in your talk. Thank you very much, and all yours.
Thank you so much, Nuria. It's great to see you, by the way, and thank you so much for the invitation to participate today. Can you all see my screen?
Yeah.
Yes? Okay, great. All right, so I have lots to talk about today. Empowering end users through AI interpretability. Let's get started. As Nuria said, I co-lead the PAIR initiative at Google, which stands for People Plus AI Research. And the idea is to bring human-computer interaction, so HCI, together with ML development, as you will see in some of the projects I'm going to talk about today. This is our team. It's a wonderful team, and so you're going to see their work today. And let's jump right in. One of the things that we keep seeing is all the hype around AI, right? So you have superhuman this, superhuman that. I'm just showing a few headlines here, superhuman doctors and so forth. And this all sets the expectations that these things are kind of perfect and that they work really, really well. And even though the accuracy of certain systems can be very, very high, they're definitely not perfect. And it's important for us to understand, how do we bring these technologies out of laboratories, and how do we make them work in everyday spaces for end users? And this is what I want to talk about today. And so, for instance, even though we keep seeing superhuman, achievements in healthcare for AI, you have situations like these where you're only really going to see this technology working in real life with doctors if doctors can understand them. So this is, an article that came out of Wired, talking about this sepsis watch system that was being used at Duke University. And one of the problems you have when these very accurate systems make their way into hospitals is a lot of times doctors will not trust them, no matter how accurate they are. So you can see a quote here: when nurses relayed these warnings about sepsis to doctors, they sometimes encountered indifference or even suspicion. Why is the system telling me this patient is about to enter a sepsis situation? So what do we do, right? How do we start addressing some of these problems? One of the things I truly believe in is that we should be proactively surfacing more information about these systems to end users. So I am talking about AI transparency. I am talking about AI explainability. But the important thing here is, how do we do that? And so we should be thinking about choosing information that matters for the end user. Okay, so not the person who built the system, but the person who's going to use the system. And how do we present this information in ways that make sense to this end user? And in pair, the way we think about interpretability and explainability methods is that there's a range of methodologies that work, and they are different. And so, you have methodologies that work for the ML experts. You have explainability that hopefully works for the domain experts, the middle column here, physicians, bankers, journalists, people who are going to be using these systems professionally, but are not ML experts themselves, okay? And then finally, all the way on the right, you have the lay users. These are people who may or may not know about ML, they may or may not care about ML, but they are on the receiving end of this technology, and therefore we should do our best to inform them about the limitations of these systems. And so for the next few minutes, I want to focus on this middle column here, and I'm going to be talking about some of the work we have done with physicians. And so one of the things that, we can all sort of, those of us who work in the ML area, know that there are by now lots of interpretability methods, and that is true, but often these interpretability methods are accessible only to ML experts, okay? They tend to be very low level, they tend to be abstract, and so I'm giving you a couple of examples here. These are great interpretability methods, but they are not necessarily the kinds of interpretability an end user might find useful, okay? They tend to be very math and beautiful, but kind of abstract. So I wanna very quickly call attention to one flavor of interpretability methodology that can be aimed at end users. So my example here is TCAV, which stands for Testing with Concept Activation Vectors. I don't have time to go into the technical implementation details of this, but I'll just say that this is a methodology where even after a machine learning system is trained, you can ask a user to express concepts they are interested in. So imagine you have a image recognition system, and this image recognition is going to look at this image and say it's a zebra. And what your user wants to know is like, okay, it's a zebra, but why did you think it's a zebra? Is it because maybe you care about stripes? So the notion of stripes, the concept of stripes, which again is a high level concept, right? Something that the user has a mental model of. I look at that zebra, I see stripes. Okay, it's the kind of methodology where the user can give the system a number of examples of stripes, of photos with stripes. And these don't have to have anything to do with zebras. They can be striped fabric patterns. They can be stripes on a crosswalk, you name it. But if you can give a set of examples, and the system then, the CAVs, will train a linear classifier that will find the direction of stripes inside this model. And so that becomes a concept activation vector. And then you can test the image recognition system to understand how important, how aligned with this CAV, this concept activation vector, was your forecast that this is a zebra. If it's very aligned, then this notion of stripes turns out to be very important to your classification of this image as a zebra. The important thing here is that this finds a way of letting end users express high-level concepts that matter to them to the ML system, okay? So we have translated from easy to define human-friendly concepts into neural network geometry. If you're interested in exactly how this works, please take a look at the paper that we're citing there. Okay, but now the reason why I talked about TCAV is because we're going to use that interpretability method as an end user tool, okay? Again, thinking about doctors. So when you have pathologists that are trying to diagnose cancer, for instance, they look at very large, very detailed images, like the big image you see in the middle here, a tissue from a biopsy, okay? And then they analyze that image very closely to try to remember what other patients have I seen that look like this? And what other cases have I seen that kind of match the case I'm looking at right now? And that's how they're going to try to diagnose the patient. And what you see here, Gleason 2, Gleason 3, these are the different grades of cancer that the doctors are going to be trying to discern. So they're going to decide, one, is there cancer? And two, if there is cancer, what grade of cancer are we talking about here? Okay. Now, this is very hard work. It's not easy to do. And one of the things that doctors really care about when they look at these images is a number of different medical concepts that they keep in mind as they're analyzing these images. So level of stroma, normal percentage of normal glands, percentage of tubular glands, fused glands, and so forth. Okay, and the doctor is looking at these and thinking, oh, I wish I could get images like this patient, but with more fused glands. So the question becomes, when you think about a machine learning system, you know, the system might look at this image and try to find, it's going to very quickly try to find the nearest neighbors it can find to that system. And it's doing all of this on a pixel by pixel basis, right? That's the way it understands the world in terms of image classification. The missing piece here is, okay, but how do I then ask the system to give me those images that have these medical concepts the doctor cares deeply about? How do I direct the system to give me, you know, images with more tubular glands or so forth? That's where we're going to go back to our interpretability method, CAVs, TCAVs. Okay, let's say we are interested in fused glands. So what we did, we asked the doctors to give us examples of patients with images of fused glands. And therefore, by feeding that to our system, we were able to find, again, the concept activation vector, okay, and in the machine concept CAV. Once we had that direction in the highly massive multidimensional space of the ML system, we capture that and we turned that into an actionable user interface. We turned that into a slider for the user, for the doctor, who could say, oh, I want more tubular glands, or I want more fused glands. That becomes a UI component, okay, that they can interact with. So in the end, we created this prototype called Smiley, where the doctor could not only see the image of the patient they're trying to diagnose, they can also look at specific regions, and our machine learning system will be bringing up the nearest neighbors to that picture. But if you look at the very right-hand side there, we're also letting the doctor decide to adjust the results by medical concepts, okay? And this is, again, where we get like percentage of stroma, percentage of normal glands. And so it allows the doctor to create a dialogue with the system. Okay. When we ran a user study with the pathologists, 12 pathologists, we showed that we had a control group that only saw a regular machine learning system with a score. Oh, I think this person is, 85% chance of Gleason 3 cancer, versus our Smiley tool that I'm showing here. Okay, the tool where you had to actually work with the tool to come up with a diagnosis. And we saw very promising results. So for instance, the level of trust, doctors felt like they could better calibrate the level of trust in the system. Part of it in qualitative interviews was the fact that they felt they could understand the system better. They kept playing with the system, not only to diagnose the patient, but to better understand how the system was behaving. And then finally, the question about, would you want to use a system like this in practice? Again, the system that had this dialogue was much more positively scored than the regular just a score machine learning system. Okay, the other thing I want to talk about is even before you start using a system like this for medical diagnosis, what might we want to onboard you with as a doctor? What informations might you want to have, okay? And again, here we're going to try to translate model explanations into usable, user actionable strategies, okay? So we did this work with 20 pathologists in prostate cancer diagnosis. And the idea was to aim these explanations, again, at the doctors, not at the developers, explain how the doctors should make decisions using the models. How might the model be helpful to them? And then communicate these, instead of as model metrics, instead of speaking the model language, we wanted to speak a user actionable language. Oh, and by the way, this work right now is being presented this week at CHI, at the conference CHI. So this is hot off the presses. So the doctors wanted to learn, even before using the system, they wanted to learn more about the system. And they wanted to learn about, like, what is the data the system was trained on? What are the strengths and limitations, strengths and weaknesses of the system? What are any AI artifacts or weirdness that I may encounter? And do you have any tips about how it may be useful for me to work with the system? And so I will walk very briefly us through some of these questions here. So let me give you some examples of these boxes I just showed, okay? So users, what they needed to know during onboarding, right? What the doctors wanted to know. They wanted an actionable strategy for knowing when to rely on the AI versus when to rely more on themselves, okay? So the team worked together to discover that the typical performance metrics they were capturing, the engineering team was capturing, were not actionable for users, you know? So for instance, saying, oh, I am 90% accurate on grade 3 cases, that was not super helpful to the doctors. The doctors really wanted to hear things like, if I think this case is grade 4 and the AI thinks it's grade 3, how likely is it that the AI is correct? Okay, and so the engineering team had to go back to the drawing board and start differentiating these cases and start giving more actionable tips for the doctors, okay? Again, trying to understand, what is the system really, really good at? What are the strengths? When should the doctor pay attention to the system? Another example here, the users really cared, the doctors really cared about edge cases. So these turned out to be cases that are very hard for the doctors to grade. And they have the names there. I'm not a doctor, but you know, atrophy or necrosis or blurry images. These are things where the doctors are especially, it's tricky for them to figure out what to do. It turns out in the original version of the system, the data had not been labeled with these edge cases in mind. It was just Gleason 3, Gleason 4, Gleason 2, okay? So what they had to do, the engineering team went back and relabeled the data to understand these subtype, to add subtype data to the labeling, okay? And this turned out to do two things. It improved the model in addition to improving the communication with the doctors, okay, the onboarding experience for the doctors. So it was great. It was a twofer, if you will. So the summary is that by working with the doctors and trying to understand what are the questions that these doctors have even before they start interacting with this machine learning system, you know, what happened was that this resulted in enhanced onboarding materials for the doctors themselves. But it also meant that the engineering team themselves developed a deeper understanding of specific and unique strengths of the tool they were building. So in the end, they learned more about the models than they knew before. And then finally, you know, communicating these error modes. Oh, let's say the system is really good at Gleason 3 cases. But, the edge between Gleason 1 and Gleason 2, for instance, if that's the case, the system is less sure of. Communicating these error modes to end users helped set the right expectations about model performance and potentially avoid frustration and the erosion of trust, which turns out to be one of the main problems when you have when you try to bring AI technology to high-stake situations like healthcare. Finally, if I have a few more minutes, just want to finish with one example of explainability for lay users. How might we want to explain what's happening with some of these systems so that we inform our lay users? And this is a lot of the materials I'm going to talk about are in this PAIR guidebook, which is available publicly. And it's a guide, it's a set of guidelines we use internally at Google, and we made public as well. And I'm going to talk about the chapter on explainability. So imagine you have a running app, okay? And you are talking about someone had your runner had an accident, is injured, and so you want a recovery route. Instead of explaining your recovery route as, we have adjusted your normal route to aid your recovery, which doesn't say much. How about you aim for something like this, where you say, oh, your recovery route details have minimal elevation, even surface, and we're setting a slow pace for you. So basically, how can we surface to the end user? What are the aspects of the data that we're relying on so that you have a better recovery experience? Okay, so again, you're trying to surface information to the end user in a way that they hopefully will understand. Another example, imagine you want to go running during the evening, okay? And your app says, night moves, be careful on your evening run. Okay, not very helpful. So how can we be more helpful? How can we talk about limitations to the end user? So we say, night moves, be careful. It's after 6 p.m. and your run route recommendations don't include street light data. So here we're surfacing data limitations to the user. We're saying, this may be fine, but by the way, we don't have light data for your route. So up to you, you decide whether or not you want to run at this time, okay? And again, this was just a very small example of some of the thinking and some of the guidelines that we try to follow at Google, where we start thinking, how can we surface some of the limitations or some of the behaviors of the machine learning system to the end user to inform them so that they are empowered to make the best decision they can make. And I'll stop there and take any questions.
Wonderful. Thank you so much, Fernanda, because I just played the chimes you still had a few minutes left, but you just did it right on time. So that's absolutely wonderful. I see there is a couple questions, so I'll just take the questions first from the chat.
Okay.
One of the questions is, do you think the way forward to evaluate these human plus AI, sort of like pairs, is doing surveys with experts, or you think they might be a more sort of like mathematical models of human behavior that could be applied? I guess the question is more like whether you need to have this more probably non-scalable process where you actually have to, get user studies and ask experts, or there might be a model that somehow could model that, and I guess then you can scale further. What are your thoughts about that?
Yeah, no, I think that's a good question. I think hopefully there will be work where we can get more quantitative data and scale the methodology. I think at this moment, though, there are enough unknowns that I think it's quite valuable to work closely with experts or with end users, right? In this case, I'm talking about healthcare. So obviously we're talking about interacting with doctors very closely. But you can imagine, you know, for consumer products, there might be a number of methodologies you might want to use: A/B testing, interviewing, surveys. You know, there might be a number of things you could do. I do think, though, that for high stakes situations like healthcare, it's really a good idea to start to understand what are the workflows that people already have, so that when we bring this kind of technology, it's actually helpful instead of unhelpful. Like, there are all sorts of processes that people follow and all sorts of questions that these professionals and experts are dealing with that are quite complex. And so I think it behooves us as people who are trying to develop the technology in a responsible way to work with these experts to try to better understand where in those workflows would it make sense to surface different kinds of information, and to, again, how then do you put these users in control of what the machine learning system is doing instead of the other way around. So I think hopefully we will get to more scalable methodologies, but I think right now we don't know enough. So I think we need a little bit more of, you know, the deeper, more qualitative understanding in addition to the quantitative.
Yeah, thank you. There are two more questions. Let's see if we have time for them. So one of the questions is related to using embedding spaces for interpretability methods, as you presented in the first part of your presentation. So I guess the question is, where do you think the limitations are of such methods, and what kinds of advances do you think there should be to really tackle such limitations?
Yeah, so I think one of the things I was really excited about with the kind of work like TCAV that I showed was this ability for end users to very quickly and very simply, in a sense, just find a set of examples that they can feed the system to sort of say, this is the concept, or these are the concepts I care about. I also think that there's a space for us to create kind of a crowdsourcing of concepts, right? Imagine you have, there are certain concepts that doctors care deeply about, but, you know, what about architects? What about musicians? What about, you know, you can have a glossary of concepts that people care about. I think one of the challenges there is these are all concepts that we care about as humans and that we understand. Obviously, there are concepts that are machine concepts that may or may not be understandable for us, right? That the system still cares deeply about. And so I think this is one of the challenges that would be interesting to look into. Of all the concepts that this machine learning system cares deeply about to come up with its, you know, prediction, which ones are human understandable or human relatable? Which ones are not at all? And should we learn more about those, or should we try to understand those, or do we not trust those? And I feel like there's more to be understood there that we care about. But having said that, I will also say, even with that challenge, I still think that it's important for us to be able to express these human concepts, because again, we want to have ways to have hooks into which we can say, oh, machine learning system, when you predicted that this is a doctor, did you do that because of the gender of this person or the perceived gender of this person? Because if you did, that's bad. I don't want you to care deeply about that. So like having ways of dialoguing with these systems, I think it's always powerful. But that does not take us away from the fact that sometimes these machines will have concepts that only they understand.
Yeah, I mean, and you raise a good point, which is maybe by looking at gender is much more accurate than by looking at other characteristics, because it happens to be that, I mean, maybe not doctor, but maybe computer scientist is a better example, or maybe doctors is a female, there's more female doctors than male doctors, right? So I think this brings me to the next and last question, which is, there's a difference between sort of like explaining how a model makes a decision and understanding how it makes a decision versus how good it is, which I think is, this doctor example is an example of, Gonzalo Ramos, who I think you might know, is asking, what do you think are promising ways to disentangle these two dimensions using UX, how the model is making the decision versus maybe what is helping the model be good at making the decision?
That is a good question. I don't have a crisp answer to that. I think for some of this, it will be very contextual in the kinds of applications that you're using the technology for. At the end of the day, some of the more complex situations in which these models are used are situations where you don't have black and white decisions, in a sense. There's going to be a lot of value driven and lots of shades of gray. And so what is a good decision there? I feel like there you're going to have to find ways of translating human values into math. And I don't know that we're very good at doing that right now. I think this, like you can talk about machine learning fairness, you can talk about different kinds of challenges where we're going to have to start bringing human values into math. And I think UX can help a lot there, because I think UX gives you a way of surfacing some of the biases, some of the different kinds of thinking, and even some of the trade-offs that you're going to have to make in order to decide what your system is going to do. So I think UX plays a huge part in, if nothing else, not necessarily making your system better, but making it hopefully easier and more concrete for the end user to grasp the set of trade-offs that they are going to have to make.
Awesome. Well, thank you very, very much, Fernanda. So I'll just clap for you.
Thank you.
These, webinars are really hard to get the feedback from the audience, but people are saying that thank you for a great presentation, and I concur with that. So, and it was a great excuse to see each other again.
Very good to see you.
Thank you very much for a really nice talk. Thank you.
Thank you.
Ciao. Ciao.
Ciao.
Appreciate it, Fernanda. Thank you for the awesome talk. With that, we'll move on to our next talk from Adish Singla. Adish is a tenure-track faculty member at the Max Planck Institute for Software Systems, where he leads the machine teaching research group. His research interests are in the algorithmic foundations of machine teaching and applying these algorithms in the application domains of computational education and trustworthy AI. He received his PhD from ETH Zurich in 2017. Before starting his PhD, he worked as a senior development lead in Bing Search for 3 years. His work has been supported by the Facebook Graduate Research Fellowship, Microsoft Research PhD Scholarship, and the Microsoft Tech Transfer Award. And without further ado, Adish, you can take it away.
Thanks a lot for the introduction. Can you hear me well? Yep. All right. Yeah. So thanks, and I'm really excited to have this opportunity of presenting our research work at this workshop. So in this talk, I will provide an overview of our research on machine-assisted teaching, and more specifically, I'll focus on our recent work in open-ended problem-solving domains. All right. So while clearly digital technology and AI can have huge societal impact by making education more personalized, cost-effective, and inclusive, right? Now, there are many different facets of education. And in the past decade, the focus has been, and the success has been in developing technology for large-scale delivery of educational content via MOOCs, right? We have also seen many success stories of AI-driven tutoring systems for personalized teaching. These success stories have been primarily limited to simpler domains, for instance, involving memorization of content or mastering a well-defined procedure, for instance, to solve algebra problems. So focus of our current research is on developing educational technology for open-ended conceptual tasks, right, such as programming or working on a mathematical theorem or solving hard puzzles. And these tasks are crucial to foster more general problem-solving skills among students, which is basically very important for their success in STEM and computing fields. Now, developing this technology is challenging and requires advances in several different fields, including AI, human-centered ML, as well as in cognitive science. So what makes this challenging is that when solving such conceptual tasks, there is really no well-defined procedure that student could follow to solve a task, right? And they would basically have to devise search strategies for exploring the complex solution space. And these tasks could also have multiple different pathways to reach a solution, or even multiple solutions, right? And there is also no clear taxonomy of skills that a student could master to basically gain expertise in this domain. Now, these issues basically in turn make it challenging for us to design algorithms that could infer the student knowledge effectively or their misconceptions, which is very important for us to do some kind of interventions, right? So as a very concrete example, so let us look at this block-based visual programming environment, which is used for introducing computing concepts to novice learners, right? While general programming tasks can be a lot more complex, I'm using this very simple task here from Hour of Code Maze Challenge by code.org to convey some of the key ideas in this talk. So in this task, student has to basically put together code blocks in this workspace to move this Angry Bird agent from its starting location to its target catch pick, right? Now, this workspace basically requires that students should only use 5 blocks to get the full marks. They can use more blocks, but they wouldn't get the full marks in that case. And if student has a full understanding of how to basically nest moves and turns inside a repeat block, the solution is quite simple. And in this case, it basically involves move forward, turn right 3 times, right? Now, even though this is a very simple task, the need and popularity of these kind of block-based visual programming platforms is huge. So in last 7 years, over 50 million unique students worldwide have collectively spent over 1 billion coding hours on code.org. And this has been made hugely popular because of initiatives like Hour of Code. Now, beyond this maze challenges, block-based programming is also very interesting kind of domain to study because it provides a digital abstraction to many more complex learning tasks, right? In fact, advanced block-based languages are also used for introducing kind of programming constructs in introductory programming courses in universities, and I'll bring that up later in the talk as well. So let us look at a journey of a student who is solving this task number 9 on maze challenge, right? So here for illustration, I'm considering a student who is basically struggling to solve this task, and they're trying to put together multiple repeat blocks to construct the solution, right? The student seems to have a lack of understanding. They can actually put multiple moves and turns within one repeat block. Instead, they're basically somehow seems to be putting only one action block inside a repeat. So what we would like to do here is to develop machine-assisted techniques to help this student, right? By providing some kind of hints of what to do next when they get stuck. Now, computationally, this is a challenging question because even for this very simple task, the number of potential programs or partial solutions could be unbounded. And more importantly, before we can provide effective hints, we do need to understand the student's search strategy, right? What exactly are they going to go do in near future so that we can provide hints which are kind of aligned with their search strategy while still we can nudge them towards a solution. So in this case, in this huge search tree, the student has this current node, which is shown in red, right? And they basically have, we want to nudge them to go to the correct solution code, which is green, right? And of course, we want to provide these hints without exposing too much about the solution. We don't just want to reveal the solution itself, right? One way to think about hints in this case is that we could tell them that they should remove one repeat block, right? And one could instantiate these hints by basically AI agent taking one of the actions instead of human student taking this action. Now, more formally, we can think of providing these hints as some kind of a collaborative problem solving between human and AI agent, where human agent is solving most of the task, right, taking most of the actions. However, when student is stuck, AI agent could take over and intervene and provide a hint to get this out of this trap, right? But to provide these optimal hints and interventions, we basically need to know some idea about how a human is going to act in your future. Now let us look at the student's journey across tasks, right? So let's say in previous task number 9, student received a hint and then they constructed the correct solution, and then they would move on to this task number 10. So the problem here is that every student is basically going to follow this linear curriculum of these 20 tasks in this maze challenge, right? Going after one task after another. Now, clearly students would differ in terms of their current knowledge, understanding, and pace of learning. So for instance, if a student was unsuccessful on task number 9 and they received hints, they might not be ready for task number 10, which introduces a new construct of repeat until. They might need to practice more tasks about repeat loops before they can basically go to more challenging tasks. So what we would really like to do is infer the students' current knowledge and have some estimate of learning dynamics and then assign them tasks which is more effective for their experience. Now, this is challenging for open-ended domains because there is really no clear taxonomy of skills that we could say, oh, this is basically what is the current knowledge state of the student. And second point is that even if we know the learner model, designing curriculum is trivial given the complexity of this domain, given the type of tasks that they need to master. So with that as motivation, 2 different motivating scenarios in which how we could assist a student by providing hints within tasks or by designing curriculum across tasks. I want to use this slide to take a step back and formalize this question of what does it mean to teach, or what does it mean to assist a learner in their learning process, right? And how does this idea of machine assisted teaching differs from the formalism that one would have in mind when they're looking at more standard machine learning problems? So at a very high level in machine learning formalism, we are kind of focused on designing algorithms for this learner who will basically have some training data or some experience, and based on that data, they would basically output some kind of a decision-making policy, right? So for instance, in robotics, we would like this algorithm to be able to learn a good decision-making policy that they could apply in future. Now, when we are reasoning about this machine-assisted teaching algorithm, the formalism is somewhat quite different. And here the focus is on designing algorithms for this teacher. As an input, this teacher would get 2 things at a very high level, right? So one is the target policy that we want to teach or convey to the student, right? You could imagine this target policy could be the desired execution behavior that would solve all the tasks in this domain. And we would also need some kind of a learner model, which basically is a proxy or a surrogate model for a human learner. So we can reason about if we do these kind of interventions, how would it affect this learner in turn, right? So we need some way of quantifying the utility of our interventions. Now, given this input, our goal basically here is to design these teaching algorithms that could optimize the data or experience, which will steer this learner to the target policy quickly, right? And the technical challenge or novelty in this formulation is that, we have to design this teaching algorithm which has to solve some kind of inverse problem to this learning. So in a nutshell, when we are looking at problems in this space, there are typically 3 different components one has to reason about, right? So first is, what is a formal representation of the domain? And what is really the interaction protocol in which we could assist the student? And you could think about this protocol being, are we providing hints within the task? Are we designing a curriculum? Or are we providing some kind of a grading feedback? Once we have this protocol, next we need some kind of a surrogate model for a computational model of a learner that basically would allow us to quantify what is going to be the effect of different kind of interventions, right? So this is basically a proxy model, right? Given this model and some desired target policy, then we'll focus on designing these teaching algorithms. And here the question would be, how could we influence the experience of this learner in order to speed up their learning process? And finally, to evaluate the performance of these teaching algorithms, we basically have this last arrow here, which is to evaluate these algorithms by conducting user studies with human learners, right? And it's kind of a closed loop research here, because after conducting studies, we might discover some new phenomena or discover some limitations of our models, and we will have to go back and rethink about the learner model that we begin. So with that, those three components, I want to deep dive a little bit more into these components to give you an overview of the research problems in this machine-assisted teaching landscape. So I'm going to use this slide to provide broader overview, and for the rest of the talk, I'll deep dive into one of the specific problems, right? So in this landscape, one way to think about this landscape is you have x-axis where we are reasoning about what kind of learner model are we looking at, or what is the focus of our setting. On the right side, we have educational applications of the kind we saw earlier, right? And here we would like to have a simple model of a human learner to design our algorithms. So these models could be data driven. So if you have access to historic student data, you could use some kind of imitation learning to come up with a proxy model of a human student, right? Or this could be based on some simple cognitive principles, such as zone of proximal development, or some simple intuitive principles that we could use for designing the learner model. On the right side, the focus is more on theoretical foundations of teaching, and here we could consider a bit more machine learner model, for instance, agent-based on reinforcement learning or imitation learning, right? On the y-axis, one could vary the type of intervention and the teaching algorithm. So at the bottom, what you see here is the kind of teaching algorithms where we assist the learner by giving hints or demonstrations. On the top, we have a teacher who assists the student by designing new tasks, designing curriculum, or provide some kind of grade points. So quickly going over each of these quadrants, right? So the bottom right quadrant is what we saw earlier already. So here we would like to design algorithms which could assist a human student by providing hints when they get stuck. Bottom top right quadrant is basically about designing curriculum or synthesizing new tasks when the available pool is limited. And the top left quadrant is what the recent work that we have been looking at is in context of what we call environment design, right? And here, basically, the question is, given a reinforcement learning agent, how could you design better rewards or better transition dynamics, which would speed up the learning process of this agent, right? And one way to think about designing rewards is that it is somewhat implicitly connected to the problem of designing grade points in pedagogy. And bottom left quadrant is we have been looking at questions more about sample complexity of teaching. For instance, how much speed up in convergence we can achieve if we provide better sample data, right? And here there is a notion of complexity known as teaching dimension that we have studied in different contexts. So for the rest of this talk, I'm going to focus on one recent work from NeurIPS 20 conference last year, where we have been looking at problems in the context of curriculum design for block-based visual programming, right? And that brings us back to this slide that we saw earlier. So in this slide, we asked the question, right? So how do we assist this student by providing a better selection of tasks? Instead of following this linear curriculum, can we basically infer their knowledge state and select a better task for them, right? Now, this is a very challenging problem to design curriculum, because for this, we would require a human-centered model for problem solving. We would also require techniques which would allow us to infer the knowledge state of the student, so we can basically decide what to do next. And the curriculum design itself is a challenging problem, because it allows we will have to reason about the long-term learning gains as we provide a curriculum of tasks. In this work that I'm presenting, we consider a very simple problem. So we asked, right, so if a student wasn't able to solve task number 9 here, could we provide them more tasks of the similar type so they can practice that concept? So task number 9, if you remember, was this repeat loop block, right? So if they received hint on task number 9, instead of progressing them to task number 10 in this series, which introduces a new concept, can we have some practice tasks for repeat until, for the repeat loop, so that they can master that repeat loop construct before moving to task number 10, right? even today, this is not feasible, right? Even this simple problem of doing practice is not feasible because of lack of availability of practice tasks, right? So if you look at this hour of code maze challenge series, there are 20 tasks in this series, and each task basically is more or less distinct, right? So each task basically introduces some new concept, and maybe there is one or two tasks which are about of similar concepts. But if student was not able to solve a particular task, they would typically move on to next task in this series, right? And this really limits their ability to practice and master these concepts. So in this work, we basically formalize this problem of synthesizing practice tasks. And the formulation is actually quite simple and intuitive. And the idea is that if you are given a reference task T in along with some reference solution code C in, we want to generate a set of practice tasks T out and C out, along with solution code C out, that are conceptually similar but visually dissimilar. Okay, so let me explain these two ideas through this example. So if you look at this hour of code example that we saw earlier, so here the angry bird is now replaced with this blue marker, and the target catch is replaced with this peak, with this star, right? And the conceptual similarity here basically means that if you look at the structure of C in and C out, they have the same nesting structure. So both of them have if conditional nested inside repeat until conditional. So that's basically what we mean by conceptual similarity. And by visual dissimilarity, we mean that the grids T in, T out are actually visually distinct. And the idea here is that we want students to stay fresh and engaged so that we, by bringing in these new distinct tasks, right? So that's basically what we want to generate, right? So before introducing our approach, I want to highlight some of the key challenges in synthesizing tasks in this domain. So for other domains such as algebra problems, one way to synthesize these tasks is through some kind of a mutation-based approach. And the idea is that you are given T in, you could mutate that T in to get T out, right? And then you could use that mutated task as basically a proxy for T in. So it's a very simple idea, right? Mutation-based approach typically works for many domains. However, this actually is highly ineffective for block-based visual programming because of the following reason. So if you slightly mutate your input task, the solution code could change drastically. So the mapping from tasks to solution codes is highly discontinuous. So let me illustrate this idea with this example. So this is a T in from previous slide where the C in solution code has these 5 blocks. With if nested inside repeat until, right? So I'm just showing the structure of that. And I've created 3 different T outs here with small mutation of T in, right? So these tasks look very kind of close to T in. So that's what a template-based approach would do. However, if you look at the solution codes for these 3 different tasks, they vary vastly in terms of size and structure. Okay, so for the last task, T out, you actually cannot solve any more using repeat until block, and you will have to put together 28 blocks of moves and turns to solve this task, right? So this is what I mean by discontinuity. Now, furthermore, enumeration-based approaches are not really applicable here because of very large space of task configuration and solution codes, even for very simple problems that we are looking at here, right? So in summary, the grand challenge that we want to resolve here is, how do we basically find some nice, good tasks for a specification, even if we are dealing with way too many potential tasks and configurations, most of which are not desirable for the specification we are looking at. So our approach to solve this problem is somewhat orthogonal to this task mutation approach, which I've shown here with red crosses. Our approach is basically to first map this solution code C in to some kind of a meta level conceptual space. And in our case, this basically is the sketch or the structure of the solution code that we want to preserve. Then as a next step, we create instantiations of this solution sketch to create new solution code C out. So at this point, we don't have a task T out. We're creating new solution code C out. while enforcing some kind of constraints. For instance, what could be the upper limit on the size of CL. Then as a third step, we project this solution code C out to the task space to generate T out using some combination of symbolic methods and reinforcement learning. We basically use Monte Carlo tree search to basically get this task, right? A takeaway message from this slide is that basically, if we have tasks with visual or text specification, they can be too brittle if we directly mutate them in the task space. And instead, we would like to go to conceptual space where we have a bit more flexibility. Right? And this general principle can be more broadly applicable for problem generation in domains such as mathematical word problems or programming with text specification. Right? So just very quickly, I want to show the kind of tasks that we could generate. And here we used 10 reference tasks from 2 different programming platforms. One is the hour of code task that we saw earlier, right? So here we were able to generate, for instance, over 440 tasks with 46 distinct solution codes. Another programming domain that we looked at is this Carol domain, which is somewhat more complex than the domain of hour of code. And here, basically, one has to write code which transforms input grids to output grids, and there's additional marker activity. In fact, Carol environment is actually a Turing complete language, provides Turing complete language for you to write more complex computing concepts such as sorting or finding midpoint. Right? For this reference task, we were able to generate over 5,000 different tasks. So very quickly, we evaluated this technique also through some user study for which we developed this app, which is publicly available. Right? And here the goal was really to measure the performance of the task synthesis in terms of the quality. Right? And this user study was done with novice adult programmers. And there were 2 metrics that we wanted to compare here. Right? First is the how many tasks we can generate, what is really the number. And second is quality, measured in terms of visual dissimilarity, and also measured in terms of if novice programmers were able to solve our tasks, if they already know how to solve the reference task, or if they have seen the solution to the reference task. This study is not designed to capture the long-term learning gains which would require further longitudinal studies, right? So in this evaluation, we compared our task to approach to task mutation and also human-generated tasks. And for human-generated tasks, we actually took the tasks from these platforms which are already available and were similar to what we had. So what we can see here, right, in a quick summary, that we were able to generate hundreds and thousands of tasks for different reference tasks, whereas there were only very few tasks which were provided by tutors in these platforms. And also in terms of quality of fraction of tasks solved and visual dissimilarity, we were quite close to human-generated tasks, whereas task mutation performed quite badly in this. Right, so just basically getting back to this research landscape, that was a very quick summary of the recent work on task synthesis, right? And here we tackle this problem of generating practice tasks, which is kind of a very important ingredient of curriculum design, right? And the complexity of this specific project about just synthesizing similar practice tasks basically highlights that a lot needs to be done if you would actually have to develop end-to-end algorithms of curriculum design in these domains. As a concluding remark, I would just like to mention 2 points, right? One is this landscape that I presented as a distinction between a human model and machine model is not always so distinct. And there's important feedback loop here, basically for us to take insights from education to developing more human-like models for machine learning and the other way around. And the second important point is that a lot of technology that we need for enhancing education in open-ended domains still needs to be developed, right? On one hand, we need computational models of human learning for open-ended problem solving. On the other hand, we need basically new kind of techniques which can reason about these models and provide effective interventions. And for the audience in this workshop, I would like to mention that educational technology for open-ended domains is an ideal playground for researchers and could help actually bring in next scientific breakthroughs within human-centered machine learning. Right? So with that, I would like to thank my collaborators, and I'll be happy to take more questions.
Awesome. Thank you for that, Adish. This is a really, really interesting presentation. If anybody has any questions, feel free to put it in the chat. If not, I actually have one question. Have you guys considered in your last slide, have you got what when you're talking about like these code sketches and this idea of like the quantifying like the difficulty of a problem, how much of it do you give like a sequential treatment to like the child or the student's like learning ability over time? So you identify that they struggled in a particular portion of a particular task, and then can you continue to stress the importance or the difficulty or continue to teach them on a subsequent task? So I guess to word my question better is, do you guys really treat the problem in a very sequential nature, like we learn continuously throughout the course of a year? And how does the learning paradigm shift, and how do you kind of see that fit into this landscape?
Yes. So far, we haven't looked at the problem of actually designing curriculum for open-ended domains like programming. So we have been only looking at very simple problem of basically providing similar practice tasks or providing slightly more difficult tasks than what they practiced before, right? The next big step here is really, if we have some simple model of how human learner is going to evolve over time, right? About some kind of a model about that. Then you could imagine that doing some kind of reinforcement learning, right? So some kind of a meta reinforcement learning over this whole problem domain would allow us to reason about what is effective curriculum policy for this, right? So that would be the right way to go about. But there are some missing pieces here, like what is a simple model that we could use, right? And then still on top of it, designing a curriculum using the reinforcement learning approach. That's kind of another layer of complexity that would sit on top of it. But this is kind of the direction we want to move in.
That's really interesting because you have like these nested loops where you have agents helping you, but also the meta agent kind of guiding your curriculum. Yes. That's really interesting. And I think there's lots of cool questions for our community to ask. So thank you once again for joining us today. And with that, I'll hand it off to Plamen to introduce our next speaker.
Excellent.
Thanks.
Excellent. Thank you. And I'll move to the next presenter. I'll present briefly Chen-Hao Tan. He's assistant professor of computer science at University of Chicago, and he's also affiliated with the Harris School of Public Policy. He obtained his PhD degree in the Department of Computer Science at Cornell University and bachelor's degree at Tsinghua, the leading Chinese university. Prior to that, he was with the University of Colorado Boulder and postdoc at the University of Washington as well. His research interests are in natural language processing, human-centered AI, and computational social science. He holds a lot of awards, including NSF Career, NSF CRI, and number of others, Facebook Fellowship, and his research was also in the media. So without further ado, I'll give the floor to Dr. Chen-Hao Tan.
Thank you very much for the nice introduction. And thanks very much for having me in this workshop. It has a very exciting talks, and I was here for the last hour, and the talks are both very interesting and actually very connected to what I'm going to talk about. So that's very nice too. So in this talk, I'm going to give a kind of short overview of some of our recent work on how we can use explanations to improve human decision-making in what I call discovery tasks, and I will explain that concept soon. And I guess all of us are here because we're excited about the promise of AI to improve our society. AI can help doctors with medical diagnosis and can help with teachers design better curriculums, can help judges sometimes make better bailing decisions, and even can help every one of us identify misinformation and hopefully be more informed on various issues. And in all these cases, I kind of emphasize the word help. And because kind of most of this talk starts from this position that automation is often not desired. And in fact, for instance, in the US, there starts to be laws that are explicitly against using automation in some domains. For instance, this one is about a compass risk assessment should not be used to determine the severity of a sentence or whether an offender is incarcerated. And there's another clause right after this is along the line that judges need to be made aware of the limitations of risk assessment tools. So kind of the important question, I think, for our community is to figure out what it means to make the decision makers or the relevant humans aware of the limitations, and what does it mean to help them understand the tools. And explanations have kind of been the leading hypothesis in the hope that somehow we can use explanations to bridge human and AI, there has been a lot of work in the past years. And in fact, okay, like the notion of expansion also dates back much further. But in the recent move, because of deep learning, I think there have also been a kind of big resurgence of explanations. And hopefully explanations can help humans and AI work together and achieve better decision-making than either of them alone. And the key question we are going to think about here is how can we use explanations of AI predictions to assist human decision-making? And the first part I'm going to talk about is the word AI. And I kind of want to highlight that there are, in fact, two modes of AI that when we typically use the word of AI. For instance, one is emulation and the other is discovery. Let's start with emulation, and like the dog kind of signifies the classic example of let computers be able to see or recognize objects in an image. And in practice, most of the modern AI has two important components. One is the data and one is the model. And usually model can be used regardless of where the data comes from or how we got the data. So the kind of key distinction I'm going to talk about is data. And in data, on the one hand, in the emulation, for instance, here example in the text domain, known as sentiment analysis, and this is a movie review. And even from the first 3 words, most people can quickly tell this is a negative review. And in this case, if we build such a data set and we get the AI to perform the same task, and is essentially trying to get the AI to emulate human intelligence. And that kind of goes back to the very root of AI. And kind of the main hypothesis is that human intelligence can be so precisely described that a machine can be made to simulate it. And indeed, I guess that has been the kind of big inspiration for a lot of AI researchers. On the other hand, in the discovery mode, for instance, here is a task known as deception detection, and we are going to work with this task quite a bit. So I'm going to spend a little time on this one. And this can also be interactive. I'm going to ask you whether you think this review is deceptive or not, and feel free to use chat, or I guess if you think it's deceptive, you can use the yes or thumbs up, whatever icon. I will just try to get some feedback. So this review says, my stay at the Talbot was a wonderful experience. The service at this upscale hotel was beyond my expectations. The Gold Coast location is close to Michigan Avenue, the museums, and many of the other sites Chicago has to offer. If you are visiting Chicago, I highly recommend the Talbot. So the question I'm asking is that whether this author actually stayed at the hotel. Was this review entirely made up? If you think it's made up, maybe put a yes in the chat or raise your hand. Okay, I guess we get 3 deceptive based on my observation. What about if you think it's not deceptive? The person actually stayed at the hotel. And 1 person already put a not deceptive, and we got 2 more. So roughly among the people who participated, I think roughly we get a kind of even distribution between deceptive and not. And in reality, this is deceptive. So I guess in this case, we happen to almost perfectly replicate the human performance in this task. Is about 50%. And indeed, deception is a very difficult task for humans. And we are going to kind of at least help you understand a little bit about this particular data set we are using, which were built for hotels in Chicago. And you can notice that humans are not good at this task. So when we build an AI to perform this task, AI can potentially discover interesting insights that a human doesn't know. And if we kind of go back to how we collected this data in the emulation mode, usually these tasks are what we think humans can do. So we can build labels, for instance, from crowdsourcing. And we just ask people to do this task, and we design AI to simulate how human or emulate how human did this task. And in the discovery tasks, usually the labels actually come from observing social processes. For instance, in the example I was just showing, the label comes from we ask someone who have never been to the hotel to write a review. And then that label was deceptive. And we won't just ask a bunch of mechanical Turkers to guess the label, and that when we know humans are better in this task, so that label cannot really be used as ground truth. And in fact, in a lot of the examples that I showed earlier, for instance, in the justice systems, the typically studied recidivism prediction task, the label comes from observing those people who end up getting bailed and look at the behavior for 2 years and see whether they fail to appear in the court again or whether they commit a crime outside. And we don't just simply ask mechanical Turkers or even judges to label, since judges label is already in that allowing these people to get bailed. And similarly, in the doctor case, doctors may have a prediction of whether treatment will work or not, but the ground truth label of whether treatment will work or not requires us to observe the biological processes or after observing the patient get this treatment. And in all of these cases, there's a lot of AI can discover from this external signal that humans may not have been aware of. And I think that's a kind of key challenge in working on these tasks. And as I kind of was alluding to, a lot of these high-stake decisions are actually discovery tasks. And in fact, like we kind of have experts or professionals to do it because it is a difficult task. And experts are usually far from perfect in these tasks. And this also has implications on how we can think about bridging human AI. And in the first case here, we are highlighting some words. These are kind of essentially attribution style explanations. And we are going to show, kind of discuss them in a little bit more detail later. But on the left one, you can kind of see for sentiment analysis, it's very easy to see why these words are highlighted. They kind of validate our intuition about what makes a negative review. But on the right side, even knowing the label of this is deceptive, it can be very hard to understand why these words are highlighted. For instance, why is Chicago deceptive? And we are going to kind of come back to this again later, try to kind of reason about what's going on here. And this clearly kind of highlights the challenges in how having humans and AI working together in working on in making these critical high-stake decisions, and how can we use AI to support human decision making. So the second part of this presentation will focus on the assisting part. How can we use AI, explanations of AI predictions to assist humans in discovery tasks? And we're first going to kind of think about, explore the full design spectrum on how human and AI can work together. And then we are kind of going to dive into a particular part that's very connected with Adish's talk on machine teaching. And we are kind of doing a very constrained version of machine teaching here. So let's start with human decision-making with a machine in the loop. And on the one end, we can have full human agency where the human makes a decision without any machine assistance. And on the other end, we can have the full automation, which we know is not desired. So what we are thinking about is how we can feel this spectrum and what are possible assistance that a machine can provide and how that roughly affects their agency. But I guess I want to kind of, before I move on, I want to highlight the word agency is hard and is also hard to define, hard to measure. And here we're just matching some very rough intuition of our perception of human agency. So for instance, the most straightforward, and I think this is the most commonly used assistance that we are seeing in practice, is showing people the pretty label. For instance, I can give the same review that I showed you earlier and tell you this machine predicts the below review is deceptive. And you can then decide whether you would like to trust the prediction or not, or whether you would like to follow the prediction or not. And that is kind of in the middle of the spectrum we explored in this particular work. And we kind of think that this, in a way, is actually very strong priming. We tell you what the machine would have done for this particular instance. And what would be less intruding would to leverage the notion of explanations, and we only show you these explanations. For example, we just highlight these words. We don't tell you the machine predicted label and ask you to decide whether this is deceptive or not. And if you can make better decisions based on this, you seem to have better agency in this process, and you are just kind of making decisions by paying a little bit more attention on what the machine think are important words. And these are another form of explanation by showing you similar examples. I'm kind of going to gloss over this one quickly. So that is one ideal mode of explanation. In many ways, I think a lot of my recent work is thinking about how can we make the showing only explanation mode powerful. And I think we're still very far, and I think there's a lot of open questions down the road. But on the other hand, sometimes maybe in some scenarios, we are okay with less agency. We can use ideas from behavioral economics and think about how we can nudge human closer to AI decisions. For instance, we can tell you, in addition to the predicted label, we can tell you the machine has an accuracy of approximately 87%. And if you know that your own performance is about 50%, maybe it makes sense to follow AI decision a little bit more. So that is kind of the very end of the spectrum that we're going to explore here. We just have a kind of middle ground where we show you the label along with the explanations rather than give you the very strong priming or the strong nudging. So that kind of completes the spectrum we are going to look at in this work. I'm going to hold it here a little bit. By the way, feel free to interrupt me if you have any questions. And the amount of information from the machine generally increases as we move from the left to the right. And if you're interested, you can also go to this machineintheloop.com, where we have some demos of our recent work. And we are interested in how kind of human performance changes and in particular how trust changes. And in this short presentation, I'm going to focus on human performance. So our first question is, can explanations alone improve human performance? So again, just to remind you, this is the most desired scenario, at least in my opinion. If we can improve human decision by only showing explanations, humans still have a lot of agency in this process, and they are only slightly change their attention on what is important and what is less important, and they decide how to use that information on their own. And there's no machine predicted labels involved in this mode. And in practice, explanations only slightly improve human performance. The improvement is statistically significant in some conditions. And the best one is just highlighting words. And as kind of glossed over, the examples are actually kind of hard to make sense in this case, since designing similarity in the text space is a little bit more complicated compared to the image case. And the human perception of text similarity is also, I guess, requires more cognitive sense work to understand how human perceive text similarity. And just to remind you the number a little bit, we kind of improved it from just right above chance to about 57%. And control just means human making this decision without any AI assistance. So our next question is, can predicted labels improve human performance more than explanations alone? And the answer is kind of very solid yes. And if we show you the predicted label without accuracy, the performance is improved to about 62%. And what drastically improves human performance is this strong nudging. If we tell you explicitly the machine's performance, people are much more likely to perform better in this decision task. And that goes all the way to about 75%. So far we have seen kind of a very clear trade-off between agency and performance. Higher agency means lower performance, and the lower agency kind of tends to be associated with higher performance. And the final question I'm going to talk about in this part is to think about whether explanations can moderate this trade-off. So we are going to look at kind of the middle part between showing predicted labels and showing predicted labels and this high accuracy. We are going to look at predicted labels along with explanations. Just to kind of situate you in this performance figure, so we are looking at the performance of predicted label without accuracy is about 62%, and predicted label with accuracy is all the way about 75%. So we are thinking about where predicted label and the heat map is going to be. And it turns out that it's almost as good as explicit accuracy, is much better than just predicted label without any information. So it seems that the explanations can somehow moderate the trade-off. But just to remind you, this is still much worse than the AI performance in this particular task. And we are going to kind of return to this point at the end of this presentation. So in this work, what we have seen is that there's a trade-off between human agency and human performance. And this agency is moderated by explanations. So what we have seen here is roughly that this kind of real-time static explanations by just highlighting something or show you some examples, nearest neighbors, they are not sufficient for human to improve their decision making to a desirable level. So the first idea we are going to think about how we can improve this is this notion of model-driven tutorials is very connected to the teaching work that Adish was talking about. Our hope is that by showing people these model-driven tutorials, we can enhance humans' ability to understand the patterns. We are looking at a very constrained form of how the teaching protocol would work. And the second idea that we had was interactive explanations. It happens to be very well aligned with Fernando's work, so I guess is very well situated in this one. I'm not going to talk about this one in this presentation, but if you're interested, I'm happy to talk more offline about what we are thinking about, how we can use interactive explanations to improve human decision making. So in model-driven tutorials, I'm going to answer this question: why is Chicago deceptive? So just to kind of think about the explanations where we just show people like these real-time assistants where we highlight some words and during your decision-making process, or highlight some features more generally, it's kind of like throwing a life buoy to a kid in the water who doesn't know how to swim. And it's unclear they would know how to use this buoy, and it's unclear they can actually swim with the buoy. And it seems useful to be able to give them some coaching beforehand. That was kind of the main motivation for these model-driven tutorials. And that's why it aligns very well with this teaching idea. So these tasks are in the discovery mode, they are challenging for humans to work on their own. And the model may be able to learn some insights in a data-driven way, but this data-driven insights may require more time for people to digest. There's a question. It seems to be a more high-level question, so I'll take that question later after I finish this part. And what we hear is a kind of very constrained form of model-driven tutorials. We are going to identify roughly 10 examples, and for each examples, we are going to ask people to first make a decision, and then we'll reveal machine explanation and AI label, and then maybe use some quiz to help people understand what's going on in this example. And here, I'm just going to pause and explain why is Chicago deceptive. This deceptive review data set was created for hotels in Chicago. So for the genuine reviews, they just get reviews from TripAdvisor. For the deceptive reviews, they hire mechanical Turkers who have never been to the hotel to write some imaginary writing. And it turns out that it's very common that when people do imaginative writing, they are more likely to write more abstract things. They are less likely to write specific things. So in the context of hotels in Chicago, so they are much more likely to mention the city name. While if you just write a genuine review, you are much less likely to mention the city name. And there seems to be kind of genuine hypothesis and even kind of can be validated theory behind this feature that we're highlighting. But this kind of hypothesis formulation and thinking through process might be very hard for people to do on their own. And here we are going to look at whether these model-driven tutorials can affect human performance. And we are going to look at two types of models. One is a linear model. By the way, this is the model we have been using in the previous experiment, and explanations are just the coefficients. And the other one is BERT. And for BERT, we also try two different explanations. One is the attention-based explanations, which would be unsigned. And it seems unfair compared to the SVM explanations we are using here. So we also use BERT-LIME explanations, which are similarly signed. And you can see Chicago would be thought of both. In both cases, Chicago is associated with deception based on both models, both types of explanations. And what I've seen is that this kind of training of model-driven tutorials lead to better human performance. If you look at the dark black bar and versus the red bar, training almost improves performance in all settings. And another very interesting phenomenon is that SVM model actually leads to better performance than either version of BERT. BERT-LIME is slightly better than BERT attention, but it seems that in this case, linear models or simple models may sometimes actually lead to better human performance. we think the reason is related to the fact that the signal in the model-driven tutorials or in the explanations are much more consistent. And in the bird case, sometimes, for instance, in the attention case, the bird may highlight a lot of periods, and that becomes very hard for people to understand. And there's much higher entropy in terms of what words will be highlighted. Unlike SVM explanation, if the word Chicago is present, is always with very high coefficients. And this consistency seems to be very important for humans to understand how these models would work. Okay, 2 minutes, that's good enough. So just quickly summarize what I've been talking about in this talk. And if you I hope that you keep these 3 sentences away. So explanations can moderate the trade-off between human agency and human performance. And model-driven tutorials can help people better understand model behavior. And linear models may sometimes lead to more effective human AI teams than complex models. But at the end, most of, and I think this is also shown in a lot of other work, what we have seen in general in this kind of discovery tasks is that human performance is worse than human plus AI. So human plus AI indeed improves the human performance. But because these are already in discovery, so usually what we see, or the reason we want to get human AI to help is because AI actually outperform humans, just based on very simple measure of accuracy or performance. And in that measure, we do not see human plus AI outperforming AI. And sometimes this may be referred to as complementary performance. There's some recent work, like exceptions of this, but I think by and large, this is supported by a bigger body of work. And I'm going to briefly mention why this is the case. I think one is certainly discovery versus emulation. And by definition, there are some genuine insights that AI finds that are hard for people to understand. And second, I think the key challenge is to figure out how to help people accurately impute these valid mechanisms similar to the Chicago example that I was talking about, while avoiding drawing inferences based on spurious correlations. So what we usually say is that by introducing AI, it will change human behavior and it will make human doing better. But the error pattern is not clean or is not strong enough so that a human plus AI is better than AI alone. And finally, I guess before I conclude or read the question, I want to thank the students involved in these 2 projects and all the sponsors who made this research possible. Should I read the questions? Or?
Okay, thank you. Yeah, we'll make a bridge between these. Your summary was a very good bridge between the question. First, let's thank you. I'll ask everybody to thank you. And the question is actually coming from your summary, is really the aim to improve the human performance or to reach the level of AI, or it can be even actually surpassing? This question from Patrick.
Yeah, I'll just repeat Patrick's question completely. This helps me understand the question better. Do you see any possibilities instead of augmenting human to become as good as AI to use explanations? In a way, human plus AI can achieve stronger results compared to both alone. Yeah, I definitely see the possibility. I just don't think we are there yet. And there was one thing that I didn't mention in this talk that we are recently exploring. Like I think, in general, I think a lot of the setup also use the standard machine learning setup where we use random split to get a training set and random and test set, and then evaluate both human AI performance and AI performance on this test set. And in a way, this is actually the best case scenario for AI since it follows the IID assumption. And in practice, when we complain about AI performance, usually it's because AI fails to adapt out of distribution. So I think figuring out how we can probably evaluate out of distribution human AI plus AI performance is also an important direction in achieving this complementary performance or human.
I think that the question is about integration of the efforts and the complementarity, but there are other interesting questions which also I was thinking about how specific these results are to the scenario and cohort you have chosen and how generic they are. You used statistical measures, p-value, and so on, but this is only on one single experiment.
Yeah, so I think
generic it is.
similar, like I think like this, so there are a couple of directions other people have been working on as well. For instance, like the group at University of Washington, Dan Weld and Gangang Bessel and Tongshuang Wu had a kind of a couple of very interesting projects on this. And I think like, for instance, one hypothesis is that in our experiment, the performance gap is very big. AI is about 87 and human is about 50. So people have tried other dimensions. And in general, I think in many tasks, people have observed similar things, even in recidivism prediction, where AI may be just about 65 and human is about 60, it still is very hard to exceed AI alone. There are a couple of other questions.
Yeah, I think I summarized them.
Oh, okay, cool. Yeah, I think in general, you definitely, like, I think a big question, another kind of open question for the community is to think about how we can generalize experimental studies from this kind of work, because we do not really have a principle or framework to think about different tasks. And what are the important dimensions? For instance, I was using performance gap as one dimension, but there are many other possible dimensions such as domain expertise and the particular kind of task nature, whether it's based on tabular data or versus text data. I think it's very important for us to figure out a way to interpret results from different studies. And I think that would be a very valuable kind of framework.
Yes, precisely in these tutorials that you mentioned that improve the human performance, what type of data were used? If these were the data that were used from the same cohort,
yeah,
it may it may be different from if you use from completely different cohort of people.
Yes, that's a very
Then
good question.
Complementarity.
Yes, totally agree. And I think both of these, all the experiments I'm showing here are based on mechanical Tukers. So they are kind of the same cohort, but that's certainly a strong limitation of this work. And if you think about recidivism prediction, people have also been running experiments with mechanical Turk, but partly because it's very hard to get judges to do the experiments, but that kind of is certainly a very strong validity.
This might be a good idea for the future. You mentioned crowdsourcing and using additional information to the cohort that has been in study will have a potential to actually improve. So maybe actually to surpass the AI. Okay, it's a good thing to consider in the future. I don't see any other questions in the chat, but if somebody wants to voice, there is still time. So there were three questions.
Thanks very much. I think it's time to move on to the next session. Okay. Thanks so much, Chen Hao. That was a wonderful talk, and thank you, Plattman, for chairing it.
Thank you.
Thank you.
Well done. So actually, our next session follows on really well from Chen Hao's themes of issues like explanations and how they can help humans, and also how potentially they might be able to deceive humans and hurt humans. So this next session is very topical. We're really excited to have 5 wonderful panelists who are going to talk to us about the proposed EU regulation on AI, which many of you might have seen was published just recently. We've got a wonderful set of people. What I'm going to do is, well, maybe I'll first tell you their names, but I'll introduce them properly a little bit later. So we have Gabrielle Mazzine, we have Arnav Joshi, Michael Veal, Richard Benjamins, and Amelia Gomez, all real experts. I'm very excited about what we're going to be able to do. The way we're going to run the session is that Gabrielle has kindly agreed to first talk for 10 to 15 minutes, so you can get us all up to speed on what's going on with the proposed rules. And after that, each of the other panelists will have a few minutes to talk to us about any special views they have on what's good or bad about the regulation. And then we have until 6:30 UK time, 7:30 European time. So we have a total of an hour to really get into some interesting issues, to discuss them, and very happy to take questions as usual by people posting in chat. So next up, I'm very pleased to be able to introduce Gabrielle Mazzini. As officer of the European Commission since 2017, Gabrielle focuses on legal and policy questions raised by new technologies. He contributes to shaping and implementing the policy and regulatory initiatives of the European Commission on artificial intelligence. He co-authored the white paper on AI in 2020 and recently designed and co-drafted the proposal for the Artificial Intelligence Act in 2021. He previously served in the European Parliament, the Legal Service, and the Court of Justice. And also he was Associate General Counsel at Millennium Villages, an international development initiative across several sub-Saharan countries. So that connects well with some of our earlier talks. He's qualified to practice law in Italy and New York. So he's really very well suited to tell us about the regulation. Please, Gabriel, take it away.
Thanks a lot, Adrian, and thanks a lot for inviting me for this presentation. It's a pleasure to be here. So I have prepared a few PowerPoint slides, which I'm going to share from my screen. Hopefully this works. Okay. It should be, you can see them here. Show windows. Here you go. So let me know if you can see the slides.
We see your screen, but we're seeing all of the, all the different slides. I don't know if you want to share full screen, so we just see the slide you're on.
Okay.
Perfect.
So now should be a full slide. Perfect. Okay. So let me immediately get started. I try to keep it indeed to 10-15 minutes, but it's a rather complicated topic overall. So if I'm getting too long, just stop me. Okay. So first of all, I'm going to present the regulatory framework, which was adopted by the Commission on the 21st of April. First of all, a couple of key regulatory concepts. So 3 main points. First of all, this legislation is an internal market legislation. So for those who are lawyers, Article 114 is the main legal basis. What does it mean? A classic internal market legislation means a number of rules for the placing on the market and putting into service of certain products. In this case, the products are AI systems. This approach is pretty much aligned with a very large amount of EU legislation on products, which should be applied jointly. And I'll explain in how that works. In particular, when it comes to AI, that is a component of products, like, for instance, a robot or a medical device. We do not cover AI for military purposes. An essential element that will come over and over in our regulation is a risk-based approach. I'll discuss briefly what that means. And indeed, we use the pyramid to express a bit the concept that essentially the more you go up, the more regulation becomes stringent. But essentially, a risk-based approach means also that we do not want to regulate the technology as such, but concrete use cases. And the type of risks that this regulation is trying to address are risks to health and safety and fundamental rights, and notably discrimination. One of the principles of this legislation is that it puts both EU and non-EU providers on equal footing, in the sense that this is a legislation for putting on the market in the EU. So when someone wants to introduce a certain AI product in the market, it has to comply with this legislation. And this is nothing new. It applies to all products. Okay, so first of all, what do we mean by AI? We have identified a rather, say, broad definition, which is relying extensively on the OECD definition, and it's also not particularly different from the definitions that was also put together by the high-level expert group on artificial intelligence, with whose work probably you're already familiar. The goal of this definition of AI is to be as neutral as possible, because we don't want this regulation to become obsolete too quickly. So, and our overall aim is to cover AI in all its possible facets as they are known today. And in order to create legal certainty, we want to make sure that this definition of AI, which is in Article 3, is accompanied by an annex listing the techniques and approaches that specifically sort of should help developers and practitioners to identify when a certain software system should be considered AI or not for the purpose of device regulation. And one of the advantages of using the annex is that the annex can be amended over time by the Commission in a simplified procedure. So here we come to our risk-based approach and the pyramid. As I said, the more you go up, the more regulation becomes stringent. Notably, we think that at the bottom of the pyramid, so where the base is largest, this should essentially cover the greatest majority of AI systems, which do not present any risk or only minimal risk. So in these situations, those applications will be completely unaffected. So there will be no restrictions. Of course, there will be other regulations that may apply, like for instance, GDPR, but this regulation does not foresee additional requirements. The higher level, the yellow one, is related to those AI systems that we think pose certain transparency risks. Whether it could be, for instance, a bot in a customer service, or it could be, for instance, a content generated by an AI system through a deep fake. In this case, these systems are certainly permitted, but are subject to certain information or transparency obligations on the user of the system. So essentially, we think this system should be identified as AI as such. The next level is the high-risk AI systems. This is really the core of the regulation. Most of the provisions and the enforcement system focus on this type of high-risk AI systems. Those systems are also permitted, so the idea is not to prohibit them, but they need to comply with certain requirements, and they need to be assessed ex ante. Ex ante meaning before they're put on the market. And finally, we will have a very limited number of cases which, in our view, pose certain risks that are unacceptable in light of our EU values and principles. And those limited use cases should be prohibited. I'll briefly touch upon them later. Okay, so as I said, green area, minimal no risk, no restriction. For this type of AI systems, we foresee the possible application of code of conduct. So we think that the Commission and the board should encourage the drawing up of code of conducts for the purpose of either subjecting those AI systems to certain requirements that are the same of those applicable to the high risk, or for possibly subjecting those systems to additional requirements. The point is that this is, at this stage, a very it's not certainly the core. We think those systems should be completely unaffected, but we want to foresee the possibility that perhaps there is an interest in terms of applying certain requirements voluntarily. And so we will propose to draw up code of conduct. The transparency risks here cover essentially three situations. The cases where humans interact with an AI is the case, for instance, the chatbot, but they're not able to distinguish whether the voice on the other end of the phone is a machine or a person. The exposure of humans to emotion recognition or biometric authorization systems. For instance, you go in a shop and you have a system that checks how you react to certain merchandise and so on. And the deepfakes, so essentially the artificially generated content. For these three categories of systems, we foresee an obligation of transparency, essentially, to indicate that we are dealing with AI systems. As I mentioned, so high risk is the core. Here, there is a major distinction between AI systems that are components of products, so meaning hardware products, when those products are regulated by EU law. So the example is medical devices, machinery, but also cars or drones. We think that AI systems that perform safety functions in those products shall be considered high risk when the product itself is subject to essentially an ex ante assessment according to motor vehicle legislation, aviation legislation, machinery legislation, medical device. So you see here there is an intersection between this regulation and existing regulation. A second category of high-risk AI systems are what we call standalone. So they're any AI system that is unrelated to a product. And for these systems, we foresee 8 areas. Those areas are listed in an annex, the Annex 3. They're biometric identification of categorization of persons, critical infrastructure, education and vocational training. I see here, okay, 5 minutes. I'll try to speed up. Let me check what time is now. Okay. So these areas are broad areas, which are considered high-risk areas. But however, only the specific AI systems that are listed in the annex under each of those areas will be considered high risk. The idea here is that we want this legislation to be future-proof. So we want the legislation to be able to adapt over time. And the Commission may not change, for instance, an area, law enforcement. This is determined by the legislature, by the Parliament and by the Council. But the Commission may add within the bucket of law enforcement, perhaps additional use cases. Moving on, doesn't work. Let me do. Okay. These are the requirements. When a high-risk system is classified as high risk as such, it needs to comply with certain requirements. Those requirements are essentially those that have been identified by the high-level expert group. So something on the quality of data, documentation, transparency, human oversight, and then robustness, accuracy, and cybersecurity. What it is important to note is that all these requirements will apply in light of the intended purpose of the AI system. So the intended purpose of the AI systems is a key feature of the regulation. Basically, so the process which developers needs to undergo to, in our terminology, we call them providers, is they need to ensure that the AI system complies with those requirements, those 5 requirements we just discussed before they're put in the market. So first of all, they need to determine whether the system they intend to develop is classified as high risk or not under the regulation. If it's not in the annex, if it's not marked there, then nothing, the regulation does not apply. If the system is in the annex, then they have to make sure that their design and development of the system is in compliance with the provisions of this regulation. Further, they need to undergo this conformity assessment procedure, which means it has to assess and demonstrate that it has complied with the requirements of the legislation. Following that assessment, there is a CE marking that can be affixed. Essentially, you're all familiar with the CE marking. That's a very known feature of the internal market. And then the system can be placed on the market or put into service. Just very briefly, the regulation identifies 2 main actors. The provider, I just discussed for the CE marking process, what his obligations are, but they are not only related to that. There are additional obligations, which I won't get into detail. And then the user. So the user is the legal or natural person under whose authority the system is being used. And we foresee a number of obligations also for the users. Very quickly, at the top of the pyramid, the unacceptable risk is the AI that contradicts EU values. Here, we think that there are just 4 cases which we want to prohibit. 3 cases are prohibited without exception, and is the subliminal manipulation resulting in physical or psychological harm, the exploitation of vulnerabilities also resulting in physical and psychological harm, and then social scoring. The 4th category, the real-time remote biometric identification for law enforcement purposes in public accessible spaces, is prohibited, but there are exceptions. The exceptions are essentially 3. If you look here on the left-hand side of the column, so law enforcement purposes will not be allowed to use remote biometric identification in public accessible spaces unless when it's about searching the victim of crimes, there are threats to life or physical integrity or threat of terrorism, or it's about identification of perpetrators of serious crime according to a list which is identified in the EU arrest warrant decision. Not only it's essential that these conditions are fulfilled, but the use of the system by law enforcement authorities needs to be subject to an ex-ante authorization by judicial authority or an independent administrative body. The system per se will also be high risk, which means it has to comply with all the requirements indicated before. In addition, there will be also a couple of additional specific requirements on logging and the so-called 4 eyes principles. I will stop it here. I think I've exhausted my time, and perhaps I can come back to some questions if needed.
Thanks so much, Gabriel. That was a terrific overview. It's a complex topic, as I think people can tell, and that was a really great way to introduce some of the complexity. Thanks so much. I'm now going to go through the rest of our panelists and introduce each one at a time. And after I introduce them, it would be wonderful if they could just give just a few minutes, maybe 2 to 3 minutes on quick thoughts that they'd like to share on the overall proposed regulation, perhaps talking about what they think is particularly good or bad. And then we'll be able to get into a discussion as soon as we've done that. So next up is, this is no special order, but delighted with everybody. Next up is Emilia Gomez. She's lead scientist of the Human-Centric project at the Joint Research Center at the European Commission, and is a guest professor at the University Pompeu Fabra in Barcelona. Interestingly, actually, her background is in music information retrieval, with a focus on developing machine learning algorithms in the audio domain. Starting from music, she researches the impact of AI in human behavior, for example, on jobs, decisions, cognitive and socio-emotional development, and cultural diversity, which are obviously very relevant to this regulation. She was president of the International Society for Music Information Research and is a current ELLIS Fellow, a member of the One AI OECD network of experts on AI, and a member of the Spanish National Council for AI. Emilia, delighted to hear your thoughts.
Thanks a lot for the introduction, and thanks a lot for having me. I will just share a few slides very shortly to talk about a little bit few points I wanted to mention on the regulation, and also from the point of view of this program, which is organized in the workshop, which is human-centered machine learning, and also the things that from my point of view I consider relevant as a research challenges in this field. As it was mentioned, I work at the Joint Research Center of the European Commission. So the goal of our center is also to provide some scientific evidence and also technical support to our policy colleagues in defining the regulation. So we have been working with Gabriele and the rest of the team also on somehow which is how this regulation connects to the state-of-the-art research, also to the recent development of the field. So I was just wanted to give a short pitch on what I think on that. So this is maybe a quote from that was published in the IEEE Spectrum on the reality of machine learning research. So saying that those of us in machine learning are really good at doing well on a test set, but unfortunately deploying a system takes more than doing well on a test set. And we have been seeing also during the workshop today how this affects a lot addressing a problem in a particular context. We have seen examples in different contexts, and how changing the context, changing the uses that we do, we have to really go from the lab to real world scenario. So this is really the need or the motivation for this regulation. There is all these systems are going from the lab to the market. So we now see them deployed in real world scenarios, and then we become aware on the need for evaluation and the need of for assessment, and the need also to ensure the risks, and also to try to assess the opportunities versus risk and try to minimize the risk of those technologies. So as it has been presented by Gabriele before, this is really the motivation behind the regulation, and also it has been shown, I put here the high-level expert group that had representatives from academia, from industry, from civil society, how we should be you should make sure that AI systems are continually evaluated and addressed throughout its life cycle. So this is really an opportunity for machine learning or human-centered machine learning techniques to work on and develop research that makes sure that we really evaluate. And I wanted to focus on 3 main points that I think are very relevant and challenging from the research perspective. The first one is we see that smarter systems need smarter evaluation. There has been a strong focus in the machine learning field to develop systems, but not so much to evaluate them. So we should make sure that, of course, a system is doing what we want it to be doing. And instead of going from maximizing accuracy or having greater accuracy in new models, we also need to learn from other areas and how to evaluate, to have, for instance, strict standard certification testing tools. And I cite here an approach for 3D requirements, for instance, for recommender system, where we need to incorporate technical, user, and business views for the evaluation. And of course, we need as a field to develop standard methodologies for evaluation that I think will be crucial also in the implementation of the regulation. The second point I would like to mention that is also very important and challenging from the research perspective is that from implementation, we also need to document, and this relates to the technical documentation annex also of the regulation, and that was also mentioned by Gabriele. We need to describe very well how we develop our system, how we design it, how to evaluate, and there's still no standard methodology for this documentation. So this is really also a challenge to our field. And the third point I wanted to make is that, as it was mentioned also, we are not trying to regulate technology itself, but the proposal tries to put the technology into its context. So we need to assess risk, to define methodologies for human oversight, and also to research on short and long-term impact of AI on people, which might go beyond the machine learning community to other communities from other disciplines that might contribute to the discourse. I think that the regulation is a good motivation and presents many research challenges to be addressed in the coming years, on also how to integrate knowledge from different disciplines to make sure that the AI systems we develop are done with people and for welfare of everyone. So these are the points I wanted to make, and in short to express a little bit how this connects to our field or to research program also in this particular context. So thanks a lot for the attention.
Thank you so much, Amelia. Excellent points. Next, I'm very glad to introduce Arnav Joshi. Arnav works at the leading commercial law firm of Clifford Chance, where he leads their working group on digital ethics and is a member of the IEEE's working group on standards for ethically driven robotics and automation systems. Also involved in Tech UK's working group on digital ethics. Arnav specializes in data privacy and protection, cybersecurity, digital ethics, and AI. Arnav, we'd love to hear your thoughts.
Thanks, Adrian. And hi, everyone. I think it's really good to get a really good comprehensive overview from the speakers, and I think it sets the context really well. I'm going to try and keep my points sort of brief, but also as interesting as I possibly can. Aside from my sort of general academic interest, I'm going to try and keep these to the somewhat, hopefully not boring operational points of the sorts of questions we would get from the sorts of very large organizations that would come to us asking specific questions about sort of what does this mean and what next and how best do we, where do we go from here? I think off the bat, it's really good to see legislators sort of finally putting pen to paper after years and years of sort of dabbling in very good guidance and sort of principles and best practice, a lot of which has emerged from academia, for which, for obvious reasons, uptake has been somewhat patchy. There's been a lot of latitude granted to organizations in how they like to interpret guidance and what they would consider best practice and what they might not. I think also definitionally, it's good to see that the final definition that there's been consensus on in the proposal is not one of the more, shall we say, unhelpfully esoteric ones, and it will be really useful for organizations as they look to comply. I think given that it is a sort of a specialist technical regulation, it's really good along expected lines to see that operational governance requirements are logical and at least as things stand, are reasonably nuanced, which is something that the other regulation around machine learning that I tend to advise on, for instance, which is the GDPR, for obvious reasons, is sometimes sort of found lacking in the amount of guidance it provides on what you must really do to be able to comply. So it's really helpful to see that sort of those mechanisms and the requirements around testing, for example, which the proposal includes. I also think that practically that it comes at a time where some amount of precedent and best practice around GDPR's use for automated decision making has made really good progress. And as organizations look to comply with this regulation, they may be able to borrow from all of the good stuff that's emerging from GDPR compliance. So I do see some overlaps also in sort of language that's used in a few places in the proposed regulation, which is really good to see, because it means that we're not sort of, there's not 1,000 flowers blooming and people struggling to figure out what's where. I think on some of the more critical points, I suppose, I think, and I think someone's raised a question on this already, I think there will be a slightly difficult task for some organizations, but also regulators and courts of law in trying to interpret what harm and risk means for, I mean, I think the annex and the definition of high risk is really good and it's robust and it makes sense. But I think as we start to move into interpreting whether some of the more everyday technologies that we use are high risk and what's the level of harm that they pose to a user, that's something that I know that we've been struggling, for instance, with the GDPR as well. So there's been recent Supreme Court judgment in the UK, for instance, which is the Uber drivers case, where we now see that they're classified as employees, and all of the automated decision making that goes on behind the scenes for them, and issues such as transparency and harm, etc., are finally sort of being left to the courts to decide. We may end up seeing something similar, unless there's more sort of nuanced guidance around this, which is actually really hard to pen down, I would imagine. So
thanks so much, Arnav. I think we'll be able to come back to a lot of these questions.
Yeah, sure.
Excellent. Those are great points, and like you say, we're already getting some good questions coming in on just those points. I want to make sure we have time to introduce everybody else. So next up, we have Michael Veal. Michael Veal is a lecturer in digital rights and regulation at University College London. His research focuses on how to understand and address challenges of power and justice that digital technologies and their users create and exacerbate in areas such as privacy-enhancing technologies and machine learning. Great to have you with us, Michael.
Great, thanks, Adrian, and thanks everyone. So I want to raise some points around the regulation. They might be a bit esoteric, but I think some current challenges and issues with it as it stands in the current issue, the current version, that I'd like to see rectified going forwards. Gabriela did a great job of summarizing it, and it is a complex piece for those who are not familiar with product safety or unfair terms law already. So the first challenge I think we have in the regulation is it plays a lot on this importance between distinguishing between a user and a provider. And in that area, and that's clearly an area that I think has given the Commission some trouble when they've been drafting it initially. We think that harms from machine learning systems come when they're put into use, but this is governing a more upstream process. So what happens in this regulation? Well, the regulation does govern both users and providers, but users have very, very few obligations under this regulation that are set out clearly in the regulation. Users have the obligation to do as the provider says, basically, to follow the instructions that the provider gives alongside their product. And then they have some broad monitoring obligations to check everything's working. They don't, for example, directly have human oversight obligations. They only have those obligations insofar as they flow through the instructions given to the product, given by the provider of the product. And that makes quite an interesting challenge. Human oversight obligations, we typically think, and other EU law really require careful examination of the organizational setup of a user. For example, does a frontline worker really have the ability to challenge a decision that's being made on the ground? Will they get fired or reprimanded for doing so? In the early leaked draft of the regulation, which I know Commission can't comment on it as existing really, the authority and competence requirements were under human oversight, but clearly they cause tensions because a provider can't specify an organizational form of a client so specifically and hope that you sort of regulate organizational structure through the certification of a product that they might buy or not. It's not a sensible fit. So instead, there are no obligations directly on users for human oversight, which makes it quite an interesting tension. And that's a challenging area, I think, because that's, I think, an area that we really need to focus on governing. Instead, the regulation supposes that you can design either capabilities of human oversight, which will then naturally be used, or that those are effectively determined. Those will be determined effectively by instructions. I'm not sure that will be the case, because we also find that machine learning systems are sold increasingly as APIs, as services, as very general configurable options. And this really, again, makes this tension between user and provider very difficult, because a provider of an AI service will be providing a language API or an image recognition API, maybe that can be improved with a data set via the provided by the user. And indeed, the regulation assumes that users may provide with data sets live while still remaining a user. It says they'll monitor as it learns and improves. So transfer learning, the provider can provide a generic system and users can update. That is itself another challenge because providers in that world, providers will never really have ownership of the consequences of those systems. They're very general purpose. So prohibitions in the Title III prohibitions will never trigger because providers will claim that they can always be used for a variety of purposes, therefore will never inevitably lead to psychological or physical harm. So in that world, we really see those are pretty toothless. And actually, in the way they're written, they're also weaker than the existing prohibitions under the Unfair Commercial Practices Directive when it applies to economic transactions. And that's, I think, something to bear in mind. And so I just want to then sort of finish off and say that we've got all these loopholes as a result. And we see that there's the last gap, which is that enforcement of this will be really problematic, because as it's taken the product safety regime has no private right of action. The product safety regime has powers given under the market surveillance regulation, which do not relate to users, do not relate to investigating users or getting information from them or really monitoring them. The resources of notified bodies are not going to be such as to examine users. Market surveillance authorities do not tend to have those powers or resources to go and examine all public sector agencies or users or companies. And so there's this disconnect. Citizens can't even raise complaints under this scheme. I do suggest that the EU learn from the EU Timber Act in this regard. Environmental regimes are much closer to product safety than product safety to a lot of AI issues. And the EU Timber Act allows for substantiated concerns to be raised by citizens and for basically effectively market surveillance authorities, the equivalent in there, to have to take best efforts or to endeavor to respond to them and to examine them insofar as they're substantiated. So there's a lot that needs to be sorted out, and there's a lot in the weeds really that doesn't always make so much sense, but it takes a very close reading of the regulation to follow this through. And that's what I'm really hope will get fixed both by the Parliament, maybe by the Council, and also in trialogue.
Fantastic. Thanks, Michael, raising a lot of really interesting and provocative issues. Just before we get into the discussion, we have one more panelist, and really excited to have Richard Benjamins with us, Chief AI and Data Strategist at Telefonica, also co-founder and vice president of the Spanish Observatory for Ethical and Social Impacts of AI. He's the founder of Telefonica's Big Data for Social Good department, expert to the European Parliament's AI Observatory, and strategic advisor to many startups. He's author of the books, The Myth of the Algorithm, Tales and Truths of Artificial Intelligence, and the soon to be released A Data-Driven Company. Richard, could you share your quick thoughts with us, please?
Yeah, thank you very much, Adrian, and hello, everybody. It's a pleasure for me to be here, and very interesting comments so far. I'm talking on behalf of a company. It's a different perspective. I just wanted to give a few of the highlights that I've been thinking about in this regulation. I think, first of all, it was noted already in the beginning that military use is out of this regulation, and that's one of the things that many people are worried about. But apart from military, there are also there are many statements that says about unless it is for national security. So there's another, let's say, gap in the regulation where many things that are forbidden or that are high risk can be done for other reasons than what are written in the regulation. So I think that's something to take into account. I was also wondering why an application like medical diagnosis is not listed explicitly. Of course, medical products for safety reasons are there, but I mean, if you use an AI system to decide whether a person has cancer or not, I don't see why that is not is that lower risk than a credit assignment, credit worthiness, or hiring somebody for a job. Just wondering what was the case. Then another observation is that the regulation applies both to companies and public administration, and heavily to public administration and governments, which to me, to some extent, was a surprise. But I think it was a good surprise, because it is many companies were and are afraid of this regulation for what it may imply for them. But it's not only companies; it's also governments, and I think that's a good thing. Now, from a very practical side, if you look at the requirements that are that you have to do as an organization once you are classified as high risk, it's a huge list of things that you have to do. So if we follow this, so you saw these ethical guidelines for trustworthy AI of the high-level expert group. It has 60+ questions. That couldn't be answered by one type of person. You need to bring together lots of people. We in Telefonica, we were one of the first Spanish companies that declared its principles, and then we have a methodology to implement those principles. That is the voluntary part. We have like 15 questions that take that tackle the most difficult things and tricky things in AI, like discrimination, bias, explainability, autonomy, etc. So it has to be practical for a company to work. And now we go to the regulation. It's over 100 things that you have to do, and some are very, very complex. Some of those have nothing to do with AI, but apply to any system that is a kind of high-risk system, any safety critical system, even if it doesn't use any AI. So I think there's a kind of, it covers everything that you can think of an AI system. Some of the things are specific for AI and need to be taken care of, but other things apply to any system that is working in a kind of environment. So I think in that sense, I think it's going to be very hard for companies and organizations, and especially public administrations, to live up to all those requirements in the regulation.
Thanks so much, Richard. We've heard really interesting perspectives. It's great to have experts from academia, industry, policy, and a law firm. And I know we've got some great questions already. I'm going to see how many we can get through in this time. If I can ask all the panelists, please, to try to keep your camera on as you've got now, and raise your hand if you want to answer a question. Maybe we'll try to have maybe around two people respond to each question if you feel strongly about it. I'm going to try to summarize or synthesize together some of these comments. We heard really fascinating and important points, perhaps particularly from Michael and Richard at the end, about that there seem to be a lot of really important carve-outs that are perhaps concerning. So anything that relates to military use is not governed by this at all. And in general, maybe there are a lot of loopholes and concerns about enforceability. So overall, do you feel like is this in its current form? Are the rules ready to deploy, or is this really just a discussion to get things going, and we're nowhere really close to actually having usable rules? Maybe Amelia, would you like to speak to this?
Yes, maybe I can comment a bit, because it was mentioned several aspects, such as, for instance, as a machine learning practitioner, that you take the regulation and then you try to implement somehow what is needs to be implemented in terms of documentation. Of course, there's also many things to specify. I don't think there is even in the community some standard practice methodologies for evaluating machine learning models. I mean, there's some best practices, but there's no requirements, for instance, when you submit to a journal or to a conference to say these are the best practices, no, to evaluate. This is the accuracy metric you should check. This is the error analysis. This is the evaluation study. So I think we need still as a field, and also as machine learning practitioners, to have this more defined. So I would see that during the adoption and the negotiation phase of the regulation, we might need to create standards, or at least standard practice. And there are many standardization initiatives that are already addressing that, from IEEE, from different communities. So I think there is a need, of course, to specify a little bit more some of the aspects of the regulation, because the regulation is not a technical kind of document where you have very specific I mean, you will see, I think for understanding these regulations, you might need to have a PhD in machine learning in law and to know everything. So it's also a question of vocabulary that you use in this kind of text. But yes, just to keep it short, I think we need a little bit work to get this implemented into specific practices.
Yeah, and maybe just relating it to the GDPR, which has come up in quite a few questions. People initially in our community, I think, were quite excited about what they heard as the requirement for a right to an explanation, which perhaps wasn't really so clearly there. But again, I think some people are excited about what these rules promise, but maybe it's going to be very difficult to interpret them. And even if you couldn't, even there seems to be one issue of can you interpret them, and how close are we to having valid rules for that? And also, even if you can interpret them well, maybe there are already too many loopholes that make it perhaps unworkable. Would anyone like to take that on?
It doesn't make it unworkable. I mean, the regime is based on product safety. That happens in lots and lots of sectors. Many systems are already subject to similar things. Accusations this is going to be an overbearing, gigantic regime, don't work when you think about the regime as a whole. They do maybe on some nuances, which I think needs shoring up. The question is, what will it do in the world? And I think actually the high risk side will actually do very little in many regards because of these loopholes. I think that's what needs shoring up instead. Otherwise, you just create paperwork for some without actually fixing a policy problem that exists.
Richard?
Yeah, some of the questions that you said, is this implementable as it is? I think I agree also with Emilia. There's a lot of detail that we don't know. I mean, a data set has to be error-free. Yeah? So what is an error-free data set? And it needs to be of high quality. Yeah? So how do you define high quality? And so there are no standards for that. And for instance, explainability of human oversight, it has to be adequate for the purpose. So it's a lot of adjectives that are subjective to interpretation. And I think this has to be interpreted in a consistent way. Otherwise, it's just checking a box, or it can be a very big investment to be prepared for this. So I think those discussions still need to be happen, but I understand they will happen.
Yeah, and many people have asked a very sensible question, which is who gets to decide these issues? As you say, they seem subjective. I don't know if there is a clear legal answer to that or not? I wonder if Gabriele or Arnav would like to comment on that. Arnav?
Sure.
Oh, sorry.
Sorry, go ahead, Gabriele. I'll come in now.
Gabriele?
Sorry, you mentioned specifically what issues?
Well, there's been many issues, as Richard just mentioned, but also as came up in many of the questions where people were saying, how do you know if this thing is harmful? How do you know if the data set is good? So who gets to decide this under the legislation? Is it self-determined, or is there a body which decides it? Does each country have to come up with some body?
I guess, that's a question that encompasses several different answers, because depending on what piece of the legislation you're looking at, the answer is different. So for instance, the determination about the high risk or not high risk, I think I saw one comment there. This is done by the legislator. So it's the legislator. We come indeed with this approach that is quite different from GDPR in the sense that we wanted to identify specific situations so that developers and providers can identify immediately whether the system they want to put on the market is high risk or not. And so that's why we came up with a list of areas, and that's why we came up with a list of use cases within those areas. Of course, some margin of interpretation may exist. This is the law, and if that wasn't the law, we wouldn't have judges and attorneys. I think there is so much that can be done, but certainly the effort has been to shy away from a system of full self-assessment of the system in itself and whether the risk and the measures to adapt are suitable, and rather to look at, okay, I'm a developer, is my risk subject to the solution? Yes or no? I check, there is a list. And so this has been for us an extremely important approach, because we think this is going to stifle innovation less. But of course, wording can always be improved, and certainly Emilia mentioned it. When it comes to standards, will play a very important role. We are quite aware of this.
Very good, thank you. So in particular, you think that the intention, at least, and we hope the reality is that it should be fairly clear in which risk category a particular application falls. Arnav, do you think that's fair? Is it fairly clear?
Perhaps as a starter for 10, I wouldn't say it's sufficiently clear just yet, bearing in mind that there is a huge amount of sort of debate and discussion and lobbying and expansion of annexures and things still left to happen. So I think it's, as I mentioned, a good start for 10, but there is more that needs to be done. I also think that the legislators do have a difficult task, especially in a field like AI, sort of exhaustively setting out every possible option. This is rooted in human rights. It does need to be interpreted broadly and contextually in various different circumstances. I also think that we can potentially be hopeful that, given that there's a structure not unlike the GDPR of national sort of bodies and then an EU-wide body, which will hopefully provide adequate oversight, and also the technical and legal and other sort of expertise needed to provide nuanced guidance once we do have the final form of the regulation, we'll be able to answer some of these questions so that, as Gabriele mentioned earlier on, that the regulation doesn't go out of date and is practically useful for people as they attempt to comply.
Thanks very much. I should say Michael's doing a great job of answering some questions through the chat. You can all feel free to multitask with spoken and written word. But one point that brings up is with the uncertainties in trying to figure out what's going on here, and also potentially the cost to try to comply. There's always this question, which came up also with GDPR, notwithstanding the differences, that when people ask, well, will trying to comply with these rules actually end up being much easier for large incumbent players rather than for startups? And will that stifle competition?
That has been considered in the regulation, so it is nice to see the considerations there. It depends if you think about users or about providers of AI systems. So bearing in mind, high-risk systems here are a very narrow category of AI system. Providers of high-risk systems, it's not every SME that's making systems for the judicial sector or biometric or gate detection systems. It's very narrow. We're not talking about language models in general, or just general commercial applications. So they have no obligations at all, basically, no onerous obligations at all, those kind of SMEs. It's SMEs that choose to engage in very high-risk AI or embedded very safety-critical AI that have obligations that I think rightly we would still impose on an SME who's making a lift. So that's the logic there. Users, however, are more interesting. So why I keep going back to this user distinction. SMEs who are users of AI systems do not, I think, have some form filling and dancing to do, which isn't going to be very effective in practice. So I think that's where we need to focus on, like SMEs who choose to deploy APIs that Google, Amazon, Microsoft put out there. They can meet the obligations, but they shift a lot of the obligations to the user. And the way that this regulation is written, it's very easy for Google to dodge obligations, say it'll be decided downstream, and a user to mess up. And this regulation provides no recourse to citizens or real enforcement action or even obligations for those users, in my view.
Great point. So I'd like to address that in two pieces. One, if it's okay, we'll come back in a second to this user provider issue, because I'm not quite clear on it, and I think maybe some others aren't also. But first, Michael, you're claiming that actually it's very narrow what the high risk cases are, but it seems, I think, to quite a few of us that if high risk includes, as Nuria is just saying, manipulation of human behavior, that seems to cover.
High risk doesn't include that. Nuria is wrong. High risk doesn't include that. That's the prohibited practices. Those practices do not trigger high-risk obligations whatsoever. They don't trigger the certification process. So that's just incorrect.
Good. Okay. So just being clear, it's not high risk. It's actually prohibited. And so but that seems a little bit weird, because it seems like there's lots of technology which could be interpreted as manipulating human behavior. And then you're saying, no, that's prohibited. Or in your view, you think it's pretty clear that it's a small
reasonably likely to lead to physical or psychological harm. It's a very, very high bar if you look at case law in that area. Like this is not a prohibited area. This is not about recommender systems. It's not about increasing propensity to gamble. Psychological harm is a very high barrier, and people who say it's not, I think, don't really understand, actually what a legislator or a judge would say about that topic.
That's very helpful. Does anyone disagree with that? Nuria disagrees with it.
Well, yeah. Sorry, I want to ask a question to Michael. So if you look at the use of hate speech being propagated using AI algorithms, not as an intended use, but as a use, and that leads to people committing physical harm or committing suicide. We've all seen The Social Dilemma, where this is about manipulation, which in the end has physical harm. So, of course, in the leaked version, this was defined in a different way, yeah, and they rightly corrected that in the final version. But still, it is subjective, unless I missed something from the legal interpretation of those words.
I just lost the screen. Those are actually excluded as well if you read the recitals. So typically systems that rely on actual human elements, social elements, so they're what we call social machines, are actually excluded from that in the recital. So if the harm is coming from users interacting, then the regulation actually exempts those systems. So in the system of hate speech, you would very simply argue that harm is caused by the users using those systems. It's not a function of the AI optimized to cause that harm in practice. Therefore, it wouldn't fall under this. So there's a lot of alarmist talk about this regulation that really needs to read it carefully. And it kind of annoys me, the alarmist talk around this, actually. So it's important. These are important factors. And maybe that shouldn't be in the recitals. It should be in the operative text.
But it's not only about intended use. It's also about, you have to think about second uses, about other uses that might be caused by a system. So it's not only about the intended use. Of course, the intended use is mostly positive, but there might be negative, undesired, but unintended consequences that this regulation has to take care of.
But that's not the way those particular, if you're talking about the manipulation prohibitions, it's not the way they're phrased. They have to effectively exploit a vulnerability of a specific group of persons in order to materially distort their behavior. So these are systems designed to materially distort behavior in such a manner that is likely to cause that person, not society, not like.
But general... wasn't that also the part of the cause of Brexit?
But that's not. It doesn't have a regulation about society. It's that person or another person harm. The harm can't accrue to a society in Brexit, so that wouldn't trigger that article either.
So just making sure I understand. I think, Michael, you've got a clear view that actually for those who are hoping that this regulation would stop things like being nudged by social media, this doesn't go anywhere close to that.
No, it wouldn't apply in those cases. I'm quite Gabriel. I'd be interested in Gabriel's view on this. But this is, it's a lot of alarmist talk that needs to take a black letter lawyer and read these articles.
Yeah, I mean, what I can say is that the provisions are very narrowly defined. Certainly, that's been the intention, and this is not about because we know there are other provisions, like for instance, it was mentioned by Michael before, the Unfair Commercial Practice Directive. So there is the DSA regulation, which is also being adopted now. So sometimes people tend to look at these provisions as if there is nothing else. And I think we have to put that into context. And prohibitions are a very strong approach by the legislator. So we think we have to be careful about our private, very narrow, but that doesn't mean that a lot of other situations are completely unregulated.
Well, thank you so much to all of our speakers and panelists. Fascinating topic and a lot more still to discuss. Really appreciate you coming in and talking about this with us. And this debate will go on for some time. But I know a lot of people are really excited about our next talk, and I'll hand over to Nuria to introduce them. So again, thanks so much to Gabriele, to Emilia, to Michael, to Richard, and to Arnav.
Thank you. Thank you so much. And it felt really short, this webinars, everything goes really fast, but thank you so much for sharing all your thoughts. And now we are really excited to have our wonderful speaker for the next session, Eric Horvitz. He is Microsoft's Chief Scientific Officer and a Technical Fellow. He has both a PhD and an MD from Stanford University, and his doctoral dissertation was on computation and action under funded resources. And he has done a huge amount of work since the 90s on applications of AI, on inference, planning, dialogue, human-AI collaboration, in a wide range of fields, including healthcare, transportation, e-commerce, operating systems, and aerospace. He's also very interested on the broader impact of AI on society, and particularly concepts like robustness, safety, fairness, transparency, a lot of these concepts we've been talking about all day today. And also, of course, the ethical implications of using AI systems in the open world, so like in the real world. He co-founded the 100-year study on AI and the partnership on AI to support people and society. And the partnership on AI, which you probably have heard about, is a joint effort with industry, civil liberties groups, academics, and scientific organizations to sort of like maximize the positive impact of AI while minimizing its negative impact. He has received numerous awards, which I cannot fully list in a couple of minutes, including the Feigenbaum Prize and the Allen Newell Prize for his contributions on AI. He has been elected a fellow of many respectful institutions, including AAAI, the ACM, the National Academy of Engineering, the Academy of Arts and Sciences, the American College of Medical Informatics, the American Association for the Advancements of Science, and so forth. He served as president of AAAI, and he is on many advisory committees at a very high level, including the National Institutes of Health, the National Science Foundation, DARPA, and the Allen Institute for AI. Since in 2019, he was nominated to serve in the US National Security Commission on AI. And it would take me like, I don't know, an hour to continue talking about Eric, but I think I would just say that for me, Eric is an inspirational figure. He hired me at Microsoft Research in 2000, and since then he's been a wonderful mentor, in addition to being a highly energetic researcher and an excellent speaker. So I'm sure his talk is going to be thought-provoking and also inspirational. So without further ado, Eric, the floor is all yours. And,
yeah, thank you, Nuria.
Share your screen with us.
Okay, let's share screen one. I think that should do it. Great.
Eric, should I give you a cue when you have about 5 minutes left?
Yes, that'd be great.
All right.
Great. And we'll make this an anytime talk, so you can stop or go longer if you'd like. Anyway, it's great to be here today. Thanks. This is a great workshop with a great set of thematic foci. I wanted to talk today about human complementarity and human AI complementarity and human AI collaboration. I wanted to start with some basic directions that I think are interesting and important. You know, today a major focus on using machine learning, let's say in healthcare, focuses on diagnoses and outcomes, and accurate diagnosis, troubleshooting have been really important in AI and medicine for decades. One example of a system we built about almost 9 years ago now was called Readmissions Manager. We shipped this across the world. It was used in hospitals in the United States and Europe. And it does local machine learning. It tests and it trains and tests locally, and it builds models that are used to predict that a patient will bounce back to the hospital within 30 days. Bounce back probability is displayed next to each patient at discharge time. And physicians can consider this probability when they make decisions about allocating, for example, special support to patients at high risk of readmission. Some of the feedback we received, and this is true for many areas where we supply predictions in the real world, in the open world, is doctors did not necessarily know how to transform a probability into a decision. Which patient should get an expensive bundle of interventions, for example. So questions about going from predictions to actions highlights really an important opportunity for helping people with decisions. The rubber really meets the road with decisions, going from data to predictions to decisions. And we have to think deeply about decisions. So one direction for enhancing people's ability to understand hard challenge problems with action is coupling machine learning with decision analysis. For example, for congestive heart failure, to understand the cost of readmission, the cost of an intervention, the reduction of readmission, the rate with taking interventions under uncertainty. And so building utility models and understanding, for example, how the likelihoods being computed by a machine learned model intersect with that decision analysis is going to be critical. And one thing we did was to extend what we were doing was did this coupling at train and test and simulation could actually help physicians understand for different costs being or investments in packages to keep patients out of the hospital and different likelihoods of success to visualize what different thresholds would mean for on probabilities for taking action. I think this kind of thing is going to be very important moving forward. But I've been interested in even more fundamental couplings of humans and AI systems at the level of cognition, beyond these designs with expanded visualizations. How do we actually build systems that understand human cognition and human limitations? There's been over 100 years of research in psychology that's yielded results on the characteristic limitations of people, as captured by this high-level graphic here, where the y-axis captures capabilities, and the irregular frontier alludes to stereotypic biases and blind spots and gaps in human cognition. Now, work in psychology has spanned different areas, and we'd like to sort of think about how machine intellect could expand and fill those gaps explicitly, for example, in the areas of memory, attention, and judgment to augment human cognition. Let's think about judgment for a minute and start with some basics and move into some more detailed modeling methodologies. Several years back, we built a predictive model from a database of 15 years of patient visits to a large emergency department at a Washington, D.C. hospital. To build the data set, we identified cases where a patient came to the emergency department and was discharged by the expert shortly thereafter, but then came back within 48 hours with a primary diagnosis that was nowhere on the chart, and they were admitted as an inpatient. Now imagine if we just filtered the 15 years of patient records to look at these patients who were discharged, came back quickly, and were admitted as inpatients with a different diagnosis than was listed anywhere when they were discharged. So we built a model that could predict these kinds of occurrences from that data set. Rather than being redundant with expert reasoning, the system powered by this data now reasons about surprises that might be hiding in the cognitive shadows of expert reasoning. So at discharge time, the system raises an alert and suggests to the clinician, this case might surprise you. Do you want to see what I'm thinking? It's the kind of advice that doctors might be quite interested to review. Now, dipping more deeply into this topic of errors in hospitals and what we can do better, more by analogy in other areas as well beyond healthcare, a recent study from Johns Hopkins estimated that over 250,000 deaths annually in the US, and I'm sure the same is true for Europe, were caused by human errors, making these deaths the third leading cause of death right after heart disease and cancer. Unfortunately, these deaths are now in fourth place, replaced by COVID-19, which in the US is up to over 500,000 people. So the high rate of deaths based in medical errors frames a key role for AI systems. And this is of building safety nets, analogous to this safety net here pictured under the Golden Gate Bridge to capture workers when they were building the bridge from falling. To err is human and we have to expect errors, but could AI help as a safety net? So the prevalence of fatal medical errors in hospitalized patients motivated a research effort that we undertook, led by my advisee, Dae Lee, who graduated last year at the University of Washington, and work that addresses a tragic phrase that's used in medicine. This phrase is called failure to rescue. It's kind of a sad set of words, but it refers to missed opportunities to save patients who die after encountering a treatable complication. So what we did was, and we just published this work, what we did was we said, let's collect a large database of patients from the University of Washington Hospital. We're going to apply distant supervision, given what we have in the chart for what happened earlier, because these charts tend to be tagged later. And we basically learned to predict by looking at the time-stamped actions when a patient would soon need a life-saving maneuver. We had sort of proxies for organ failures in the medical records, wanted to capture situations where we could predict the start of a cascade towards death in advance, 4 hours, 8 hours, 12 hours. And this kind of work is promising in setting up AI safety nets to reduce failures to rescue patients. So it's a different task than just trying to replicate the expert. We're now trying to build the ideal safety net. I think aiming AI systems at the critical regions of need like this in cognitive gaps and blind spots will have great payoff. In this area of memory, there's another rich space of possibility. Several years ago, Ryan White, Paul Bennett, and I, and a few others, these are former colleagues of Nuria's when she was with us at Microsoft Research, built a system that's now labeled under Cortana for detecting commitments that people make to others in email. So, for example, I got this one morning I woke up and I said, well, here's some commitments you made to Nina Balkan, that you'll seek to watch something on a video and get back to her. I mentioned to Alex Madre that I'll provide feedback soon. So to know what I might forget per important commitments is very important, and having a model for forgetting and remembering is very important there too, to not overwhelm people with items that might not be important. At AMIS several years ago, Ajay Kumar, who'll be speaking later at the workshop, and I built Jogger, which was a context-sensitive reminding system. And what we found we had to do is we needed 3 separate models. A model that was from data, predicting that a user would forget item X. A model that predicted it was relevant in context, at hand. And then a model that predicted the cost of notifying the user, reminding them now. Running all 3 models together would be important in an elegant reminding system. in some related work on memory, the Memory Lens project, built a number of years ago that was presented at CHI and then at the CogSci conference, looked at predicting off calendars and off pictures distinctions that would be recognized by their owners as landmarks. In other words, what items among all photos, among all activity, among all appointments would be recognized as recognizable landmarks based on this, in those days, a graphical probabilistic model, several of them running together. For example, what appointments were landmark appointments that you can find others if you can jump between them. I want to talk about deeper weaves going beyond design into between machine reasoning and human reasoning to look at complementarity of various kinds. One approach that's very important and is a big opportunity area for us as a field is building joint models of human cognition and the world. And here's what I mean by that. Human beings looking at a problem, a situation, for example, and they may have a probability distribution as to what's going wrong, let's say troubleshooting a system. We can build models that predict what humans or estimate what humans might be thinking, their beliefs, goals, knowledge about a situation, and that's our estimation here in green. And then we can have AI systems built from large-scale data that make their own predictions about the world, whether it be traffic or a patient or failures in a large-scale system like an aerospace system, like a rocket or space shuttle, for example. And the system will have its own distribution. And the idea is to take an estimate of what humans think together with what the system is thinking, maybe based on more sensors and more data, and figure out how to ideally update or inform a human charged with making decisions. So here's an example, that was the first one for me in this space. And it was during my graduate work at Stanford that I was introduced to the Mission Control Center at NASA Johnson Space Center, and I was looking at time-critical decision-making at the time. We focused initially on some challenge problems, working with a particular team there on the shuttle's mechanical systems, in particular its propulsion systems. And you can imagine you get the schematics, you work with experts, you build, in those days, a Bayesian network to diagnose faults in the space shuttle propulsion system, some quite important, high stakes, time critical during space shuttle launches, for example, and deorbit. Then we started thinking deeply about the decision problem, and to this day we build this influence diagrams that capture not just probabilistic graphical models, but actions and utilities. And we're looking at the duration of the process and what was going wrong and the best actions to take under time pressure. But this is actually someone we were working with back then at Mission Control. They're looking at large screens full of numbers of streaming sensors. And we started thinking about the real problem was not necessarily automating an action, but the problem of display to a human operator. So now the operator decision becomes this uncertain variable here. And we want to sort of display information that will help the human operator do the best they can. So we added this human dimension to this decision problem now. And if you push this through, you end up thinking deeply about what models that will predict what humans will do. Working with an expert trainer, he built a model for a non-expert and an expert. And then you can imagine you can develop new kinds of metrics. Like in this case, we created this notion called the expected value of displayed information for an operator. And when you run this in real time, we decided to simply just highlight information that the system thought was most important to make this human the best she could be, by understanding what she might do if she saw specific information and note and recognized it. So it's interesting to think about what you might do by thinking about joint actions of belief and states of systems in the world and weaving them together. Now, I want to talk about more modern work, deeper weave with machine learning on learning about human AI complementarity, meshing human reasoning with machine capabilities. And an exciting direction for me and for our team is using machine learning and inference itself to do the weave. So here's the example that I think is really powerful and exciting. And it goes back to pathology. So in 2016, there was a challenge called the Chameleon Grand Challenge. It was a challenge about detecting breast cancer metastases in lymph node sections where breast cancer tends to show up if it's metastasizing from its primary location. Now, in the challenge, the best machine learning system, a deep neural network, did not do as well as human pathologists, I assume to the cheering of the humans. The human experts had a 3.5% error rate, capturing their false positives and negatives. Now, surprisingly, a simple combination of the best AI system and the human output about the cases led to errors going down to 0.5%, an 85% reduction in human errors. You think about why this would happen. You know, machines and humans have different overlays of false positives and false negatives. So if you figure out a way to combine them, you might be able to reduce the errors. This frames some work we did 2 summers ago with intern Brian Wilder, who led the effort. We gained access. We actually spoke to the Chameleon people and we said, can you send us all the data on human performance, those top-notch pathologists, and as well as all the the images. And so you think about this in the traditional problem, we have the training set of positives and negatives of breast cancer metastases in lymph node sections, and we build a system based on trying to gradient descent and so on, trying to minimize a loss function. And what we did instead was we said, let's take that and think deeply about the fact that we now have a human performance data set. And we asked the question, could we extend the solo AI approach with an AI plus human expertise approach where we actually build a larger system and formalize it such that we actually are computing the expected value of human input for any case? Because we have how humans did on cases as part of the data set. So we have this idea of value of asking the human, and we can actually now do an end-to-end joint training of the model and the query policy about whether we ask a human and then make the recommendation as the AI system. So to give you a sense for what happens when we did this, and we had several different models in the paper, which we just presented this year at AAAI in January. Give you maybe some insights here. So 70% of human errors we found were concentrated in a region containing just 10% of those problem cases. When we ran standard ML, like the old-fashioned ML, 30% of the errors of the ML system were in the same region where humans had their problems. When we ran the new model with the joint optimization with the query policy to humans being part of the optimization, the joint ML model now had 0% errors in the regions where people had their errors. Now, when you do this, these models have limited bandwidth, so it pushes the errors elsewhere. So errors went up in other places, but those places the system learned to ask people because they were good in those regions. So we're learning to complement humans in that way. Beyond that paper, we have other pieces of work going on. Gagan Bansal, an intern in our team for several internships, had just published a paper with us at IJCAI on optimizing the AI human team. And in that case, we basically looked at an objective function that was trying to find regions where the system was confident. And the model was if systems weren't confident, human beings over a certain threshold wouldn't even look at the information coming from the AI recommendation. And other work going on in terms of looking at reinforcement learning, where a system learns when humans will have blind spots versus when it has blind spots, learning from simulation and then running in the open world. Now, I mentioned that we're just getting going, and in a longer talk, we would be spending time on the coordination of initiative, because humans and machines working together, it's not just a one shot, but sometimes it's multiple steps going back and forth. So there's an idea of a mix of initiatives, and volley of control, and it's very important to identify, and there's a whole set of methodologies we can employ, including reasoning under uncertainty and decision theory for coordinating initiative. It's going to be a big area, you know. So we see this in the initial technologies that are being fielded. For example, the Tesla will just, if it loses confidence in autopilot, will throw control back to the user very abruptly, with making a loud noise and just saying, "Hey, take over, steering wheel's yours," and giving up. And then the latest versions of the Tesla actually are asking people to do more kinds of mixed initiative at traffic lights, signaling with their feet, for example. And there's a whole bunch of work going on, and that's possible in thinking through a human and a system someday looking at a problem. This blob again here. There's the idea of the problem being divided into alpha and beta by the computing system. The system knows it can solve beta, but the alpha problem, that's for human beings to solve, and communicating this back and forth and thinking through the technologies for doing that well. But we're not going to have time to go through that now, given my 20-minute limit today. So I think I'll just summarize by saying there's lots to be done with human AI synergy. It's wide open. We just barely scratched the surface. One approach is building systems that address gaps and blind spots in human capabilities, building joint models of cognition in the world, harnessing explicitly human AI complementarity with machine learning as the glue, and then mastering coordination of initiative. And so I'll stop there, and we'll have time for some discussion and some questions. And really, thanks for having me today.
Thank you, Eric. Perfect timing too. So thank you so much for a really interesting talk. I see there is a question which says the following. It says, this is fascinating to have to use a machine learning system to be trained where humans are not so good, so it can complement humans. And then the question is whether you tried having two different models, machine learning models, one that is particularly trained to excel where humans are bad, but then a second one that is trying to be better than humans wherever humans are good, even if it does very poorly anywhere else, and then somehow combine them to see it does even better than having a human.
Well, our system, one that we built, actually had that property. So it would basically, since we're doing joint training, we're getting the best of the machine learning, and it's basically just trying to sort of figure out when humans would actually give you a boost in per value. So keep in mind that the model also had cost of asking a human. Let's say a pathologist is not inexpensive to sort of call up, and might be time delay too if a human's not around. So it's looking at the cost but the actual value above what it can do. The example I gave was just giving you kind of an insight as to what's happening with the air terrain when you look at certain regions and so on. And we can do much more, and the paper has much more detailed analyses. In fact, what we didn't publish was visualizations where we looked at like the embedding spaces and looked at like, wow, where, is there a way we can see visualizations of like coming up with even causal understandings of why people are so poor in certain regions? We actually, and AJ will talk about error analysis tools later today, but AJ Kumar actually applied our error analysis tool to humans to see what's up with humans. Like could you actually figure out like a decision tree about where they're failing when it comes to the type of images and so on, which might be even useful in training someday and taking humans to the next level, even without systems by their side.
Yeah, so I have a related question to that, which is, what are your thoughts on generating trust on these systems if the system is finding people's blind spots and sort of like showing where they are not very good at? Like, what is your experience in humans trusting the systems as opposed to being maybe having their own biases and not realizing that this is a blind spot that they have, and therefore maybe not trusting the system, thinking that the system is wrong, that they are right?
Yeah, all I can say is that we don't know very much about some of the actual human factors when it comes to trust or usability of these systems. I know when we didn't feel that surprise, I called it the surprise model in the emergency room that I mentioned. But whenever I would describe the data set and the kinds of things it was discovering, physicians would say, oh, didn't think about that. That's interesting. And so even the definition, like this system was trained on events that surprised experts, would be more, you'd be more apt, you'd think, to trust that system than a system that was built to help be like you. So, you know, it's just so focused on stuff that stumped your colleague in a way.
Yeah, I see. No, I mean, the human element, I think, is very important to get these systems, you know, to being used. I think there's a question about data, which is to build a model of how well humans do in certain tasks, particularly experts. We are talking about pathologists, for example. You need to have data sets where multiple humans are labeling, you know, the same instance. So that's not easy to come across. So one of the questions is, do you have any ideas on how to incentivize generating these kinds of data sets where there will be high quality labels provided by experts on the same instances to really understand and build a model of where humans fail and where humans excel?
Yeah, it's a really good question. I know that when you go into a hospital and you say, we'd like all the data you have on patients that died because of errors. You're not going to get a whole committee coming shouting and giving you all this data.
Are you a lawyer?
So we had to go in very subtly and say, we're looking for these kinds of cases, you know, and they actually, just so you know how this worked, it was the patients we got 40,000 patient cases at University of Washington who were elective. In other words, they weren't there because they had a fatal issue, right? Elective patients who somehow didn't leave the hospital alive or leave the hospital at all. And so that to us, that we called those, like, you know, probably unplanned deaths.
Wow.
And we didn't call them errors, for example. But in general, it's interesting. And the question I also would have, well, let me just say that for this whole group here, there is so much to be learned from cognitive psychology about humans. It'd be nice to even be able to build simulators someday to build, you know, to build simulated data sets for our machine learning systems based on our understandings of what humans tend to oversee or hallucinate, or whether it be in the realm of beliefs or even vision. I just think there's so much insight and sets of results to be harvested from cognitive psychology for people interested in human AI collaboration and interaction.
Great. Well, thank you very much, Eric. I don't think we can clap, but I'll clap anyway. So it's very hard in these webinars, you know, to give feedback to the speakers. I think it was a really insightful talk. I see a bunch of people clapping with their little hands. So this is great. And yeah, I think you gave us a lot of ideas also and inspiration. So thank you very, very much.
Thanks very much. And I see some friends. Adish, how are you?
Yeah.
Other people. That's great. Adrian.
Ciao, ciao.
Thanks, everybody. Bye-bye.
Ciao. Thank you.
So at this point, I'm going to introduce our next speaker. Our next speaker is Kalisha Bullard. She's a postdoctoral researcher at Facebook AI Research. She completed her PhD in computer science at Georgia Institute of Technology in 2019, where her research focused within the space of interactive robot learning. During her postdoc, Kalisha has expanded her research to explore the space of multi-agent reinforcement learning, currently investigating how to enable multi-agent populations to learn general communication protocols. More broadly, Kalisha's research interests span autonomous reasoning and decision-making for artificial intelligence in multi-agent settings. Today, she's going to talk about active learning in realistic human AI settings. And without further ado, you can start the presentation.
Thank you, Stratus. Thank you for the introduction. I'm just going to go ahead and share my screen now. Okay, can you guys see that? Okay. Okay, so thank you all for inviting me to come and talk a bit about my work. This is actually work from my PhD. It's on active learning in realistic human AI settings. And in the spirit of human-centric machine learning, we're going to talk about how to enable a robotic agent to adapt its querying strategy for for environments where it's more realistic to have a human teacher, where it coexists with a human teacher. So in general, as Stratus covered, my interests are in multi-agent settings, and I mean this in a more general sense, which includes human agents as a part of the system. And so my research has always kind of looked at this relationship between decision-making and learning. And in my PhD, it really looked at active learning, which is the problem of decision-making for the purpose of learning. So we think a lot about how to give agents a strategy or policy for enabling improvement in learning and generalization in learning. And then my postdoc has really focused on reinforcement learning, which is the opposite direction, learning for the purpose of decision-making. So learning to improve one's policy for making decisions. So the focus of this work is going to be on active learning, which is really situated in more realistic human AI settings. So, so let's imagine that we have a robotic agent which has been deployed in some environment, like the ones depicted on the right side, and it needs the ability to learn about objects in its environment in order to perform tasks to be useful. So even in homes like these, which are not necessarily unreasonably cluttered or messy, it's challenging for the agent to decipher an effective strategy for learning about objects in its environment, because there are so many objects and that can be an overwhelming task. But humans in the environment can help the agent to learn about its world in a much more sample efficient way by providing guidance and/or feedback for learning. So learning from different, and so these are some images of human-robot interaction that we might see, that we might want to see in the future in more realistic home settings. And this talk is going to focus on interactive learning in these kinds of contexts, or inspired by these kind of contexts. So learning from demonstration is a field which contributes models and algorithms for enabling an agent to learn from data provided by human examples. But, much of the research has historically focused on the passive learning case, where an agent primarily plays the role of an observer. But as we move closer to real world context, there are some inherent properties of a learning environment that can make teaching particularly challenging for a human partner. So a human teacher would have uncertainty about what the agent has already observed in its environment, particularly if you think about over time, which objects does the agent have information about, which objects does it not? And so what to teach the agent based upon that, how the agent is modeling the learning task. So if you knew how the agent was modeling the learning task and how it was reasoning about the world, it could enable you as a teacher to do a better job of trying to equip it with what else it needs. But that's difficult for a human who's situated in this environment, the agent to know. And also the state of the agent's knowledge. So like tracking the agent's knowledge over time is really an unrealistic expectation to put on human teachers. So what we want is to enable a learner to be a partner in its own learning process and to mitigate some of the challenges and reduce the cognitive burden placed on the teacher. So, there's also limitations on the teacher's time or cognitive load because the teacher has other tasks in the setting. So, when we look at human learning, however, if you look at these students raising their hand, you think about what are some of the adjectives that come to mind. You might think of curious, engaged in learning, and also this perception that the students have some sense of what's going on and they're taking initiative in their learning process. So they seem to implicitly understand when it's time to take their turn, and presumably they have some model for what they need to ask in order to resolve their uncertainty or to be responsive to the other agent. So inspired by proficient human learners, in this work, we sought to design active learners capable of not only reasoning about optimal query selection, which is typically what active learning reasons about, but capable of managing their own learning process and really including the human agent in its reasoning. So let's talk about the standard problem setting for active learning and then how we modify that for more realistic human AI settings. So typically there's an unlabeled pool of instances that the agent sees as input, and there may be some feature extraction system that allows the agent to extract a set of instances or a set of queries, which are basically typically like some kind of closed-ended query, like does this object in my environment have a particular label, and the Oracle could say yes or no, or is this feature relevant, or the Oracle could say yes or no. So it would have a batch of these query instances, and it would use some type of function to select a query. It would select some query XQ, and it would update the unlabeled pool, remove that unlabeled query from the unlabeled pool, and then it acquires a label from the human agent, and then that gets added to the label pool, which is effectively the training sample. The classifiers get updated, and then this continues until termination, either depletion of some query budget or until the instances have been totally depleted, the query instances. So these gray pieces represent what we're going to change out for a more realistic problem setting. So agents should be able to reason about, agents are in a realistic environment, not necessarily given some static unlabeled instances, but should be able to reason about how the environment is changing and extract scene information. So we set this in a dynamically changing environment. Agents should be also able to compute the state of their learning beliefs and track their knowledge over time. So instead of just getting a pool of instances, the agents will have we're going to change it so that the agents have a belief state, a learning belief state that they're using to track their knowledge over time. More generally, instead of just being able to make some closed-ended query, human learners are able to choose from an expressive set of communication actions and decide what action makes the most sense. So agents should be able to select a communication action from a more diverse set of actions. They should be able to decide whether or not they need to query. If not, that they can just go back to monitoring the state of the world. And if so, elicit a response from the Oracle, then the agent should be able to update its model just like it would for typical active learning, actually, with either labels or feature information that it could get from the teacher. And then this would continue until some termination criteria is met. So these red pieces really represent the aspects that we modify for a more realistic problem setting, where an agent coexist with a human teacher. And we want it to function more closely with the way that human learners might function in an environment that's realistic. So what we really want to move is towards agents who can manage their own learning process in more realistic learning environments. And in particular, the contribution that the agent makes to learning is that it should be able to track the state of its knowledge and uncertainty, which typically would happen in active learning, but in a changing environment. So we're taking into account the non-stationarity within the environment. It should be able to determine when it needs help. So typically active learning assumes that the agent always makes queries, and it's most advantageous to deplete the query budget as quickly as possible. But we want to enable the agent to decide that sometimes it's not advantageous to make a query. Is that? Oh, okay. The agent should be able to reason about what type of knowledge it needs to extract from a more diverse set of queries, not just closed-ended queries, as is typical with active learning. And it should be able to reason about the constraints of the other agent in its environment, which is really the teacher or the human agent. So reason about this more similarly to like a multi-agent kind of problem. So in particular, we can separate this into two clusters. One is really about inferring belief state and expanding the expressivity of the action space of the active learner. And the other is about expanding the decision expressivity so it can take into account a more comprehensive set of decision criteria that makes decisions. So we're going to focus on the first one first. And so this is really going to modify these aspects: belief state, communication, action selection, and the responses elicited. So the problem setting here is that you have a learning task, which is one of concept grounding in a non-stationary physical environment. So the agent needs to ground concepts, presumably related to some downstream task. So the learning problem is to infer some mapping F that maps the set of concepts that it's been given a priori to some object instances in its environment. And here are some examples of the type of non-stationarity we might expect the agent to encounter. So Y1 depicts changes in orientation and lighting. Y2 depicts changes in underlying object state, like if a pie is being eaten in the environment. Yn depicts changes in texture, like when my cat scratches my couch. And so we assume that there's no external data set and no pre-training. So the agent querying policy controls all the input that it can receive in order to train its concept models. And the query budget is given a priori to represent this idea that it doesn't have unlimited access to the teaching agent, who has other responsibilities. So basically, this is a table to try to help situate how this work contributed to active learning literature. And effectively, in prior literature and literature before this work, there were different types of queries that people, that algorithms looked at individually, but this was the first work to look at queries that elicited both demonstrations, labels, and feature information simultaneously. I say both, but diverse types of input simultaneously, and to reason about the teacher as part of the objective function of the learner. So it's a principled framework that really tries to like generalize the active learning problem to more realistic human AI settings. And so in particular, the first work is about expanding the expressivity of the action space. So can we enable the learning agent to effectively reason about when to query and what type of queries are most useful amongst a diverse set of options? And given reasoning about when to query, how can it adapt a strategy to a non-stationary environment? So we use decision theory in order to model the reasoning framework. The first thing is that the agent has a learning belief state, which takes into account information from its changing environment, as well as from the oracle's feedback that it would have gotten from the previous turn. It has a set of communication actions, which are different types of queries it can ask, as well as the ability to not query. It has a transition model, so it's actually reasoning about expectations around the teacher's response. So it can try to simulate what it may expect the teacher to say, and then reason about what is the maximal thing to do. And then it has an objective function that it's using in order to reason about its goals, or in order to quantify what is most important for selecting actions. Active learning is typically pursued as a myopic planning problem, which means that it simulates its actions in order to select actions in order to select which one is optimal, and it only reasons about one time step out because of computational cost concerns. So the idea here is to maximize expected utility of taking an action given the current state. And so I'm going to talk a little bit about the state and action space as well as the objective function. So this is what we use for the learner's estimate of the learner's belief state, which is the learner's estimate of the conditional probability distribution of concepts Y given unlabeled instances X in its environment, where each PXY is the probability that instance X belongs to class Y. So the types of actions that we actually enable the agent with are so label query, the second one actually is the typical active learning query. So typically an agent might be able to say something like, is this object an example of a fruit? And the oracle could say yes or no. So this is a closed-ended type of query that we would typically see with active learning. But we introduce open-ended queries like the demonstration query, which is, can you give me an example of a fruit? Or like the feature subset query, which says, what features would you use to differentiate between fruits and beverages, let's say. And then we also introduced the no query action so that the agent can decipher that it's not advantageous for it to make a query. So this is kind of the way that we, the format of the objective function, which is just a linear combination of individual objectives. I'm not going to get into the individual objectives in this part of the talk. I'll talk about them more in the second part. But this is the structure of it. And suffice it to say that the individual objectives are designed to be sufficiently general such that it can reason about a general class of tasks. So for our experiments, we experimented with two different data sets. On the left side, we used a data set from the University of Washington that varied like lighting condition and orientation, et cetera, but the actual underlying object state stayed the same. On the right side, these are the experiments that I'll show results from. We actually created a local data set where this represents the type of change in object state that we would expect the agent may see. So for example, pasta goes from being in a box to being in a pot to be cooked to being in a bowl to be served in the course of, like, let's say, a make lunch task. So the kind of realistic change that we might expect the agent to encounter. And we had two environmental conditions we test, a rapidly changing environment and a gradually changing environment. So this is going to show you a video in the background of like, this is a hard-coded demonstration of the interaction. So the querying policy was actually computed offline, but this gives you some sense of what it would look like if it were happening online. But in terms of results, so this, so actually this video is from this, it's an excerpt from this gradual environmental change condition. So the gray lines, the gray vertical lines represent when the environment changes. The dots represent when the agent makes a query in order to reduce uncertainty. The green line represents when all of the baseline active learning algorithms deplete their query budget, and the orange line represents when our experimental decision theoretic framework depletes its query budget. So what we see is that it's able to spread the queries out over time in a way that is relatively consistent with how the environment is changing. So now we have a rapidly changing condition where it's actually changing like every turn, so much more rapidly, like an order of magnitude more rapidly. And what you should see here is there's a similar pattern in terms of how in terms of the agent being able to increase the learning performance over time. There's also a similar pattern in terms of the agent requesting information consistent with when the environment is changing. So primarily when change occurs, when there's a need to gather new information. And so this was a really promising result, particularly in a continually changing environment, because it means that the agent can ask questions much more slowly when the environment is changing more gradually and much more frequently. But in both cases, it's able to acquire a representative training sample because it sees a diverse set of environmental states. So this first part was really about expanding the expressivity of the action space and looking at a more expressive set of actions and also inferring belief state in order to adapt to a continually changing environment. So now we're going to look at what about when we start to expand the way that the agent is reasoning in its objective function. So, and in particular, we're going to consider the trade-off between goals and constraints. So this comes back to, let's come back to the key result that we saw in the previous work. So the key result was that the frequency of the questioning could be adapted to the rate of change in the environment, which was a really promising and exciting result. But what if we just fixed one of these environmental conditions and just said the environment is changing gradually? And, but now we want to be able to halve the amount of time. So let's say the teacher is only available for 100 turns, and this is actually about 400 turns that this is showing, I think something like this. But let's say a teacher is only available for 1/4 or 1/2 of the time. This particular querying policy can't reason about the fact that it doesn't actually have access to the teacher for that entire period of time, and it can't adjust to the teacher's constraints. So what we want to do is, look at, can we enable an active learning agent to effectively trade off its learning objectives with constraints being externally imposed from its learning environment? So consider the learning context, the actual teacher agent in the environment as well, just like we expect of human agents who take into account the social norms and the context for the other agent that it's interacting with. So in that first work, we had two different decision criteria that we traded off, which is really about average classifier discriminability and class distribution uniformity. I'm going to talk a little bit about those. So one of those is really about getting towards learning progress, and the other is trying to minimize selection bias in the training sample being acquired. So in this work, we actually ended up realizing through our method that there was some other learning progress features that do a better job of fully capturing learning progress. And so we added a couple decision criteria for learning progress, even before we start to think about constraints. So just to give a little bit of intuition about the learning progress features. So in our learning state, there are two different types of conditional distributions. On the left side, we have class conditional distribution. So the Y sub J's are our classes. So conditioned upon a particular class, this is showing what is the probability that a teacher agent will select one of these instances, X1 through Xn, as an example of the class. So the focus here is really about learning representative instances for a particular class. And there are two different decision criteria that we used towards this, and both are statistical metrics that try to get at incentivizing training sample diversity. So really covering the space of instances allowable for a particular class. One looks at variance along the vertical direction and another looks at it along the horizontal direction. On the right, but I'm not going to go into details about it, but I just want to give you some intuition. And on the right side, we look at the instance conditional distribution. So given a particular instance, what we want to learn here is a unimodal distribution over the one true class. So on the left side, we wanted a multimodal distribution because there may be many instances that could be a prototypical example of a class. On the right side, we only want a unimodal distribution because there's only one class that should be the true label for a particular instance. And so here it's trying to increase the gap between the most probable class and the next most probable class. And this is really about incentivizing prediction accuracy. So this gives you a sense of the learning progress features that we use. In this work, we also added environmental constraints to the objective function. So thinking about, what about proportion of time allocation or proportion of budgeted resources consumed? Again, we want to go for general decision criteria, but important decision criteria for helping the learner reason about the context. So the question is, so now let's say we want to optimize for these individual diverse learning objectives. So optimization for one learning episode, you have some set of weights, it's given to your objective function. There's a learning episode conducted that takes on the order of hours to conduct. Some learning outcome happens, a fitness score is computed, and then you update the weights based upon that, right? And if you do this is one iteration of the optimization algorithm, but the problem is that this is a non-differentiable learning process, which requires on the order of maybe 10 to the 4th to 10 to the 5th iteration to converge. So it's computationally infeasible to do something like, regular multi-objective optimization to learn the weights of these diverse decision criteria I just proposed. But there's something cool here. Humans, for example, have intuitively can reason about how to most appropriately query given learning context. Humans can intuitively think about how to trade off really diverse objectives for a problem that they're familiar with. And so our approach, instead of using multi-objective optimization, which was computationally infeasible because the length of one learning episode is on the order of hours, we decided to learn to weight the decision criteria by imitating what an expert questioner would do in the same scenario. And so this is actually going to decrease the number of learning episode samples we need, like 2 to 4 orders of magnitude. The key limitation, however, is optimality is constrained by the expert's proficiency, so by the expert questioner. But what we use here is imitation learning. On a high level, if you look at the top diagram, imitation learning will take a policy of an expert in the form of demonstrations and then try to infer a policy of a learner. We use inverse reinforcement learning, which is really about recovering the objective function from demonstrations of a policy. And so on a high level, what this maximum entropy inverse reinforcement learning, which is what we use, tries to maximize the log likelihood of the expert's demonstrations. And the way that it updates the weights of the decision function is by trying to minimize the difference between the expert demonstrations and the learner samples. So for each of the decision features is trying to close the difference so that the learner samples using its current weights of its decision function will get closer to the inherent weights or the implicit weights that the expert would have been using based upon what the actions the expert chose. And so baseline is just uncertainty sampling for active learning. Another baseline we use is the previous iteration of this work where we don't take into account learning context or environmental constraints. And then the red will be, or we take into account expert demonstrations, use inverse reinforcement learning to learn the weights. So I manually tuned for the previous iteration of this work. And then we're going to conduct our active learning episode. And I'm just going to show like one key result here for the sake of time. So let's say you have a long time with the expert. In this case, on the left side, the red and the black, which are our 2 decision theoretic learners, or actually there's 3 variants of it, perform comparably when you have a low query budget. But remember that the black decision theoretic learners, which is what I talked about in the previous iteration, are not able to reason about learning context. So what happens is when we now increase the query budget in order of magnitude, the black agents, if you look from left to right, basically employ the same strategy. They basically employ this really conservative strategy where they think that they need to ask questions very sparingly of the teacher because the teacher doesn't have a lot of time, but it turns out, or the teacher doesn't have a lot of availability, but it turns out the teacher has a lot of query budget, which means the teacher is very cognitively available. The red one, on the other hand, actually ends up asking an order of magnitude more queries, as is indicated by the dots. Now, to be fair, it does get redundant after a while. So there are some limitations here. But one of the things that's really cool here is that the context-aware learner can effectively adapt its querying behavior both to the rate of environmental change, like the Black ones that we saw in the earlier iteration, but also to like the bandwidth of the teacher, the time and cognitive availability of the teacher. So it is basically always going to subsume performance of the Black learning algorithms. So concluding remarks, so key implications of this work, we're trying to move towards this artificial learner who can manage its own learning process in more realistic human AI settings, and is inspired by the expressive nature of human decision-making. We contributed a principle framework that enabled an active learner to first concurrently reason over a diverse set of communication actions, so it can take into account both when it should ask questions and choose from different types of queries that take in different types of information in order to reduce its uncertainty. And then we expand the decision expressivity so we can jointly optimize for both the learner's objectives and the environmental constraints being imposed on it, or the learning context. So this allows for a richer communication and a more flexible learning mechanism, and it has the potential to allow human teachers to specify their bandwidth constraints, knowing that the agent can integrate this knowledge into its reasoning about the learning task. So really, we're trying to move towards these agents that can manage their own learning process in more realistic settings. And with that, I'll take questions.
Thanks, Galisa. This was a very fantastic talk. And in the interest of time, we can have one question, maybe, if there is someone who wants to ask something. I don't see any questions in the chat, so maybe I can quickly ask something that maybe I missed, but I would like to, if you can clarify. I think that in the first part of your talk, you mentioned that the learner has the option to not ask for a query, so no query at all. And I guess that this depends on the expectation of the learner to what the teacher would reply if the learner tried to ask something, right? And there, can you clarify maybe how you model this anticipation of what the teacher replies when the environment is changing? Yeah,
that's a good question. I actually didn't I had some hidden slides on that, but effectively the learner would take into account, so let's say for a label query, so where the learner can ask for a particular class, it would take into account all the possible classes and what is its expectation of the teachers, that the teacher will respond with each one of those labels. And then it's going to, simulate the teacher responding with each one of these answers. What will be the next state? Update the learning, belief state for each of those possible query response combinations, and then take an expectation over the learning state for, or the learning state, or the utility of the learning state for each of these possible next worlds. So basically every query response combination, it will take into account as a potential next state, update all those classifiers, and then take an expectation over that. And then depending upon when it does this for every single action, it will choose the action that has the highest utility. So if that's a no query action, that's the one that it selects.
I see. Thanks. Okay, it's clear.
Okay.
Yes, I don't think we have more time, and I don't see any more questions. So thanks again for your talk, and maybe we can have a round of virtual applause. And then I think that Human can take over.
Awesome. Yeah, thank you for that talk. It's my pleasure to introduce our next speaker for today. It will be Paidemoya Chapfua. Paidemoya received her BS, MS, and PhDs in electrical and computer engineering from Duke. She's been advised during her PhD by Lawrence Karin and Ricardo Haneo. Her research focuses on developing representation learning and deep learning approaches to characterize individualized survival time event times from clinical data such as electronic health records and, more recently, immunomics. Her work incorporates statistical techniques from causal inference, generative modeling, and Bayesian nonparametrics. She's won numerous awards for her work, and I'm looking forward to hearing about her work today. So without further ado, Paidemoya.
Hi, thank you, Mom, for the introduction, and thank you for having me here for the workshop. So today I'll be presenting about some of my thesis work streamlined for the topic of beyond ranking, building robust time to event models. So the main motivation for this work is we want to be able to do counterfactual survival analysis, and we want to answer this question of whether a given intervention will increase the chances of survival of an individual or of the population. So a more sort of like formal approach to this problem is we want to be able to estimate the causal effects of a given intervention or treatment on survival time. So for example, we may have two treatments, treatment A and treatment B, and we want to evaluate the survival times for both these treatments. So you can see, for example, here that treatment B has a better survival than treatment A. And so when we have a new individual, we may want to assign them to treatment B. So in practice, we use randomized control trials to be able to answer these questions. However, it's very challenging to conduct RSCT studies because they're usually long-term engagements, they are expensive, and they're limited in sample size. So we may want to leverage abundant observational data that we have, for example, electronic health records, to be able to augment RSCTs and estimate counterfactual survival analysis. However, we have some challenges. So the first challenge we have is that we have selection bias. In this work, I focus on selection bias that is due to confounding, where we have confounders that affect both the treatment and survival time. For example, age, which is X, the covariate, can affect both the treatment assignment A and the survival time T. And also in practice, we only observe the factual outcome because a particular individual or patient can only be assigned to one treatment. And so the counterfactual is unobserved. Another typical challenge with longitudinal studies is that we have censoring bias. And in this work, I focus mostly on the right censoring problem, which could be informative or non-informative. And so what that means is that we have incomplete observed times. So when for example, when the censoring indicator delta is equal to 1, it means that the event occurred. And so we observe the factual outcome. So here I illustrate an example of a typical EHR dataset that we may use to estimate the causal effect. So here we have 4 patients. And so the first 2 patients received treatment A, whereas the second set of 2 patients did not receive treatment A. And so you can see that in both cases, we have censoring bias, meaning that we have loss of follow-up, for example. Some patients can drop out of the study for several reasons. And in that case, it could be informative or non-informative, meaning the observed time that we have, it just tells us that the event didn't occur before the censoring time. So we need to build models that account for these kind of biases. So I will first just give you a brief introduction to survival analysis and how we can build robust models that are probabilistic, and how we can use these models to develop a unified framework for counterfactual survival analysis. And then I'll introduce a new metric that we can use to compare our estimates with RSCTs, and we can use it to sort of stratify the risk. So in survival analysis, we're mostly interested in characterizing time to event. And so we focus on 3 functions. And so we can express the relationship between these 3 functions using the hazard rate function, also known as the risk score. And so this function is a ratio between the event density function and the survival function. And also, we can also represent it in terms of the cumulative hazard function, which is an integrated hazard rate function. So let me just give you some intuition. So in practice, we may sort of characterize the event density function f of t given x using a parametric model, and this is called AFT, or accelerated failure time. And so, for example, if you assume that the event density function is an exponential distribution, meaning that inherently it means that the hazard rate is constant over time. So this can be restrictive because in certain instances, like the risk can increase over time. For example, if you have had surgery, your risk of infection can increase, and then it can decrease over time. So in those instances, we may want to use, for example, the log normal distribution. So these models are typically used in several domains. For example, in engineering, we can use them for equipment monitoring to predict the failure times. And in finance, we can use them for detecting fraudulent activities. But in this work, I focus mostly on healthcare applications. And so in this work, I focus on being able to do risk profiling and treatment planning, deciding which treatments to assign to which patients. So a typical model that is typically used to predict the hazard function is called the Cox proportional hazard, which is not limited by the parametric assumptions. So the Cox proportional hazard estimates the hazard function in terms of two terms, one which is independent of the covariance X, and the other one which is modulated by the covariance. And so in Cox, we're interested in estimating the regression coefficients better that maximizes likelihood. And this is actually a ranking likelihood. And so the main limitation with Cox is that we mostly focus on estimating the covariate effects instead of the time event distributions. And so some work has sort of extended Cox models to be able to be more flexible and go beyond ranking. And so one of those works is it uses a recast timed event as a classification problem. So you can see this can be restrictive because if we discretize time, we have to sort of select the number of beans, and also it can be very expensive if we have too many beans, and some beans can have very few samples. Alternatively, the random survival forest is used because it makes a non-parametric assumption and is based on an ensemble of binary decision trees. However, this is limited because, like Cox, it focuses on risk predictions instead of time to event distribution. So I'll introduce some of the methods that we've developed to focus on more robust time to event models using probabilistic modeling. And so I characterize these works in terms of three buckets. So the first bucket is whether it's flexible or not, meaning the relationship between the covariates and the outcome. And so you can see that in terms of flexibility, Cox and AFT models assume a linear relationship between the covariates and the outcome, and so they're not flexible in that way. And then in terms of whether the method that the function that we map from the covariates to the outcome, is it parametric or not, in terms of like what we use to characterize the outcome. And so you can see that neural network methods that we propose are sort of non-parametric, and also the RSF, as I already mentioned, it's non-parametric. And lastly, we talk about how do we characterize time. So our work focuses mostly on characterizing the event density function, because then we can formulate the problem as a generative time to event model, and we can generate samples. And so the main motivation for developing these methods is we want to build models that are robust. And so when I started the PhD, I wanted to develop high-performing time to event models that account for these four properties. And these properties are accuracy, uncertainty, calibration, and interpretability. And so in terms of accuracy, we propose DATE, which is a non-parametric model based on adversarial distribution matching. And we also propose DRAFT, which is an alternative parametric model that is based on AFT. So you can see that DATE is actually better in terms of accounting for accuracy, because it can predict distributions that cover the ground truth observed event time in terms of the normalized relative error. And also you can see that date is better in terms of accounting for uncertainty because we can predict concentrated distributions. So you can see here the median predictions from date are quite close to the ground truth compared to draft. Although draft has better coverage, it's actually more spaced, and the median is very far away from the ground truth. And also, we're also interested in accounting for calibration. And what do we mean by calibration? So from a time to event perspective, we want to be able to predict predictions that are statistically consistent with the empirical ground truth observed times. So you can see here, this is the black line is the ground truth probability of survival. And we propose SFM, which introduces a new calibration objective, which is explicit. And you can see that SFM follows very closely the ground truth. So you can see, although date is as good as SFM, it actually is not explicit. So we want models that are calibrated. For more details, you can refer to the paper. And finally, we want to be able to account for interpretability. So we actually propose a Bayesian non-parametric clustering algorithm that we can use to jointly learn individualized time-to-event predictions and clustering at the same time. So we want to be able to stratify into high, medium, and low risk subpopulations. And you can see that like our proposed method, SCA, is better in terms of stratifying risk compared to the standard k-means, which doesn't take into account time information. So finally, we have all the tools to build flexible non-parametric models. We can now start to think about how can we do counterfactual survival analysis, and how can we account for both censoring biases and selection biases. So as I mentioned, the main goal is we want to be able to do causal effect of a given intervention or treatment on survival time. And we've talked about how do we account for censoring bias using the flexible non-parametric models. Now we're going to combine both methods to be able to do both accounting for selection bias and censoring bias. But first, we have to make some causal assumptions for identifiability to hold. So first, we assume consistency, meaning the treatment assignments between the units are IAD, and we assume ignorability, meaning all confounders can be measured. And we assume overlap, meaning there's a shared covariance support between the treatment groups. And finally, we make two assumptions for censoring, because in practice, we actually don't know the censoring mechanisms that we have in our data set. So we model for both censoring approaches. So the first is conditionally independent censoring, meaning the censoring is informative. The other one is random censoring, meaning there is non-informative censoring. And so now that we can do counterfactual inference, we need to be able to estimate the ITE, which is the individualized treatment effect estimation. And so some of the common approaches that have been used to quantify the ITE is the area under the curve between the survival function, which is the difference in the expected lifetime, or the difference in survival functions, or the hazard ratio, which is the ratio between the hazard functions. In practice, actually, the hazard ratio is the one that is used in RCTs because it is considered informative. So the hazard ratio, for example, can indicate population positive treatment effect, meaning the treatment assignment is beneficial to the population or to the individual if the hazard ratio is less than 1, but if it's greater than 1, we know that it's negative. It has negative effects. And so we propose a way to estimate the hazard ratio. And so the hazard ratio can be formulated in terms of the survival functions the ratio of the survival functions and the derivative of the survival functions. And so first we need to be able to estimate the survival function. And so we leverage the model-free population point estimate non-parametric Kaplan-Meier estimator to be able to estimate the survival function. And because it's a non-parametric estimator, we need to be able to compute its derivative. So this is a bit challenging. So for simplicity, because we know that the survival function is a monotonically decreasing function, we can fit a linear function and be able to estimate the derivative. But more complex approaches like using the splines functions can be used to reduce the bias. Okay, so now we can estimate the hazard ratio. We leverage the ACTG dataset because it's an RCT dataset that has been used to compare different treatments in HIV patients. So we use it to sort of generate semi-synthetic dataset, and we can use it to evaluate our model since we can know the ground truth hazard ratio here, which is the black line. So the way we synthesize this dataset is that we use ACTG covariates and we simulate the potential outcomes using the convex cost distribution, and we introduce bias from confounding. And so the confounders here are age and CD40. So we introduce the selection bias using the propensity score assignment. And also we introduce censoring using the log normal distribution. So we have both selection bias and censoring in this data set. And so because we know the ground truth, we want our model to predict the hazard ratio that sort of follows the ground truth. So you can see in this case that CCA info is able to follow the ground truth. And so how are we able to do that? So CCA, so we model three functions, H, nu, and phi, that are parameterized by neural networks. And so phi maps from the covariates into the latent representation R. And we introduce two stochastic generative functions that maps from the latent representation R into the potential outcomes. And because we model for both censoring, so this is non-informative censoring, this is informative censoring. And so you can see that when we have non-informative censoring, the censoring is at random. And if we have informative censoring, we have conditionally independent censoring, meaning we have to model for these potential censoring outcomes. So we also add two stochastic censoring generative functions to be able to model for informative censoring. So we learn these three functions by minimizing a bound that was previously proposed in Charlotte's. And this bound is composed of two terms. So the first term is a term that accounts for factual losses, where we optimize for either non-informative censoring or informative censoring, or and now we we also need to account for selection bias, and we do this by doing distribution matching in the latent space, where we bring the latent representations for both treatment assignments to match using the dual formulation of the Wasserstein distance by optimal transport. And so we have all the mechanism to start to do counterfactual survival analysis on observational data, which is non-RCT. And so we evaluate our model on the challenging Framingham Heart study. And in this data set, our goal is we want to estimate the effects of statins on survival time. And so this data set is challenging because, first of all, as you can see here, the green line here indicates that these individuals were assigned statins, but you can see they have sort of like worse off survival, which is counterintuitive because we know from clinical trials that statins is actually beneficial. So we need to be able to adjust for selection and censoring biases, and naive approaches would result in a counterintuitive treatment effect of statins. And so we evaluate a model using a previous large-scale longitudinal RSCT study. So this RSCT study actually showed that, as I mentioned, that studies is helpful because the hazard ratio is less than 1. And so a naive approach that uses, for example, nearest neighbor assignment will result in a negative treatment assignment because the hazard ratio is greater than 1. So you can see here, when we compare our methods to existing approaches, only Cox proportional overlapping weights and hours is able to get the hazard ratio that is close to the ground truth from RSCT studies. But however, like with Cox, we are not able to actually estimate the counterfactuals. And so our method can do both causal inference estimation and factual and counterfactuals. And you can see that it's good in terms of evaluating the calibration slope is close to 1, the mean coefficient of variation is small, and also meaning it has better uncertainty estimations, and the C index is quite small, it's quite large, meaning that we have a better accuracy. What is quite interesting about our approach is that we can actually use the conditional hazard ratio to stratify subpopulations based on their individualized treatment effects into whether it's positive, negative, or neutral. And so you can see that although when we do the population, statins is helpful from a population level perspective, but we have some subpopulations that actually don't benefit from taking statins, whereas we have some that actually benefit. So this is actually an interesting perspective. And that motivates being able to do counterfactual survival analysis. Finally, in summary, I have introduced flexible non-parametric time-driven models that can account for both informative or non-informative censoring. I have also introduced a new unified counterfactual survival analysis framework that leverages comprehensive evaluation metrics that account for accuracy, calibration, uncertainty, and interpretability. I've introduced a new non-parametric hazard ratio for identifying or stratifying treatment effects. And I've also shown some results on challenging data sets like the ACTG data and the Framingham Heart study. And so for more details, please refer to our paper. In the future, would like to understand, for example, the sensitivity of our estimates to unobserved confounding, or understand the effects of both censoring, which could be informative or non-informative, and selection bias on causal identifiability. Thank you for listening.
Thank you for that talk, Paidema. That was really interesting, and it sounded like there was a lot of really awesome hard work that went into that. And congratulations on recently defending your PhD. If anybody has any questions, feel free to put them in the chat. Doesn't look like we have any, but I'm happy to ask a question. I think that new counterfactual survival, the framework you've proposed in your thesis as well as in that Chill paper, is there something, in the spirit of being at the Human-Centric Machine Learning Workshop, is there something that you're interested in working on with practitioners, and particularly with doctors and clinical practitioners, to see how effective the framework that you develop is? And is there something you're really excited about at the intersection of working with domain experts?
Yes, thank you for the question, Oman. Actually, I'll be doing a postdoc at Stanford focused on like health policy. And so in this work, I'll be focused mostly on how we can translate this work into, like implementation into like policy. And the other piece of work that is sort of missing is, so I did mention that we compare to real world RCTs to be able to evaluate, because in practice, it's very difficult to evaluate like causal inference frameworks if you're not using synthetic data sets. So if we can find ways to sort of evaluate using observational data and augmenting with RCTs, that is another like line of work.
Wonderful. Well, congrats on starting your postdoc soon. And I guess you'll be working on this, and we'll have to invite you back in a year or so to tell us what you find. Is there something that you can foresee as being very difficult about that procedure of like validating your framework? Like, where do you think a lot of the difficulty is going to lie? I know it's probably hard to foresee.
Yeah, so the main difficulty is because you have to make a lot of assumptions to do causal inference. You know, one of the assumptions is you assume that ignorability holds, and that is really that really holds in practice. And so we have to do some sensitivity analysis, you know, to see like to get some bounds, you know, when ignorability doesn't hold. And also we have to do some sensitivity analysis to sort of measure the degree of censoring, you know, because in our methods, we sort of we model for both informative and non-informative censoring, but we need to be able to choose a method in practice. So we need to do to get some bounds in, on that as well. Yeah.
Awesome. Yeah, we're really excited to see what comes of that work. With that, if we don't have any other questions, I can hand it over to Hima, who will introduce our next speaker. Thank you, Paitamuya. Appreciate it.
Thank you.
Awesome. All right, thanks, Umang. So hi, everyone. Hope you guys are enjoying the workshop. So it is my utmost pleasure to introduce Dr. AJ Kamar, who will be our next speaker. AJ is a Senior Principal Research Area Manager at Microsoft Research Redmond. She oversees research on human-centered AI there. Her research actually spans a lot of interesting problems. So she investigates the intersection of AI systems, people, and society. She explores how limitations of AI systems lead to concerns around biases, reliability and safety problems, and also novel ways for AI systems to support people. AJ also serves as the technical advisor of Microsoft company-wide committee on AI ethics and effects in engineering and research called Ether. And in her advisory role, she consults with product teams at Microsoft on issues around responsible AI. With that, I'm very excited to present to you Dr. AJ Kamar.
Thank you, Emma, for the introduction. Let me see how I can share my slides. Can you see things? Can you see my screen? I think you are muted, Hima, but I think you said yes.
Yes, yeah.
Thank you. Thank you. It's very nice to be taking part at this workshop today. I try to listen to parts and pieces of it during the day. And I think this talk is going to fit in nicely, giving a different perspective into why we care a lot about human-centered machine learning and why that matters a lot for our work and for our society. So my name is AJ Kamar. I do a lot of work around human-centered AI. And today what I want to talk about is why do we care about human-centered AI for responsible AI work that we are doing in the company? Everybody in the room knows about the upcoming applications of AI systems into the world. And many of these areas have critical importance for our society. We have to get things right. Otherwise, there will be negative consequences for the way people live and for our society. And actually, when we look across these applications that have critical importance for our society, we know that there are rough edges in terms of putting AI systems into the world. And sometimes those rough edges come across as biases, safety problems, and can cause harms for human lives. So those are the situations we care very much about putting these systems into the open world. And like many industry partners, Microsoft recognizes this threat. And in 2016, I believe, Microsoft releases Principles of Responsible AI. And as part of this mission of getting responsible AI to every product at Microsoft, I have been serving for the last few years as part of the research arm of this responsible AI mission on a committee called Ether. But right now, what we are seeing in the company is that our efforts in this responsible AI space are maturing up with different organizations joining this more research-based arm called Ether, raises our engineering arm. We have a compliance and standard process happening from our legal department. And we also have teams and champs that are spread out across the company on this mission of responsible AI. However, what we are realizing in this mission is that putting out principles, putting out an organization out there is the easier part of this, about getting this mission right. The harder piece is actually developing the practices, doing the work, and providing the help to teams to be able to address some of these very, very difficult problems that do not have simple, correct answers. So I was thinking what I can say today about the role of human-centered machine learning and the work we are doing in responsible AI. And the one insight I would like to share is that what we are seeing in our responsible work is there's one insight that's guiding our work. There is one thing, and that is the observation that AI systems are developed by people, with people, and for people. And if we are not recognizing this fact that there are people developing these systems, the data is coming from people. And at the end, across all of these application areas that I've shown, what matters is the value that people are getting from these systems. If we are not bringing this human-centered value into the way we are building AI systems, it's pretty impossible to get these systems right. So what I mean by that, for many machine learning practitioners, when they think about AI systems, they think about a pipeline like this. There's a training data set. They throw that training data into their favorite algorithm. They get a model out. They have some test data. That test data usually comes from the same distribution as the training data. They evaluate the model on the test data, get an aggregate metric like accuracy. They say my accuracy is good. It is high enough. It is better than the previous work. I've done a very good job. But what we are seeing is that when AI systems are in the real world, in the open world, the picture is actually quite different. The training data comes from people. There are people involved in the development of these systems. When these systems are out in the world, they are working with people. What matters is how these systems are working in the real world rather than a prefixed test data that we fully understand and can observe. And what matters at the end is not how great our AI system is, it is actually how great the team performances, how much value are the humans working with these systems are getting. And if you are actually missing these humans that are in this picture, then it is unlikely that our society is really benefiting from AI. So the focus of my talk today, and I'm going to try to do this as quickly as possible, is asking this question: how human-centric view that we have, recognizing that AI systems are developed by people, for people, with people, how does human-centric view change the way we develop AI systems? And how should it change the way we develop AI systems? So I'm going to quickly talk about 3 pieces of work. The first one is going to be focusing on the by people part, and I'm going to talk about how we are thinking about supporting the developers of AI systems to be aware of how their systems are functioning in the open world. Then I'm going to be getting into the issue of backward compatibility and start saying, what are some of the expectations we have from these AI systems when these systems are working with people? And then I'm going to end up, if there's time, with one quick application area that we are focusing on, and that is human bias in hiring. So let me get going with this. A lot of our work in the tooling space from my area comes from deep investigations of practitioners' experiences at Microsoft, because we need to understand what are the challenges these people are facing before we propose solutions and start building tools. So we've done a large-scale survey of the practitioners' experiences at Microsoft. We talked to over 500 machine learning engineers about their experiences with respect to developing AI. And that point that I made before got validated in loud voices, that 10% of people's time goes into the algorithms, goes into the training of the models, and the 90% of people's times goes to things that we don't necessarily think as machine learning. It goes to data cleaning, it goes to collecting data. But once we have the models, we don't have sufficient tooling for developers to debug their models, to understand where the problems are coming from. Model evaluation and deployment are very difficult, which prevents these developers to understand the real-world implications of their systems. And also, we have end-to-end tool fragmentation. Developers need to go from one tool to the next and to the next without having the right context switching with them. So to motivate the tool that I'm going to be talking about today, and if you go to our website, you are going to see that we are working on different sets of tools, including tools for interpretability. The example I want to give to promote this work comes from the gender shade study by Joe Bolomani and Timnit Gebru. Joy and Timnit showed in this work, for anybody who hasn't read this paper, is that back a few years ago, the publicly available gender classifiers out there, including Microsoft's, had disproportional error rates for different groups of people. In fact, the error rate of the darker-skinned woman was 20% higher than the error rate of the lighter-skinned men. And of course, this paper became a big realization at Microsoft, and the teams did a lot of work collecting data to diversify the data sets in the right way. And as a result of this, what we saw is that in the follow-up models, the error rates equalized and became a lot more comparable. So this showed the value of auditing and evaluation. And if we can do proper evaluation of our AI systems and understand where the errors are, we can get better at improving these systems. The question is, can we develop any generalizable tooling that allow developers to do this quickly? And that's the work that we are doing with the error analysis toolset. So if you look into the current practices of model evaluation, what we do is we have a model, we have a benchmark data set, we evaluate this model on this benchmark data set, and at the end, we get an aggregate metric to see how well our models are doing. For example, in this case, let's say our model has 73.8% accuracy. The problem is that by just looking at these aggregate metrics, we don't have an idea of where our models are struggling. Are there particular groups of people? Are there particular use cases where a lot of these errors are concentrated? Because that would mean a lot in terms of how we are going to be deploying these systems and how we are going to be improving them. So instead, what we are asking developers to do is do a detailed error analysis where we can see different regions and their relative performances. And when we look at these regions, we can see that our models sometimes doing well for some regions and not doing well for others. And then we can start asking the question of why. So our vision in this work is building tools that can help engineers accelerate the AI lifecycle, the AI loop, so that they can be informed about how they should be improving their models, go evaluate it, do this again, especially with data coming from the real world use cases, so that we can be confident that our models are working as expected out in the open world. So our tool is currently released through Azure ML and is available as open source in GitHub. And what this does is actually quite simple. We have our benchmark data set that is coming in, and we also have our machine learning model. We run the machine learning model on the benchmark data set, and what we get is, as a result of this is error labels. For every instance we are testing, we check if our model did well or it did not satisfy expectations. So as a result of this, we actually have a data set with error labels, and we can put this data set into different interpretable machine learning models to create views into model performance at different levels. So we have levels at the global level where we can quickly see how model performance changes across major dimensions that the developer chooses to see. We use simple interpretable models like decision sets for the system, for the tool to discover what are the dimensions that matter the most in terms of explaining where the errors are. And through this experience, developers can also quickly look at instances and connect the instances with these clusters to be able to see, develop new hypotheses about how the models are doing. So I'm going to quickly demo this tool on the gender shades case study. Here we are looking at the gender shades data set where there are images of different parliaments around the world with equal representation of men and women. And in this data, we expanded this data set with a bunch of human interpretable features that encodes different characteristics of these images. Of course, this is not a complete data set in the sense that there could be other features that we haven't included, but even with the features we have included, we will be able to see interesting trends. So in this data set, we expanded the data set with attributes representing the hair characteristics, facial hair, glasses, the emotion of the person, and so forth. So in this experience, we are asking the tool to build a decision tree to be able to separate the success instances from the failure instances. And each node in this decision tree is colored by the error concentration in that node. And it's kind of a waterfall model. The thickness of the edges between the nodes represent how much of the error of the whole model is flowing into these clusters. So the top node has all the data instances in it, and it has all the error, of course, and the error concentration of that whole data set is around 5%. And now the machine is using simple decision theory to be able to find what are the characteristics that correlate most with the errors. So unsurprisingly, the first characteristic it finds is that for women, the error rate is 11% instead of 5%. However, we can actually go deeper. And as we follow this critical error path of following red nodes, we are going to be able to see higher and higher concentration and learn more about where our errors are. So if the images are coming from women, and those women are not wearing any makeup, the error rate becomes 23%. On top of that, if the woman has short hair and not smiling, we see that the error rate can be as high as 35%. So here, what we are seeing is that with this decision tree, we can now look into combinations of features and how the combination of features are leading to even denser error patterns for these models. And what else we do? From these views, you can link to different interpretable techniques to be able to explain model decisions and then look into the data distribution and develop even more informed hypotheses about where the errors are coming from. And here for interpretability, we are linking to another open source library from MSR called InterpretML. At the same time, though, it is useful to the developers to get these kind of insights automatically from these tools, but they are not the end of the story. Because at every point in the development of an AI system, we need help from humans in terms of value judgments. So first of all, what attributes should we include into our analysis in terms of responsible AI? Are there others that we are missing out that are important, but because we have included these attributes, we are not going to be able to see them? Also, our tools are only at this point capable of doing this analysis based on correlations. But in some cases, something like a hairstyle or makeup or other kind of attributes could be well linked to the demographic attributes of individuals. So if we see that there's no racial category coming up in this analysis, does that mean that our models are free of biases? How do we actually make the decision that our models are free of biases? Also, if error rates are getting closer and closer, is 1% difference good? Should we stop there? Or should we do more work decreasing this gap as much as possible? How do we collect data from different sensitive groups? Do we create even more risk for sensitive groups when we are trying to collect data from them? Is it okay to scrap data about these individuals from the internet? So what I'm trying to say is that as we are providing these tools and trying to provide some support to developers for them to better understand where the errors are in their models, there are a lot of human decision making needs to happen and human judgment needs to happen to develop AI systems. And those are also processes that should be supported by best practices or domain expertise whenever possible. So at this point, I'm going to jump into the work on backward compatibility. And here, I'm going to switch gears a little bit and ask the question of, If we know that we are building machine learning, not for the purposes of the machine learning to go into the world and work alone, but to support domain experts, what are some of the properties these AI systems should have? What are the properties we are not really thinking about when we are training AI systems, but they become important considerations when these systems are working with people? So a common teamwork framework we think about when we are putting AI systems into the world is AI-advised human decision-making. In this scenario, there is an input to a machine learning model. That model gives a recommendation, but at the end, the human is responsible. So if we are working in a medical domain, there is a human professional at the end who is accountable for the decision that this pipeline is going to be putting out into the world. So earlier in the day, Eric Horvitz talked about the readmission predictor classifier. That's a great example of this AI-advised human decision-making loop. And what matters in this AI-advised human decision-making loop is that we don't really care about AI, how accurate the AI system is. We care about it as a proxy to the real thing we care about, which is the team performance. At the end, we care that this human expert becomes a better decision maker as a result of having access to this readmission predictor classifier. And currently, the way this loop works is we expect humans to develop mental models of competence about the systems they are interacting with. So over time, by interacting with these systems, humans develop mental models about when to trust them and when to override their decisions. The question we ask in this work is that, though, what happens to that mental model when models get updated? So as I explained earlier, we expect AI systems to be in this continuous iterative improvement loop where developers look at the errors and the failures of their systems in the open world, collect more data, fix them, improve them, and continuously get through the kind of the rough edges of AI systems and reach responsible AI. But through that continuous improvement process, when models get updated, those updated models may break the expectations of humans, and the human AI partnership can get harmed from this breaking of the mental model. And in this article actually talks about this happening for the self-driving functionality of Tesla cars. What this article talks about is that every time the Tesla car gets updated, the car starts making new kind of mistakes. Maybe it gets better in some spaces, but there are places where it gets worse. And because it is not consistently improving across everything, it can break the mental model of the driver. And now the driver needs to learn all over again when to trust the car and when to override it. And that's a very costly process for a human AI partnership point of view. So in this work, going over this very quickly, what we define is a compatibility score between the V1 of the model, the existing model that the human has worked with in the past, and V2 of the model, which is the updated version of the model. So the compatibility of the new model to the old model is computed based on, among all the things the old model was doing right, what is the percentage of those things the second model still can get right? So how much of these things the human has been trusting the original model with, the human can still trust when this update happens. So the goal of computing this compatibility score is making sure that the upgraded model is not going to be making new types of errors that is going to be breaking the expectation of the human. So we call this the compatibility score. So you might ask the question that why do we need to care or worry about compatibility? Don't we get compatibility by default when we upgrade our models to a more accurate version? What we see across the data sets is that it is not true. Even when we train models with the exact same data set, with the exact same algorithm, we can actually get two very different models that are not compatible with each other. And we actually see this here across well-known data sets that even when the VT has a higher performance, the compatibility can be low. And what we show in this work is that we can introduce a new loss function, a factor into the regular loss function of machine learning that penalizes models for making new types of errors. So we call this term dissonance. And by varying the lambda parameter from low to high, we can tell the model how much attention to pay into not creating new errors. And what we can do is that by varying that lambda, we can train different types of machine learning models. Each machine learning model becomes a dot, becomes a circle in this compatibility and accuracy diagram. And one interesting thing we see is that at small values of lambda, we can get a lot of compatibility for free. So we can get high accurate models that have higher backwards compatibility than not doing this form of training. But then by increasing the lambda, we can put more emphasis onto compatibility. And at that point, we start sacrificing accuracies little by little, but then gain a lot of compatibility back. So this becomes another tool for developers to be able to analyze how much compatibility they have when they are upgrading their models, and how they can use this sort of weighted learning to be able to get a lot of compatibility back in the way they are doing machine learning, at least be more informed about it. So this tool is also available as open source in GitHub. And here, in addition to this sort of backward compatible learning, we also have visualization tools for developers to see how their models are progressing or regressing. So just getting into the human experience a little bit more. Across these many domains that we very much care about, what matters is really how much the AI is helping people, how much AI is augmenting people. However, across all of these cases, I don't think we really figured out how to develop AI to help people. What we are doing is we are automating decisions, putting these systems out there, and we are expecting that collaboration is going to emerge automatically just because we can do automation, and that is wrong. Collaboration does not naturally emerge from automation. As Eric showed, that what happens in our current practices of machine learning, we are developing the best AI we can as if this AI system is going to be functioning alone in the world, and then try to, in an ad hoc way, couple that together with a human and try to get the high team performance. However, what instead we need to do is start thinking about this collaboration from the very beginning and really ask the question of what kind of an AI system we need to be able to get this collaboration out. Eric talked about this work already, so I'm just going to pass this very quickly. But one way we are trying to do this in our work is put collaboration, teamwork as an objective into the way machine learning models are trained. I think that's just one direction we can follow with respect to really uncovering collaboration, but there's a lot more work to be done there. Just finishing up with some ideas. I really believe in the future that machine learning is going to be very helpful to fill the gaps, biases, and blind spots of humans, but we really need to figure out what's going to take to bring this picture to reality. And one area we are doing this kind of thinking at the moment is asking the question of how AI systems can help human experts in the task of hiring individuals. We all know that if you are just putting AI out there to automate human decision making, a lot of biases can happen, and that's not the right way to do that. But we are asking the question of, like, if you look into the whole pipeline of hiring, are there places where AI systems can help? We know that in hiring, it's already a complicated problem because world and societal biases already exist. Our world distribution of different professions are already very skewed. At the same time, right now, we already have screening algorithms in the loop that are getting these candidate pools and choosing which candidates to show to human decision making. And while these screening algorithms can pose additional risks, they can also pose additional opportunities in terms of representing more diversity in terms of who gets shown to a human. And in our HCOM 2019 paper, we actually show that ensuring a representational criteria in the screening algorithm can help on some crowdsourcing experiments in terms of how the hiring recommendations can represent more diversity of the world. So I'll just conclude with some final takeaways. We have to develop practices and tools to be able to put reliable AI applications into the open world. And we need to think about the developers, the users, and the humans where the data is coming from. At the same time, until AI systems are perfect, we rely on human-AI collaboration, and we need to uncover what it takes for AI to be an effective partner. And in many cases, we recognize that just putting AI systems into the world introduces a lot of risks in terms of biases, in terms of reliability. But at the same time, removing AI systems from the loop does not solve these problems either, because humans, as humans, we also have important societal and individual problems. But we need to be very careful about how we are designing and integrating AI systems into the loop. So I'll stop there, and if there are any questions, I'll be happy to take them.
Awesome. Thank you so much for the wonderful talk, AJ. Again, feel free, anyone, if you have a question, feel free to jump in. But in the meanwhile, maybe I'll start with one question. So AJ, some of your work, especially the one with Brian Welder and Eric, is almost kind of trying to play to the notion of the complementarity of human and algorithmic decisions, right? So in some sense, we don't just have to design the most accurate classifier. We instead have to design our predictor. We instead have to design something that does a good job where humans falter. So that is almost like the underlying principle of that work. So I just wanted to like kind of get more of your thoughts on that, in the sense of, do you think we should, as a field, more and more move towards that direction instead of always focusing on, let's try to optimize for a model's accuracy standalone? Do you think that that's like a thought framework that we need to use going further, given that, you know, human AI complementary systems are being deployed so much?
Yes, that is the, yes, thank you, Hima, for the clarification. That is the whole motivation behind that line of work. As I said, across the many applications we are looking into right now, the end purpose is not really putting the AI systems alone into the world for the AI to take over and make all the decisions. If that is the case, I think optimizing for AI accuracy is the right one, especially if all the errors are going to have equal weight. But in many cases, that is not what we want. We still want the human to be in the loop, to be accountable for the decisions, because we acknowledge that there are going to be cases where the AI systems are not going to be able to do well. And at that point, I really don't understand why the objective of getting the highest accuracy AI is the right one. What we see with the chameleon data set is that there is actually a pattern to human shortcomings. In that data set, 50% of all of the human errors can be explained by a combination of two features. So there is a clearly defined space there where the humans are struggling, because as humans, we have our own shortcomings too, both in perception and in reasoning. And in that work, by just telling the machine that there is a region where humans are struggling and try to be extra careful, there seems to be moving the needle significantly. However, there is another part of this question that we haven't really touched yet in that work, and I'll point that out for others who might be interested in. So in that work, the machine makes a decision about how to integrate the human decision with the machine decision. So the machine is the aggregator. I think we still have a lot of unknowns about the human doing this integration, the human getting the machine recommendation, and the human asking the question of, how do I integrate my thinking with the machine thinking? Because at that point, there are so many issues with automation bias, explainability, interpretability comes into play, and getting the incentives right get into play. So I think that is the place that I have a lot of unknowns, how to actually bring the human and the machine together, where the human can be that successful aggregator, but still maintains her accountability and autonomy.
Okay, awesome. So I think we are exactly at time, but there are a couple more questions in the chat. Maybe AJ, you can look and answer in the chat, but given that we want to stick to time, maybe I'll stop here. So thanks again, AJ. And now we are going to hand it over to Adrian for our next speaker.
Thanks so much, Hima and AJ. That was a fantastic session. And I know it really resonates with me. I really struggle with my shortcomings. So a lot to think about there. We're now sadly on to our final session, but by no means, well, we're finishing very strongly. We're really delighted that in this final session, we're joined by Moritz Hart. Moritz is an assistant professor at Berkeley. He has a lot of wonderful research engaging with the consequential interplay of algorithms, data, and society. Moritz co-founded the original FATML workshop on fairness, accountability, and transparency in machine learning. And he's a co-author of Fairness and Machine Learning, Limitations and Opportunities, and Patterns, Predictions, and Actions, a story about machine learning. Really looking forward to what you have to say, Moritz.
Thank you so much for the introduction, Adrian, and my pleasure to wrap up this fantastic workshop. Thanks so much to all the organizers for having me. And let me share my screen with you. Here we go. So I'm going to talk to you about an adult problem, and in particular, some reflection on the state of data sets for fairness research in machine learning. Where we are and where we can go on that. Let me try to, where is the presenter tool? Here we go. Okay, so yeah, let's see. So first of all, this is joint work with Francis Ding, John Miller, and Ludwig Schmidt at Berkeley. Actually, Ludwig is now at TRI and will soon be at UW as an assistant professor. So in machine learning, we like to think of data sets often as benchmarks. So we often proceed by splitting data into a training set and a test set, and we evaluate and compare methods on the test set. So your code is allowed to do anything with a training set, but then we only get to evaluate it on the test setting. We look at things like accuracy and so on. We take this kind of paradigm for granted, this data sets as benchmarks paradigm, but actually, it's fairly recent. Okay, so it's sort of emerged much later than machine learning. It wasn't there from the beginning, and you can sort of trace it back to the 1980s. And there's a nice article by Pat Langley where he talks about the origins of this paradigm, and he said this experimental movement was aided in part by the development of this UCI machine learning repository that was created by David Aha in the late 1980s and started hosting these kind of data sets with the intention that they'd be used as sort of consistent, benchmarks or test cases for comparison of different methods. Okay, and so let's have a look at the UCI machine learning repository. You can do this today, and you can go online and look at the most popular data sets on the UCI repository since 2007. And you'll see that the most popular one is the IRIS data set. It's associated with Fisher's 1936 article. And the last three, I don't actually know what they're about. It's something about wine and heart disease. I've never looked into those. But the second one is sort of the unlikely protagonist of this story on my talk. And I'll tell you what's up with the adult data set and how it became sort of relevant for fairness research and what I'm going to talk about. So let's look at the adult data set. The goal in this prediction task is to predict whether income exceeds a threshold of $50,000 a year based on US Census data. It's also known as the census income data set. And it consists of about 50,000 instances with 14 attributes and was donated in 1996. And there's not a lot we know about it other than the description of this data set, which is very brief. It just says extraction was done by Barry Becker from the 1994 census based on some criteria, like presumably the age of a person, something like maybe adjusted gross income, some other variable, and some hours of work maybe. And the prediction task is determine whether a person makes over 50K a year, okay? And so the donor was Ronnie Kohavi and Barry Becker, then at Silicon Graphics. And you can email, ronniek@live.com for questions. which, by the way, let me say more on that later. We may or may not have done that, actually, and I'll tell you about it in a second. Okay, so the attributes are, described as follows, and that's really the full description of the data set. There's age, work class, education. Education num is actually the same thing as education, it's just some encoding. Marital status, occupation, relationship. Then there is a race attribute and a sex attribute. Race is coded as white, Asian Pacific Islander, American Indian Eskimo, other, and black. And it has capital gain, capital loss, hours per week, and some country of origin coding called native country. Okay, and presumably these were all related to US Census data or attributes that were found in US Census data at the time. Okay, so how did this enter fairness research? It was actually there from the beginning, and you can look at some of the very first papers on what we now call algorithmic fairness. And they actually already used this this data set. Okay, so there was a paper by Kalders, Cameron, and Pasheninsky called Building Classifiers with Independency Constraints from 2009. Another paper by Kalders and Verver that also used it. There was an earlier paper by Pedreschi, Ruggieri, and Turini from 2008 that actually used another UCI data set, the German credit data set, which is even smaller and older, but didn't use UCI adult. So I asked Toon Kalders why he started using this and what motivated him. And he said, the main interest of picking this data set at the time were the presence of a sensitive attribute, namely sex or gender. The base rates for males and females are different. The label itself can be considered ground truth, but he says the last point needs some clarification, and sort of gave me a very nuanced and good clarification there. And what he means is just that, of course, there's structural inequality in the income distribution, but as far as measurement goes, presumably the Census Bureau is really trying to be accurate in, coding or recording somebody's income. Okay, and so from there it sort of took off, right? These are all like good reasons why you might want to use this for fairness research. People started, it appeared in other papers on, various topics in fairness research at the time. These were sort of 2011 through 2016 were the years of, fairness research was sort of around, but not a lot of people working on it. But the papers or the folks that were working on it were aware of this data set. And then 2016 was the year that fairness research kind of took off, and everybody started, working on this problem, and a lot more people used this data set. And you can see that also, like there was huge uptick in usage of this data set across the community. And there were literally dozens and even hundreds of papers. And so by 2020, I think there were too many to keep track of. And so we counted just from a sort of a lower bound. This is not an upper bound. There were at least 300. There have been at least 300 plus papers on algorithmic fairness that use the UCI adult data set. And by the way, my video stream here is doing something funny, so I'm going to reset that real quick. Yeah, so there were about 300 plus papers on algorithmic fairness that use the UCI adult data set as a benchmark. So what I'm going to do in this talk, is to give you some archaeology of the UCI adult data set. I'm going to talk about where it actually came from. We did reconstruct it, and you can reconstruct it from US Census data that is still available today. And I'll talk a little bit about some of its issues, but also what's reasonable about it. And then I'll tell you about a new software package that creates data sets from available US Census microdata that we're introducing and releasing shortly. And I'll tell you 4 or 3 new data sets that we created using this package, which let you or which give you sort of a broader way to evaluate algorithmic fairness using census data. And in particular, we'll see some findings on these new data sets that kind of challenge existing narratives on this topic. So yeah, as Adrian said, please feel free to put questions in the chat. I'm actually monitoring the chat so I can see when you're asking something. Okay, so where did the UCI adult data set come from, and what is it? To answer that, I have to say a word about the US Census data products. The US Census Bureau is actually mostly known for the decennial census. So every 10 years, it does a broad census of the US population. But there's a lot more that it does. It offers several high quality data products based on extensive annual surveying efforts. And several of these surveys are publicly available or are turned into publicly available data products. Mostly those are aggregate statistics and tables, but also the Census Bureau releases microdata. Microdata means sort of individual level data. And some of that data comes from the American Community Survey. That's one major survey that the Census Bureau does. It's the largest household survey in the United States. It gives you a lot of demographic information about the country and the people in it, down to sort of, local communities, basically. So you have different levels of geography. This is a mandatory annual survey that kind of replaced the long form census questionnaire. So this is done once a year and it's released once a year by the Census Bureau. And there's a large microdata sample that's released. So it's mailed out to approximately 3.5 million households, about 70% responses. And so this data set is fairly large and is available at the Census Bureau. Okay, so it's released as PUMS, Public Use Microdata Sample, each year. There's another important survey called the Current Population Survey. It's a non-mandatory monthly phone and in-person survey, so it appears more frequently. And it's more detailed, but it goes to fewer households. It goes only to about 60,000 occupied US households. And the Current Population Survey has something called the Annual Social and Economic Supplement, ASAC, which provides much more detailed economic information, but happens only once a year. Okay, but it's particularly relevant in this case because it contains a lot of income information and so on. So there's a question in the chat. Since we know how much the genealogy of data sets matters for bias, why do so many projects utilize popular data sets assuming validity of production process? Yeah, so that's a great question for a discussion. And in fact, this is the sort of question that this talk is getting at, right? I mean, for all these years, we've been using this data set without sort of like looking under the hood of where it came from and what went into it. Okay, and so part of what we're seeing in this talk is exactly how the sausage was made. Okay, so yeah, and there are several different notable differences between the CPS and the ACS. You can look at them online, but basically, for the purpose of this talk, these are somewhat similar but different data products. So we did manage to reconstruct the UCI adult data set, and it's interesting. It took us a while, but eventually we were able to match all 4,842 records in the UCI adult data set uniquely to records in the US Census data. And the source, as it turns out, is the 1994 CPS ASAC. So it's this annual addendum to the CPS, and it's available from a service called IPUMS to this day. IPUMS, just a data provider. It's not to be confused with PUMS. Bunch of attribute names and encodings have changed from the UCI adult description, so we had to like map this back and forth a bunch of different ways. And some countries in the IPUM CPS are coded differently than the UCI adult, so there were some things we had to resolve. Yeah, again, don't confuse IPUMS with PUMS. It's a different thing. We did not recover this mysterious A final weight column that you can see in UCI adult. It stands to reason that it's some kind of sampling weight. But we didn't find it. Okay, so we did actually email Ronnie K at live.com about 25 years later after he put that email address on that website. And to our surprise, he more or less got back to us immediately. And he wrote, final weight came from the census and the description was copied into this thing that I showed you earlier already. And that's really all we have. So that seemed like a dead end. We're not able, we also emailed Barry, but we're not able to get that. Don't be too sad though. It was probably just some sampling weight. So it shows you how to adjust the records in the data set so that you get the demographic markup of the US population back. And there are various other sampling weights that are available. We just haven't been able to match this particular one. Philosophical question in the chat. Are the incentives for AI and ML recognition, publications, etc., too strongly tied to proving that the algorithm you developed beat a benchmark using the same data set somebody else used, regardless of the flaws in the data? Yeah, I think that's another good question. You know, there are sort of different benefits and disadvantages to this benchmark paradigm. I mean, it's been very successful in some ways, but yes, it also created sort of you know, perhaps a way of using data sets that turn sort of you know, or ignore certain questions regarding the source and origin of the data set, and I would agree with that. I don't think it's necessarily all about incentives, but yeah, we can discuss that later on. Yeah, you could argue that sampling weights shouldn't be used for prediction anyway, so this is maybe not the most important column to recover. So let me actually mention a few good aspects of UCI adult before. I don't want to throw this under the bus. It's not like the worst data set you could imagine. So first of all, it follows sort of established survey and data collection standards by the U.S. By the U.S. Census Bureau, and there's a lot of effort put into this. It's not an ad hoc, you know, data source, right? At least where it came from is a well-documented, rigorous survey that's used for a lot of very important policymaking in the United States. Okay, in particular, it comes from a quality sampling frame capturing the US population. It was created by skilled and compensated labor, in contrast with a lot of ad hoc Mechanical Turk data collection that we do in machine learning. And it's thoroughly documented. Okay, so you can go at the website of the Census Bureau and really look at all the ins and outs of this. And so in some sense, the census data is arguably already responsive to some of the important issues that were raised about machine learning data sets in various influential works in the community, for example, Gender Shades paper or the data sheets for data sets paper, which emphasize some of the issues with existing machine learning data sets. So yeah, but there are still some very significant issues with UCI adult. And you know, first of all, it's 25 years old, to state the obvious. So various things have changed significantly. For instance, the encodings that the US Census Bureau uses for race have changed very substantially. And state information, many other features are not included. So it underutilizes this wealth of census information or census data that we actually have. And there's a lot more that you could do. And finally, which was sort of always the most concerning to me, is that $50,000 is actually a very high income cutoff that's way above the median income, right? For instance, if you just have the all 50K baseline, that achieves about 93% accuracy in the Black population. Okay, so just because most people in that population make less than $50,000, so it's way above the median income. And so as a result, you always get this unusual effect where models have higher accuracy, for example, on the Black population than the white population, or the female population than the male population, because the prediction task was much easier in those subpopulations because the cutoff is so high. Okay. And now that we've reconstructed this data set, we can actually look at this. We can, you know, we've recovered the data, so we can set the threshold differently. The adult data on UCI had only this one cutoff, so there was no way to compare with other cutoffs. We can now draw the cutoff whichever way we want, and you can actually see how this affects things substantially. Here's the accuracy by group for a gradient boosting model. So GBM is gradient boosted decision tree model. And you can see that, you know, if you just take a majority class baseline, so all yes or all no, you get, you know, 50% accuracy at the, you know, median income, which is what you would expect. And interestingly, all the group specific accuracies kind of cross over at that point. So up until the median income threshold, your accuracy is lower on the Black population than the white population. Above that, it's higher on the Black population than the white population. And the crossover occurs roughly here, okay? One thing that's, you know, interesting is that at the 50K cutoff, the gradient boosting model is not much better than the constant predictor, okay, in the Black population. So that's a very degenerate sort of situation to study the problem in, right? It's even, in some sense, more striking with a male and female population again, you have this crossover, but the differences in accuracy are much greater. So you see that the accuracy for the female population is very high above the crossover point. And in fact, the 50K cutoff maximizes the difference between female and male accuracy. So this cutoff that was implicit in UCI adult is actually very specific. It's a very specific setting of the prediction task. And so you could worry that all this stuff that we've been doing with UCI adult is sort of specific to this kind of extreme scenario that results from this 50K cutoff. Okay, so we asked if we can get the best of the census data, so some of the good aspects of it, while addressing the issues that were specific to UCI adult. Okay, so here's what we did. So we created new data sets from available census public microdata samples using a software package that nicely wraps around census data. So it's kind of plug and play. You just import this and it does sort of all the stuff for you. It downloads the census data and turns it into a usable machine learning prediction task that you can stick into various machine learning tools. And we exposed 3 prediction problems based on this American Community Survey microdata. One is based on income prediction. It's kind of a plug-in replacement for UCI adult. And actually, yeah, that's what I'll mostly talk about. But the other tasks are an employment-related task where the prediction problem is to predict employment instability, and one relating to health coverage. And so what's nice about this data source is that it's big, it's millions of records, it's 50 states, and it's multiple years. Okay, so it's ideal for studying performance variation and distribution shift across geography and across time. Okay, so if you're interested in that sort of stuff. And so here are just some new insights from this data set that I thought were kind of interesting to me. At least they changed the way I think about the sort of fairness in machine learning. First of all, and it would take me a few plots to show you all this, to develop this in plots. I'm just going to give you the conclusions, and you'll have to look at the paper for all the plots. Okay, so the first thing we're seeing consistently is that trade-offs between statistical fairness criteria are kind of highly specific to the method and to the subpopulation. Okay, so logistic regression on Idaho can be very different from gradient boosting in Massachusetts, right? And so when you talk about statistical trade-offs between, let's say, error rates and calibration, it really bears sort of, specifying which population you're talking about. Okay, so statements about statistical fairness criteria can never be, without qualification of exactly what subpopulation you're talking about. We're also seeing a lot of variation in the effectiveness of algorithmic interventions. That too varies greatly by context, can vary by geography. It can vary whether or not you do the population or the intervention at the US population level and then look at states, or if you implement it locally at the state level. These things are very different. And this sort of observation draws attention to the question, like, what is really the right locus of intervention? Where do we even when we think about applying some algorithm to achieve some kind of fairness criterion or to perform some other intervention, where do we actually implement this? What subpopulation? And third, what's kind of interesting is that these algorithmic interventions have very interesting effects on secondary criteria. So if you're interested in, let's say, removing some disparity in one, with regards to one criterion, that can have all sorts of consequences in other criteria, right? And those will vary by method and subpopulation. Okay, and so finally, another thing that we saw consistently is that code that was developed for UCI adult actually struggles with seemingly very similar data sets. Okay, so even though all this is tabular data, and we imagined that the code would transfer pretty easily, it's actually not so easy, and we struggle quite a bit in getting code to run on these new data sets, which kind of shows that there's also a bit more we can do on the software ecosystem side in this research community. I want to leave a little bit of time on for questions. So I'm just going to give you a few takeaways and then wrap up. It's fair to say that the fairness community has recognized the importance of data sets, and there's some important papers on this topic that I mentioned. But the data and software ecosystem that the community actually relies on are still lagging. Okay, so there's kind of this dissonance between recognizing the importance of data sets, but then at least in some domains using a very limited set of data sources, namely just UCI adult when it comes to tabular data. Also, I like to say that sort of tabular data is actually pretty important for policy purposes, right? A lot of the consequential decision-making settings that we're talking about happen on these kind of small attribute tabular data sets. So the fact that we only had one or like a few to try out things on it was a little bit concerning, okay? But fortunately, the census data products provide a rich source of new high quality data sets that we make accessible through the software package that we're gonna release shortly. And hopefully you can use this both as a plug-in replacement for UCI adult, but also as a way to go well beyond UCI adult and have much more nuanced evaluations of methods and criteria for your research, okay? And finally, what we're seeing is that distribution shift and intra-data set variation pose sort of challenges in how we conceptualize fairness criteria and how we think about fairness, right? And that things that are tied to sort of statistical measures just have a lot of variation across time, geography, et cetera. And when we talk about the meaning and significance of these things, that's something we should be taking into account. All right, with that said, thank you so much. Oh, yeah, that's basically just what I said. So that's all, thanks.
Thanks so much, Moritz. That was a great talk. Lots of really important points about data that we haven't been thinking about enough. And presumably, this may prompt a lot of revisiting of past studies.
Yeah, so just to sort of shout this out there, I mean, obviously we're sort of created the data and we sort of make the data accessible, and we're looking at some of the things you could do now with those new data sets, but really that's a much broader effort to like revisit all the things that we did on UCI adult and figure out if they still stand or if they fell apart, right?
Yeah, so really looking forward to the paper where I'm sure you look at a few things, but are you open to suggesting any other things that maybe people should take a look at, or any of the highlights you think from the work which you're about to publish?
Yeah, so I think one thing that we haven't done too much is actually looking at, there are all these 300 papers that provide methods for different things. I don't think we'll be able to go very deep into how each of these methods, perform on the new data sets, just because there are too many. And so we're focusing on some high level aspects. But if you in the past have like created a method that used UCI adult, I would just love for you to, just try to run it again on this and just tell us. I mean, either publish it or just send us an email and tell us what happened, right? And that would be great for us to see what's sort of happening with things that have been developed on UCI adult or have used UCI adult heavily, and what's happening now in these new data sets.
Fantastic. And we probably have time for one more question. Carolyn's just come in with this really good one that you can see there, Moritz. I mean, I assume that your work is really saying we do need to think about moving away from one benchmark, and you're providing a tool to enable that. Is that fair?
Yeah, let me read the question real quick. So yeah, when it comes to fairness, which is so context specific, do we need a major paradigm shift away from benchmarks on particular data sets? What should this look like? Yeah, so this is interesting, right? So, there are a few things. I think we need to start to distinguish between what we can do with benchmark data set for this research community and what we cannot, right? And so I think if you're trying to simply see how well a method works for like getting demographic parity or learning fair representations or something like that, I think there is, to some extent, benchmark data set can answer that question, right? How does that method perform? How does it trade off with other things? But now when it's and we're talking about in a particular decision-making or policy setting, what should we be doing? That's not a question that can be answered from benchmark data set because it's specific to the setting, right? And so I think we need to have a better sense of what are the things that transfer from like, benchmark data to what we're actually interested in, and what are the things that do not transfer, right? So what are things that we're kind of, you need data sets like social scientists, which are very specific to what you're doing, and what are things where you're okay with machine learning data sets as sort of benchmarks data, right? And so it's kind of interesting that there isn't really that distinction yet, and we don't really have a clear sense, at least I don't have a clear sense of where to draw that line, right? What are things that I'm okay with doing on benchmark data set, and what are things where that's inadequate? And so yeah, I think that's an excellent question, and I'd love to see more work on that.
Fantastic. Thanks again, and we're starting to get a bit late in Europe, so
for sure, yeah.
But,
appreciate it.
Thank you, and thanks for the great talk. I have to say that that history was really fascinating, and learning about the origins of the UCI dataset. Sorry for the bad joke, but it was a real aha moment for me. I'm sure you've heard that before. And please send regards to Frances Sting too. We were lucky to have her in Cambridge for a year for a master's.
Awesome. Yeah. She really enjoyed it. So, yeah, great. So thanks so much, and I'm happy to take more questions by email or whatever if they come up later. But I think we're out of time, and we're mindful of the late hour in Europe.
Wonderful. So please join me in once again thanking Moritz. And because we're at the end, I think we should take the opportunity to thank all of our wonderful speakers and panelists today. And of course, thank you also to all of you for joining us and participating in the great questions. There's so much more for us to work on together and discuss. So please be in touch with speakers or with any of us organizers if you're interested in any of these areas. Thanks so much, everyone, and hope to see you soon.